Hi, welcome to Sunil Maths tutorial. From this video, we start a new lecture series according to functional analysis. Functional analysis by Sunil Maths tutorial. For this lecture series, we use the following books as reference. Introduction to Topology and Modern Analysis written by G.F. Simmons. Functional Analysis written by J.N. Sharma and A.R. Vasista. Functional Analysis written by Balmohan V. Limaya, retired professor, IIT Bombay. And I use one more book, Functional Analysis written by Professor Somasundaram. And in this lecture series, these are the following topics covered by us: Banach spaces, Hilbert spaces, and finite dimensional spectral theory. With these three units, we cover the following topics: definition and some examples of Banach spaces, continuous linear transformations, the Hahn-Banach theorem, the natural embedding of n in n double star, the open mapping theorem, the conjugate of an operator. In the chapter of Hilbert spaces, again the definition and properties of Hilbert spaces, orthogonal complements, orthogonal sets, conjugate space H star, adjoint of an operator, self-adjoint operators, normal and unitary operators, projections. In the third unit, finite dimensional spectral theory, we cover the following topics. The first one, eigenvalues and eigenvectors, matrix of a linear transformation, and spectral theorem. So our focus is mainly our focus on theorems and proofs. Remember that. Our focus on theorems and proofs. And to understand the theorems, we use some examples and some problems and their applications. Our main focus depends upon like this: theorems and proofs, examples. We solve some problems depends upon the theorems and some applications to understand the concepts. So let us start with linear space. Yes, let us start with linear space. So this linear space is also known as vector space. This linear space is also known as vector space. Remember that. So to define the linear space or vector space, we need two sets. One is L, which is a non-empty set. One is L, which is a non-empty set of vectors. And one is F, the field of scalars. So we need two sets. One is L, the non-empty set of vectors. The second one is field of scalars. And we need two operations. One is addition. Vector addition is an internal operation defined over the set of vectors. And multiplication, which is known as scalar multiplication, which is defined over L, defined in L over capital F. And this is known as scalar multiplication property. For an element A belongs to F and alpha belongs to the set of vectors, implies A alpha belongs to L. This is known as scalar multiplication property. So now let us define the linear space. A non-empty set of vectors, a non-empty set of vectors, capital L, over the field, capital F, over the field, capital F, is said to be linear space, or vector space. It is also known as vector space if it satisfies two major properties. The first one is capital V with respect to plus is an abelian group. Capital V with respect to plus is an abelian group. I mean, here V means, I think it is L, L set of vectors. L with respect to plus is an abelian group. It means the set of all vectors forms an abelian group under vector addition. The set of all vectors forms an abelian group under vector addition. And the second condition is scalar multiplication property. An element A belongs to capital F and alpha belongs to L, implies as A alpha belongs to L. This is known as scalar multiplication property. Scalar multiplication property in the set L over the field capital F. Again, these two major conditions, 1 and 2, satisfies the following minor conditions. The first one is A into alpha plus beta. A into alpha plus beta is equals to A alpha plus A beta, and the second one is A plus B into alpha is equals to A alpha plus B alpha, and the third one is AB into alpha is equals to A into B alpha is equals to A alpha into B, and 1 into alpha is equals to alpha. For all alpha comma beta belongs to the set of vectors L, A comma B belongs to the field capital F, and 1 is also a scalar from the field capital F. So linear space is also known as vector space, and it is defined like this. L is a vector space or a linear space over the field capital F if it satisfies two major conditions. L with respect to 2 plus is an abelian group, and it satisfies the scalar multiplication property. Again, these two conditions satisfies the following four conditions. So remember that A into alpha plus beta is equals to A alpha plus A beta. A plus B into alpha is equals to A alpha plus B alpha. AB into alpha is equals to A into B alpha. It is equals to A alpha into B. 1 into alpha is equals to alpha for all alpha comma beta belongs to L, and A comma B belongs to F, and 1 belongs to capital F. Instead of the symbol L, you can use V also, because it is the set of vectors. So you can write simply L of F or V of F is a vector space. Now we go for normed linear space. The next definition is normed linear space. So in the name normed linear space, you observe that there is the term linear space. So let us define a linear space capital N is said to be normed linear space. A linear space is said to be normed linear space if it satisfies for each vector small x belongs to capital N. For each vector x belongs to capital N, there exists a real number. Which is written like this: double mod x, and read as norm x. Such that it satisfies the following properties. The first one is norm x is always greater than or equals to 0, and norm x is equals to 0 implies and implied by x equal to 0. It means norm of the 0 vector is 0. And the second property is norm x plus y is less than or equals to norm x plus norm y. And the third condition is norm alpha x is equals to mod alpha into norm x. So you observe that for all, here alpha is a scalar, and n is a set of vectors. First of all, it is a linear space. And this x belongs to capital N. This is true for every element of capital N. Observe that. So normed linear space. A linear space capital N is said to be normed linear space if it for each vector x belongs to capital N, there exists a real number double mod x which is read as norm x, such that it satisfies the following conditions. The first one, norm x is always greater than or equals to 0, and norm x is equals to 0 if and only if it satisfies the condition x equal to 0. Norm x plus y is less than or equals to norm x plus norm y. Norm alpha x is equals to mod alpha into norm x, where alpha is a scalar. This n is a linear space. Remember that n is a linear space and x is a vector in capital N. So after the normed linear space, we learn about Cauchy sequence. Let us see a sequence Sn is said to be Cauchy sequence. A sequence Sn is said to be Cauchy sequence if for each for each epsilon greater than 0, for each epsilon greater than 0, there exists a positive integer. There exists a positive integer p. For each epsilon greater than 0, there exists a positive integer p such that it satisfies the condition mod Sn minus Sm is less than epsilon for all n comma m greater than or equals to p. So, a sequence Sn is said to be Cauchy sequence if for each epsilon greater than 0 there exists a positive integer p satisfying one condition mod Sn minus Sm less than epsilon for all n comma m greater than or equals to p. Remember that. So after Cauchy sequence we learn the definition of complete. So a normed linear space, a normed linear space is said to be complete, or complete normed linear space, if it satisfies the following condition. Every Cauchy sequence in it, is convergent. It means if every Cauchy sequence is convergent in a normed linear space, then that normed linear space is known as complete normed linear space. I repeat the definition. A normed linear space is said to be complete. A normed linear space is said to be complete if every Cauchy sequence in it is convergent. We go for next definition, and very important definition. Let us see Banach space. A complete normed linear space. A complete normed linear space. Is called a Banach space. Here, remember that complete means every Cauchy sequence in it is convergent. Normed means for every vector x belongs to capital N, it satisfies three different conditions. One is norm x greater than or equals to 0, and norm x is equals to 0 implies and implied by x equal to 0, and norm x plus y is less than or equals to norm x plus norm y, and norm alpha x is equals to mod alpha into norm x. This is the definition of normed linear space. And what is linear space? Linear space is a vector space. Defined over a field capital F. So Banach space is clearly a vector space. As it is, it satisfies the norm conditions. It means it satisfies the linear space as well as normed linear space definitions. And also complete means every Cauchy sequence in it is convergent. So this is the definition of Banach space. I repeat, remember that this is one of the very important definition for us. Banach space, a complete normed linear space, is known as Banach space. So let us see some two simple examples in question and answer format. Show that a normed linear space capital N is a metric space with respect to the metric D defined as d of x comma y is equals to norm x minus y. So let us prove this one. From this example, we understand that every normed linear space is a metric space. So from this question, we understand that a normed linear space is always a metric space with respect to a definition d of x comma y is equals to norm x comma x minus y. Let us prove this. Let x comma y belongs to capital N. Capital N is a I'm sorry. Let us take x comma y belongs to capital N. So n is a normal linear space. So it is a linear space. It means x minus y belongs to capital N. We observe that capital N is a linear space. Every linear space is an abelian group under addition. Every linear space is an abelian group under addition. Now we are choosing two elements x comma y belongs to capital N. Under addition it is an abelian group. Under addition is an abelian group. Apply the inverse axiom. Apply the inverse axiom for the element y. Then we get x comma minus y belongs to capital N. Apply the closure axiom under addition. X plus of minus y. X plus of minus y belongs to capital N. What it means? X minus y belongs to capital N. So x comma y belongs to capital N implies as x minus y belongs to capital N because it is a linear space. And if x minus y belongs to capital N and N is a normed linear space, N is a normed linear space, which implies norm x minus y is greater than or equals to 0. If norm x minus y is greater than or equals to 0, what it means? D of x comma y is greater than or equals to 0. Because D of x comma y is defined as norm x minus y. D of x comma y is defined as norm x minus y. This is the first condition of normed linear space. This is the first condition of a metric space. I am very sorry. D of x comma y greater than or equals to 0 is the first property of metric space. We go for D of x comma y is equals to 0. D of x comma y is equals to 0 implies and implied by norm x minus y is equals to 0. Implies and implied by x minus y is equals to 0. Implies and implied by x equal to y. What it means? D of x comma y is equals to 0. D of x comma y is equals to 0 implies and implied by x equal to y. X equal to y. D of x comma y is equals to 0 implies and implied by x equal to y. So from these two conditions, D of x comma y greater than or equals to 0 and D of x comma y is equals to 0 implies and implied by x equal to y, we said that capital N satisfies the first property of the metric space. We go for second property. Now see, D of x comma y is equals to norm x minus y. It can be written like this: norm minus of y minus x. It can be written as mod minus 1 into norm y minus x. Mod minus 1 into norm y minus x. Mod minus 1 is nothing but 1. So you can written as norm y minus x. This is nothing but d of y comma x. Therefore, we conclude that d of x comma y is equals to d of y comma x, which is the second property of metric space. We go for third property. D of x comma y is equals to norm x minus y. This is the definition, which is equals to norm x minus z. We add plus z. Norm x minus z plus z minus y. We split the norm, then we get less than or equals to norm x minus z plus norm z minus y. This is nothing but d of x comma z plus d of z comma y. Therefore, we conclude that d of x comma y is less than or equals to d of x comma z plus d of z comma y. This is the third property of metric space. From these three properties, here you observe that the first one is d of x comma y is greater than or equals to 0 and d of x comma y is equals to 0 implies and implied by x equal to y, and d of x comma y is equals to d of y comma x. d of x comma y is less than or equals to d of x comma z plus d of z comma y. From these three properties, we conclude that capital N satisfies all the properties of metric space. This shows us capital N is a metric space. So what it means? Every normed linear space is a metric space. Every normal linear space is a metric space. With respect to the metric, d of x comma y is equals to norm x minus y. d of x comma y is equals to norm x minus y. Remember that every normal linear space is a metric space. We prove one more inequality but in the same class. Let us see. Prove that mod norm x minus norm y is less than or equals to norm x minus y. Now the simplest one. Now consider, let us take x belongs to capital N, which is a normal linear space, and norm x is equals to norm of x minus y plus y. You can write, I add minus y, I plus y. So which is simply less than or equals to norm x minus y plus norm y. So here in the left side we have norm x. Now shift this norm y into left side. Norm x minus norm y is less than or equals to norm x minus y. Let it be equation number 1. Now consider in a similar manner, norm y can be written as norm y minus x plus x. So which implies as norm y is less than or equals to norm y minus x plus norm x. So you can write again norm y minus norm x. We shift this norm x into left side. So is less than or equals to norm y minus x. So again norm y minus x. Let it be equation number 2. In the left side you can write like this by making minus common. Norm x minus norm y is less than or equals to norm of minus 1 into x minus y. So by using the normal linear space property, you conclude that this is nothing but norm x minus y. Equation number 2. From this equation 1 and equation 2, you observe that from this equation 1 and equation 2, we conclude that mod norm x minus norm y is less than or equals to norm x minus y. Now consider this is the one of the inequality in the normal linear spaces, in Banach spaces. So here there is a small note point. You have to observe that. Note, norm is always continuous function. And addition and scalar multiplication are well defined over capital N because N is a linear space. Remember that. In the next class, in the next video, we will learn the examples of Banach space to understand the definition of Banach space. Before going to close the video, you observe the definition of Banach space because that is the important one here. A complete normed linear space is called a Banach space. A complete normed linear space is a Banach space. And what is complete? Every Cauchy sequence in it is convergent. And what is normed space? It satisfies three different properties of every vector x belongs to capital N. And linear space means it is a vector space. So a complete normed linear space is called a Banach space. In the next video, we learn different examples for Banach space. Happy learning. Wish you all the best. Hi, welcome to Sunil Maths tutorial Functional Analysis class number 2. In this video, we learn examples of Banach space. Before going to learn the examples, let us see the definition of Banach space. Banach space is a complete normed linear space. So what is mean by complete? Complete, every Cauchy sequence in it is convergent. Complete means every Cauchy sequence is convergent. Every Cauchy sequence is convergent. And normed linear space means it satisfies three conditions. Norm x is greater than or equals to 0, and norm x equal to 0 implies and implied by x equal to 0, and norm x plus y is always less than or equals to norm x plus norm y, and norm alpha x is equals to mod alpha into norm x. So Banach space is a complete normed linear space. Now we learn 10 examples of Banach space. Let us see the first example, and which is very basic and trivial. Example number 1. The real linear space capital R and the complex linear space capital C both are Banach spaces. Real linear space and complex linear space both are Banach spaces under the standard norm defined by norm x is equals to mod x for all x belongs to capital C or x belongs to capital R. We prove this example. So let us see, norm x is equals to 0 implies and implied by mod x equals to 0, which implies and implied by x equal to 0. What it means? The first condition of norm x equal to 0 implies and implied by x equal to 0. And norm x is equals to mod x. We know that mod x is a non-negative function. Mod x is a non-negative function. So by using that, norm x is always greater than or equals to 0. Norm x is always greater than or equals to 0. This proves the first condition of normed linear space. Let us see. Let z comma w be the complex numbers, and z bar and w bar are their conjugates of z and z respectively. Now consider z plus w whole square. Z plus w whole square. We know that in the complex space, z square can be written as z into z bar. We know that mod z square or simply z square can be written as z into z bar in the complex analysis. By using that fact, z plus w whole square can be written as z plus w into z plus w whole bar. Again we know that z plus z1 plus z2 whole bar is equals to z1 bar plus z2 bar. By using this fact, here it can be written as z bar plus w bar. Now we multiply with one another, z into z bar, z into omega bar, w bar, w into z bar, w into w bar. So we get this step. Again by using this fact, z into z bar is equals to mod z square. So this is clearly mod z square, z into z bar is equals to mod z square, w into w bar is equals to mod w square. Now we use the fact that z into z bar plus z into w bar plus w into z bar is can be written as 2zw. 2zw. That's why we replace equality by inequality. Equality by inequality. Because of we know that by complex numbers theory, z1 plus z1 into z2 bar plus z1 bar into z2 is always less than or equals to 2z1 into z2. 2z1 into z2. That's it. So this step, that's why we write here this equality becomes inequality. Now by using this RHS, this is in the form of a square plus 2ab plus b square. So which is less than or equals to a plus b whole square. It means mod z plus w whole square less than or equals to mod z plus mod w whole square. By removing squares, By removing squares on both sides, we get mod z plus w less than or equals to mod z plus mod w, which is the second property of normed linear space. And the third property, norm alpha x is equals to, by definition of norm, it can be written as mod alpha x, and mod alpha x can be written as mod alpha into mod x, where alpha is a scalar. This shows us the set capital R as well as capital C both satisfies the three properties of normed linear space. Hence, we conclude that C and R both are normed linear spaces. And we know that both complex numbers and real numbers are complete. Therefore, they are complete as well as normed linear spaces. C and R both are complete as well as they are normed linear spaces. Hence, both C and R are Banach spaces under the standard metric defined as norm x is equals to mod x. If anybody wants to proof of set of complex numbers and set of real numbers are complete, please message under the video, then I provide the proof for that. Let us see example number 2. Again, this is also one of the standard example. The linear spaces R power n and C power n. The linear spaces R power n and C power n. This power n represents the set of all n tuples. The set of all n tuples like this. X is equals to x1, x2, and so on, xn of real and complex numbers. Both are Banach spaces under the norm defined by norm x is equals to square root of x1 square plus x2 square plus and so on plus xn square. This norm can be simply represented like this. Summation over I is equals to 1 to n xi square whole power 1 by 2. This R power n is called Euclidean space and C power n is called unitary space. We go for example number 3. Again, one of the standard example. Let P be any real number such that 1 less than or equals to P less than infinity. P is a real number and it is 1 less than or equals to P less than infinity. This LP power n, standard notation, LP power n be the set of all n tuples which are consisting in the swarm x is equals to x1, x2 and so on, xn of scalars. This LP power n also a Banach space under the norm x power p is equals to summation over I is equals to 1 to n xi power p mod xi power p whole power 1 by p. This is nothing but mod x1 power p plus mod x2 power p plus and so on mod xn power p whole power 1 by p. Again, so LP power n, the set of all n tuples which are in this form, is a Banach space under this norm. We go for next example, example number 4, which is also in the similar manner as example 3 with a small difference. Again, P be a real number and 1 less than or equals to P less than infinity, and here LP is the space of all sequences. Here LP is the space of all sequences. X is equals to x1, x2 and so on, xn and so on. In the previous example, they are n tuples, but here they are infinite. They are infinite in number of scalars, satisfying the condition summation over I is equals to 1 to infinity x power n whole power p is less than infinity. It means it is a finite quantity. This summation n is equals to 1 to infinity mod x power n whole power p is a finite quantity. Then this space LP is a Banach space with the same norm defined as above. Norm xp is equals to summation n is equals to 1 to infinity mod xn power p whole power 1 by p. This example holds for all positive. Real numbers. If you replace this n by p, then you get like this. If you replace, not n by p, n is equals to 2. I'm sorry, not n or n equal to 2. If you replace this p is equals to 2, you get norm xp in place norm x2 is equals to summation over n is equals to 1 to infinity x2 xn power 2 whole power 1 by 2 whole power 1 by 2. So this example, from this example you construct many more examples. Instead of, in place of p, you can replace 2 3 4 5 like that and so on. This theorem can be very helpful by using, Riesz-Jett representation theorem. This LP is complete by using Riesz-Jett representation theorem, Riesz-Jett-Fisher theorem. In the upcoming classes we prove that theorem also. Example 5, and one of the more important example for your examination. Let us see the linear space C of all convergent sequences. Observe that C is the set of or linear space of all convergent sequences x equals to xn with the norm x is equals to supremum of xn, supremum of xn, supremum of the sequence xn such that is a Banach space. So the set of all convergent sequences defined with the norm forms a Banach space. We prove this example because of its importance for your examination. Here observe that we define the norm as norm x is equals to supremum of the sequence. Norm x is equals to supremum of the sequence. First we show that it is a normed linear space, and then we show that it is a complete. It satisfies the completeness property. It means every Cauchy sequence in it is convergent. Right. Mod xi is always greater than or equals to 0. So obviously norm x is greater than or equals to 0. Norm x equals to 0 implies and implied by definition supremum of xn is equals to 0. If supremum of the sequence is 0, then each term xn equal to 0. It means x equal to 0. So norm x equal to 0 implies and implied by x equal to 0. This shows us the first condition of the normed linear space. First condition of the normed linear space. We go for second condition. Let us take x is equals to sequence xn, y is equals to sequence yn be two elements of C. Remember that C is the space of or collection of all convergent sequence. All convergent sequences. Now x plus y is equals to sequence xn plus yn. Now by definition of norm x plus y is equals to supremum of xn yn, where you can write 1 less than or equals to n less than infinity. It is obvious. So this equality becomes inequality by splitting the supremum of xn plus supremum of yn. What is supremum of xn? Norm x. And what is supremum of yn? Norm y. This shows as norm x plus y is less than or equals to norm x plus norm y. This is nothing but second property of normed linear space. Second property of normed linear space. We go for third one. Consider alpha is any scalar. Now norm alpha x is equals to supremum of mod alpha xn. By the properties of supremum, it can be written as mod alpha into supremum xn, mod alpha into norm xn. This condition shows as third property of normed linear space. Hence we conclude that this set satisfies all the three properties of a normed linear space. Therefore, capital C satisfies all the properties of normed linear space. This shows us C is a normed linear space. Now we have to prove that this C is complete. We have to prove that this C is complete. What is mean by complete? Every Cauchy sequence in it is convergent. So right, now define a Cauchy sequence in it. X power n be a Cauchy sequence in C. X power n be a Cauchy sequence in C. Then this xn can be written as x1 power n, x2 power n, x3 power n, and so on, xi power n, and so on. We assume that C is the set of all convergent sequences. The set of all convergent sequences. Obviously, by using that example, by using that definition, capital C consisting of all convergent sequences. So by definition of C, for each epsilon greater than 0, there exists a positive integer n naught satisfying the condition x power n minus x power m is less than epsilon. This is less than epsilon. This condition is written by the definition of, we can take epsilon by 3. We can take epsilon by 3. Instead of epsilon, let us take epsilon by 3. X power n minus x power m is less than epsilon by 3. I'm sorry. This inequality can be written by using the definition of Cauchy sequence. So right, after that, norm x power n minus x power m is less than epsilon means, epsilon by 3 means, by the definition of norm, supremum of over I, xi power n, xi power m is less than epsilon by 3. By applying the definition of the norm in this example. Hence, for each fixed I, the sequence of real numbers xi power n is a Cauchy sequence in capital R, and we know that capital R is complete. Capital R is complete means every Cauchy sequence in it is convergent. This shows as the limit xi power n is equals to xi for each fixed I. Now we fixing n greater than n naught and letting m tends to infinity in the above inequality xi power n minus xi power m less than epsilon by 3, we get xi power n minus xi is always less than epsilon by 3. This shows us supremum of xi power n minus xi is less than epsilon. This shows us norm x power n minus x tends to infinity as n tends to infinity, where this x is equals to the sequence xi. Now it is remaining to prove that x belongs to capital C. The limit of the sequence also belongs to capital C. It is enough to show that it is a Cauchy sequence in capital R because it consists of all sequences which are convergent. So now xi power n naught is equals to xi power x1 power n naught, x2 power n naught and so on xn power n naught is a convergent sequence. So xi power n naught is a Cauchy sequence. Apply the definition of Cauchy sequence. You get xi power n naught minus xj power n naught is less than epsilon by 3. Now you can write like this. Xi minus xj is equals to xi minus xi power n naught plus xi power n naught. I add and subtract the same terms. Similarly, xj power n naught minus xj power n naught. By splitting the terms, this equality becomes inequality norm x minus x power n naught plus norm mod xi power n naught minus xj power n naught plus norm x power n naught minus x. By previous argument, we have all these inequalities less than epsilon by 3 plus epsilon by 3 plus epsilon by 3. Every term is less than epsilon by 3. So by using equation 1. Hence we conclude that mod xi minus xj is less than epsilon. It means this xi is a Cauchy sequence in capital R. If this xi is a Cauchy sequence in capital R, obviously this x belongs to capital C. This shows us every Cauchy sequence in C is convergent. Hence, capital C is complete. This condition shows us capital C is complete. Already we proved that it is a normed linear space. Now we show that it satisfies the completeness property. Therefore, C is a complete normed linear space. Hence, C is a Banach space. Remember that proof of this example is lengthiest one, and go through it carefully. So I repeat the statement of this example. Observe that the linear space C of all convergent sequences x is equals to xn with the norm x is equals to supremum of the sequence xn such that where 1 less than or equals to n less than infinity is a Banach space. Now let us see example number 6. Example number 6. Closed interval a comma b is a bounded and closed interval. Then the linear space C of closed interval a comma b. This symbol represents the set of all continuous functions defined on closed interval a comma b is a Banach space with the norm f is equals to supremum of f of x where each x belongs to closed interval a comma b. This C of a comma b, this is important. C of a comma b, C of closed interval a comma b means the set of all continuous functions defined on the closed interval a comma b is a Banach space with the standard norm supremum of f of x such that x belongs to closed interval a comma b. And let us take one more example, example number 7, C of x. C of x, remember that, where x is a compact metric space, where x is a compact metric space, it satisfies the compactness property. C of x be the set of all continuous real valued functions. C of x be the set of all continuous real valued functions defined over the compact metric space capital X. This is also a Banach space with the norm defined by norm f is equals to supremum of f of x such that x belongs to capital X. It means the set of all continuous functions defined over a closed interval by using previous example, the set of all continuous real valued functions defined over a compact metric space, both are Banach spaces with the metrics defined in the same way. The main difference in the examples is here the closed interval a comma b, here the compact metric space capital X. That's it. We go for next one and depends upon topological space. C of t. C of t. The set of the C of t denote the linear space of all bounded continuous real valued or complex valued. Remember that. C of t denotes the set of all bounded continuous real valued or complex valued functions over a topology capital T, over a topological space capital T. Then C of t is also a Banach space with the norm f is equals to supremum of mod f of x where x belongs to capital T. In the example number 6, 7 and 8, you observe the difference. In first example, we choose a closed interval a comma b, example number 6. In the second one, compact metric space capital X. In the third one, we use the topology T, but the nature of the norm is same, supremum of mod f of x. We go for example number 9, which is a measurable function. Let capital X be any measurable space with measure mu. X is a measurable space with measure mu and P be any positive integer. Then LP consists of all measurable functions. Then LP consists of all measurable functions defined on capital X such that f of x power p is integrable. Remember that LP is the set of all measurable functions defined on capital X such that each measurable function is associated with another function f of x which is integrable. Then LP is also a Banach space defined by the norm f is equals to integral over x mod f power p d mu whole power 1 by p. And last example, observe that consider the linear space of all n tuples x is equals to x1, x2 and so on xn of scalars, and the norm is defined by norm x infinity. Norm x infinity is equals to maximum of mod x1 comma x mod x2 and so on mod xn. Then this linear space is a Banach space and it is denoted by L infinity power n. L power n infinity, L power n infinity, norm x infinity. So observe that in this class we learn 10 examples of Banach space, 10 examples of Banach space, and we prove two examples, example number 1 and even example number 5. And we prove and we state some examples over the closed interval a comma b and over a compact metric space capital X and a topology capital T, and also we see an example over measurable functions also. So from these 10 examples you can understand Banach spaces, various Banach spaces over different types of functions. So I conclude this class. In the next class we learn some inequalities according to functional analysis. All the best. Hi, welcome to Sunil Maths tutorial. Functional analysis, class number 3. In this video, we learn Holder's inequality. Let us see the statement of Holder's inequality. Let x is equals to x1, x2 and so on xn. Y is equals to y1, y2 and so on yn denotes n tuples of scalars. N tuples of scalars. They may be either real or complex numbers. That scalars may be either real or complex numbers. And the norm defined like this. Norm x is equals to norm x over p is equals to summation over I is equals to 1 to n mod xi power p whole power 1 by p for all p greater than or equals to 1. For all p greater than or equals to 1. Then the Holder's inequality can be written like this. Summation over I is equals to 1 to n mod xi yi less than or equals to norm x over p norm y over q. You can replace this q by p also. Okay, now we prove this inequality. We learn the proof of this inequality. Suppose if x is equals to 0 or y is equals to 0. If any of the tuple is 0, if either x is equals to 0 or y is equals to 0, then the inequality is trivially true, is simply true. There is nothing to prove. If any one of the vector either x is equals to 0 or either x is equals to 0 or y is equals to 0, one of the vector is 0, then obviously the inequality is true. There is nothing to prove. So let us take x and y be non-zero vectors. Let us take x and y be non-zero vectors. Both are non-zero vectors. So if any one of them is 0, then it is not equal, then the trivially, there is nothing to prove that inequality is trivially true. So x is not equals to 0 and y is also not equals to 0. To prove the Holder's inequality, to prove this Holder's inequality, we use the following lemma. We use one lemma. Lemma means it is a standard result. It is a standard result. That is, if ai greater than or equals to 0, comma bi greater than or equals to 0, then ai into bi is less than or equals to ai power p by p plus bi power q by q. Let it be equation number 1. Where remember that both p and q real numbers and greater than 1, they satisfies one condition. 1 by p plus 1 by q is equals to 1. 1 by p plus 1 by q is equals to 1. Remember that. So to prove the Holder's inequality, we use this standard result. Observe that if anyone needs this proof of this standard result, mention in the comments, then I can prove this result. I can make one more video to prove this inequality. So in the same inequality, put ai is equals to mod xi by norm p and bi is equals to mod yi by norm yq. We replace in equation 1 ai by mod xi by norm xp, bi by mod yi by norm yq. In equation 1 we get. Simply we get ai mod xi by norm xp to mod yi by norm yq is less than or equals to 1 by p mod xi by norm xp whole power p plus 1 by q mod yi by norm yq whole power q. Whole power q. Now the left side can be written like this, simply mod xi yi divided by norm xp norm yq is less than or equals to. So the right side cannot be changed, as it is we have 1 by p mod xi by norm xp power p, here also power p, plus 1 by q mod yi power q by norm yq power q. That's it. Now taking summation on both sides, taking summation over I is equals to 1 to n on both sides. In the left and right sides, if we take summation over I is equals to 1 to n, then the same inequality becomes summation over I is equals to 1 to n mod xi yi divided by norm xp norm yq less than or equals to 1 by p summation over I is equals to 1 to n mod xi power p by norm xp power p plus, in a similar manner you can write 1 by q summation over I is equals to 1 to n mod yi power q divided by norm yq power q. By the definition of norm, the left side is as it is you have. So same you have in the left side, summation over I is equals to 1 to n mod xi yi divided by norm x norm y according to p and q, which is less than or equals to 1 by p. By applying the definition of norm here in the statement we have, here it is the definition of norm. Let us see. Norm xp is equals to summation over I is equals to 1 to n mod xi power p whole power 1 by p. If you shift this whole power 1 by p into left side norm x power p, you simply, this norm can be written like this. Norm xp power p is equals to summation over I is equals to 1 to n mod xi power p. Mod xi power p. We use this result in our derivation part here. We use the same result in our derivation part here. So that can be written as norm x power p divided by norm x power p plus 1 by q norm y power q divided by norm y power q. So according to the same definition of the norm, you observe that the numerator and the denominator are same in both the steps here and here. The numerator and denominator are same, so they get cancelled and you get 1. So that left side completely takes the form summation over I is equals to 1 to n mod xi yi divided by norm xp into norm yq is less than or equals to 1 by p plus 1 by q. In the lemma, we assume that 1 by p plus 1 by q is equals to 1. So we assume that 1 by p plus 1 by q is equals to 1. So by using that result, this must be equivalent to 1. It means summation over I is equals to 1 to n mod xi yi divided by norm xp norm yq is less than or equals to 1. Now shift the denominator into right side, 1 into that term is you get the norm. Summation over I is equals to 1 to n mod xi yi is less than or equals to norm xp into norm yq. That's it. This is the required statement of the Holder's inequality, which is required, which is the required result. That's it. So one of the important inequality which is very useful to prove different theorems in functional analysis. If you take here, if you take the value of P and the value of Q is equals to 2. If you take the value of P and Q is equals to 2, then obviously this inequality becomes summation over I is equals to 1 to n. Summation over I is equals to 1 to n mod xi yi is less than or equals to norm x2 norm y2, which is known as Cauchy inequality, which is known as Cauchy's inequality. So if you take P value and Q value is equivalent to the number 2, then Holder's inequality becomes Cauchy's inequality. So after that, so you can apply the Holder's inequality for non-negative real valued functions also. So Holder's inequality can be applied. Holder's inequality can be applied for non-negative real functions also. Non-negative real functions. Non-negative real valued functions. Real valued functions like this. Suppose f comma g both are non-negative real valued functions defined over a closed interval a comma b. These f and g are non-negative real valued functions defined over the closed interval a comma b. Then the Holder's inequality can be written like this. Integral a to b mod f of x into g of x is dx less than or equals to integral a to b mod f of x power p dx whole power 1 by p into you can write g of x also integral a to b mod g of x power p, or you can write q also dx whole power 1 by q. That's it. So Holder's inequality can be applied for non-negative real valued functions also. In the Holder's inequality, same, if you replace p and q by a real number 2, then you get the Cauchy-Schwarz inequality or Cauchy's inequality. So this is the complete information of Holder's inequality. In the next class, we will learn about Minkowski's inequality. That's it. Keep learning. Hi, welcome to Sunil Maths tutorial, Functional Analysis, class number 4. In this class, we learn about Minkowski's inequality and its proof. If p greater than or equals to 1, then the Minkowski inequality can be written in this form. Norm x plus y p less than or equals to norm xp plus norm yp. Observe the difference between Holder's and Minkowski's inequality. In the previous class, we learned the proof of the Holder's inequality. Now, we learn the Minkowski's inequality. In other words, the same inequality can be written like this. Summation over I is equals to 1 to n. Summation over I is equals to 1 to n. Mod xi plus yi power p whole power 1 by p is less than or equals to summation over I is equals to 1 to n mod xi power p whole power 1 by p plus summation over I is equals to 1 to n mod yi power p whole power 1 by p where p and q satisfies this condition. 1 by p plus 1 by q is equals to 1. 1 by p plus 1 by q is equals to 1. So let us see the proof. If p is equals to 1, then Minkowski inequality is, then there is nothing to prove. Then there is Nothing to prove because it is trivially true. If p is equals to 1, then the inequality is always true. Minkowski inequality is true. The Minkowski inequality is true. So assume that take p greater than 1. Take p greater than 1. Yes, now we prove the inequality. To prove this, let us consider summation over I is equals to 1 to n mod xi plus mod yi whole power p. This can be written like this. You can write, everybody knows the formula, a power m plus n is equals to a power m into a power n. By using that formula, you can write like this: summation over I is equals to 1 to n mod xi plus mod yi whole power p minus 1 into mod xi plus mod yi. That's it. So after multiplying and using this formula, a power m plus n is equals to a power m into a power n, you get again same term, summation I is equals to 1 to n mod xi plus mod yi whole power p. So in the RHS, you can multiply summation over I is equals to 1 to n mod xi plus mod yi whole power p minus 1 into mod xi plus mod xi plus mod yi whole power p minus 1 into mod yi. We split the term. So this is summation applied for whole term. So we multiply with the summation this term with xi and again the same term with yi also. Now we can split the mod. If you split the mod, then this is equals to becomes, if you split the mod, this is equals to, or this equality becomes inequality less than or equals to summation over I is equals to 1 to n mod xi plus mod yi whole power p minus 1 into mod xi plus summation over I is equals to 1 to n mod xi plus mod yi whole power p minus 1 into mod yi. Let it be equation number 1. Now in the RHS we have two terms. The first term is this one, summation over I is equals to 1 to n mod xi plus yi power p minus 1 into mod xi, and in the same term the difference is only mod yi. Now applying the Holder's inequality, applying Holder's inequality for both the terms in the RHS. For both the terms in RHS of equation 1. In RHS of equation 1 we get. What it means? We are applying the Holder's inequality for the two terms. This is the first term and the second term of the equation 1. So if you apply the Holder's inequality for first term, you get summation over I is equals to 1 to n mod xi plus mod yi whole power p minus 1 into mod xi is less than or equals to, we are applying the Holder's inequality, is less than or equals to summation over I is equals to 1 to n mod xi power p whole power 1 by p into summation over I is equals to 1 to n mod xi plus mod yi power p whole power, sorry, not power p, p minus 1 whole power 1 by q, whole power 1 by q, sorry, whole power 1 by q. So after applying this, just a minute, we are applying the Holder's inequality. We are applying the Holder's inequality for the first term as well as for the second term. Whole power p minus 1 whole power q whole power 1 by q. Yes, you are right. That's it. That's it. That's correct. Here you have to write. Here you have to write. I'm sorry. Yes. This is p minus 1 power q whole power 1 by q. This is Holder's inequality because we know that by the definition of Holder's inequality, summation over I is equals to 1 to n mod xi yi is less than or equals to summation over I is equals to 1 to n mod xi power p whole power 1 by p into summation over I is equals to 1 to n mod yi power p whole power 1 by q. So by applying the same, we get this. So which is again less than or equals to summation over I is equals to 1 to n mod xi power p whole power 1 by p into summation over I is equals to 1 to n mod xi plus mod yi power, here you observe that p minus 1 into power q means p minus 1 into q whole power 1 by q, whole power 1 by q. Now you have to simplify this term p minus 1 into q. I'm sorry, p minus 1 into q. It is equals to pq minus q, pq minus q. What is the actual result? 1 by p plus 1 by q is equals to 1. So you can write p plus q by pq is equals to 1. You can write by cross multiplying p plus q is equals to pq. So if you write pq is equals to p plus q, then you get p plus q minus q. So plus q minus q cancel, you get p. So what is final result? What is final result? P minus 1 into q is equals to p. So applying that result here, you get which is less than or equals to, the first term is as it is, summation over I is equals to 1 to n mod xi power p whole power 1 by p summation over I is equals to 1 to n mod xi plus mod yi. P minus 1 into q becomes p whole power p whole power 1 by q. Let it be equation number 2. Similarly, the second term in the RHS of equation 1. Similarly, summation over I is equals to 1 to n mod xi plus mod yi whole power p minus 1 into mod yi is less than or equals to, you can write same step, but instead of xi you have yi, instead of xi you have yi. Summation over I is equals to 1 to n mod yi power p whole power 1 by p into summation over I is equals to 1 to n mod xi plus mod yi power p whole power 1 by q. Let it be equation number 3. Using equations 2 and 3 in equation 1 we get Now we use equation 2 and equation 3 here in this equation number 1. We replace these two terms. This term is represented in equation 2 and this term represented in equation 3. So this term here, this term is replaced by equation 1 and this term is replaced by equation 3. By replacing that both the equations, both the terms, we get summation over I is equals to 1 to n, summation over I is equals to 1 to n mod xi plus mod yi whole power p is less than or equals to summation over I is equals to 1 to n mod xi power p whole power 1 by p plus summation over I is equals to 1 to n mod yi power p whole power 1 by p into you can write one more term. What is that? That is the common term of equation 2 and 3. You see here in equation 2 as well as in equation 3, this term is same. Here and here. These two terms are same. So let us use both the terms here. So plus, not plus, multiplying. We are multiplying summation over I is equals to 1 to n mod xi plus mod yi whole power p whole power 1 by q. That's it. Now divide on both the sides with the same term. Divide on both sides with summation over I is equals to 1 to n mod xi plus mod yi power p whole power 1 by q. We are dividing the above equation on both the sides with the same term. By dividing with the term, this term cancel in the RHS and we get the same term in the denominator of the LHS. So simply you get summation over I is equals to 1 to n mod xi plus mod yi power p divided by summation over I is equals to 1 to n mod xi plus mod yi whole power p whole power 1 by q. The numerator and the denominator are same but the exponents are different. Here in the numerator the exponent is 1 and in the denominator the exponent is 1 by q. That's it, which is less than or equals to. In the RHS, after dividing, this term get cancelled, so you get only simply two terms. The first one is summation over I is equals to 1 to n mod xi power p whole power 1 by p plus summation over I is equals to 1 to n mod yi power p whole power 1 by p. You have to simplify in the left side only. So let us shift this denominator into numerator. You simply get summation over I is equals to 1 to n mod xi plus mod yi power p whole power 1 minus 1 by q. Everybody knows that a power m by a power n is equals to a power m minus n. By using that result you get here 1 minus q. So which is less than or equals to, again same terms, summation over I is equals to 1 to n mod xi power p whole power 1 by p plus summation over I is equals to 1 to n mod yi power p whole power 1 by p. In the left side already we know that 1 by p plus 1 by q is equals to 1. So 1 by p is equals to 1 minus 1 by q. So here in the left side 1 minus 1 by q is replaced by 1 by p. So after replacing that we get this. summation over I is equals to 1 to n mod xi plus mod yi power p whole power 1 by p is less than or equals to, the RHS is again same, so no need to worry about it, it is the same, summation over I is equals to 1 to n mod xi power p whole power 1 by p plus summation over I is equals to 1 to n mod yi power p whole power 1 by p. Now in the LHS you can observe that there is a result or summation over I is equals to 1 to n mod xi plus yi power p whole power 1 by p is always less than or equals to summation over I is equals to 1 to n mod xi plus mod yi power p whole power 1 by p. What is the difference between these two terms? You observe that here mod xi mod of xi plus yi, but here we split the mod xi plus mod yi. That is the main difference between them. Using this result in the above inequality, we get the left hand side takes the form summation over I is equals to 1 to n mod xi plus yi power p whole power 1 by p whole power 1 by p is less than or equals to, again the right side is same, summation over I is equals to 1 to n mod xi power p whole power 1 by p plus summation over I is equals to 1 to n mod yi power p whole power 1 by p. Now use the norm symbol. If you use the norm symbol, then the left side, this term can be written like this. If you use the mod symbol, this term can be written as norm x plus y p less than or equals to norm xp plus norm yp, which is the required condition, hence proved. This is the required Minkowski inequality. You observe that this derivation part is somewhat confusion. At the same time, it is very simple and clear. So observe that by using the screenshots, you can write the notes also. So in the next video, we learn some another theorems according to functional analysis. At the same time, you remember that this Minkowski inequality can be applied. For this inequality applied for real valued functions which are non-negative. Suppose f comma g are non-negative real valued functions defined over a closed interval a comma b. These two are non-negative real valued functions defined on a closed interval a comma b. Then the Minkowski inequality can be written like this: integral a to b mod f of x plus g of x power p dx whole power 1 by p is always less than or equals to integral a to p mod f of x power p dx whole power 1 by p plus integral a to b mod g of x power p dx whole power 1 by p. So Minkowski inequality can be applied for real valued functions which are non-negative over a closed interval a comma b. That's it. In the next video, we'll learn a theorem according to the functional analysis. That's it. Hi, welcome to Sunil Maths tutorial, functional analysis, class number 5. In this video, we'll learn a theorem. Let us see the statement. Capital M be a closed linear subspace of a normed linear space capital N. The norm of the coset x plus m in the quotient space n by m is defined by norm x plus m is equals to infimum of norm x plus m where m belongs to capital M. Then n by m is a Normed linear space. Further, if n is a Banach space, then so n by m. It means n by m is also a Banach space. Now we observe that we prove this theorem in three parts. In the first part, introduction, we give introduction to the statement and understand the statement elaboratedly. And then in the second step, we prove that n by m is a Normed linear space. And then in the third step, we prove that n by m is a Banach space. So to prove the theorem, we use these three steps. So right, first one, introduction. By data, capital N is a Normed linear space and capital M be a closed linear subspace of capital N. N is a Normed linear space and it is, observe that M is the closed subspace of capital N. Now the quotient space N by M is defined as the set of all cosets, the set of all left cosets. So left cosets means 0 plus m, x plus m, y plus m and so on, where the elements 0, x, y and so on, they are belongs to capital N. They are belongs to capital N. And observe that capital M is equals to 0 plus m is the additive identity in the quotient space n by m. That is the 0 element. 0 plus m is the 0 element in n by m. And additive inverse of any element x plus m, the additive inverse of the element x plus m is given by minus x plus m. Because you observe that capital N is a linear space. Capital N is a linear space. Linear space means it is a vector space. Every vector space is an abelian group under addition. Abelian group with respect to addition. So the additive inverse of the element x plus m is given by minus x plus m. And then we go for, by given data, definition of norm. So norm x plus m is equals to infimum of norm x plus m such that small m belongs to capital M. So x plus m is a left coset. Observe that it is a left coset in n by m. Since norm is always non-negative, so norm x plus m is also greater than or equals to 0. By definition of norm x plus m, it is defined by infimum and norm is positive. Norm is always positive and it is defined by infimum. It means this set is always bounded below. This set is always bounded below. You see here, this infimum set is always bounded below. If it is bounded below and already we say that it is positive, so norm of x plus m is always greater than or equals to 0. Further, suppose that norm x plus m is equals to 0. If norm x plus m is equals to 0, then we observe that infimum of norm x plus m such that m belongs to capital M is also equivalent to 0. This condition from definition. By the definition of norm in this theorem, in the present theorem, norm is defined by infimum of norm x plus m. So this term is equivalent to 0 means infimum is also 0. If the infimum of this set is equivalent to 0, there must be a sequence mk which defined over capital M, such that norm x plus mk converges to 0 as k tends to infinity. It means norm x plus mk tends to 0 means that mk converges to minus x. Mk converges to minus x means that minus x belongs to capital M. Minus x belongs to capital M means x belongs to capital M, because M is a linear subspace. Capital M is a linear subspace. So every linear space is a vector space and every vector space is an abelian group under addition. So whenever x belongs to capital M, minus x also belongs to capital M. If minus x belongs to capital M, then x also belongs to capital M. So if here x belongs to capital M implies as x plus m is equals to m. This shows us norm x plus m greater than or equals to 0 and norm x plus m is equals to 0 implies and implied by x plus m is equals to m. Hence, this first condition shows that this satisfies the first property of the normed linear space. This is the first property of normed linear space. Let us take two elements, x plus m and y plus m belongs to n by m. Now norm x plus m plus y plus m is equals to infimum of x plus m plus norm y plus m. So you can split this or addition of cosets. By using the addition of cosets, you can write like this: x plus m plus y plus m. This simply written as x plus y plus m. This is the addition of cosets. So infimum of x plus y plus m. So infimum of norm x plus y plus m1 plus m2. So this can be split again, norm x plus m1 plus x plus m2. Whenever we split the norm, if you divide the above set into two sets, then this equality becomes inequality less than or equals to infimum of norm x plus m1 plus infimum of norm y plus m2. This is nothing but norm x plus m plus norm y plus m. Hence, norm x plus m plus y plus m is less than or equals to norm x plus m plus norm y plus m. This is the second property of the normed linear space. We go for third one. Norm alpha into x plus m. Right. Norm alpha into x plus m is equals to infimum of norm alpha into x plus m. This can be written as infimum of mod alpha into norm x plus m. We know the property mod or norm small a into alpha or small a into norm small a into x is equals to mod a into norm x. Mod a into norm x. By using that condition, here it can be written as mod alpha into norm x plus m. Right now, mod alpha is a constant, so right outside the set mod alpha into infimum of norm x plus m. This is nothing but mod alpha into norm x plus m. Hence, this proves the third condition. Norm of alpha into x plus m is equals to mod alpha into norm x plus m. This shows us from the conditions 1, 2, 3. Here you observe that this is condition number 1, and this is condition number 2, and this is condition number 3. From conditions 1, 2, 3, we conclude that n by m is a normed linear space. This is the second part of the theorem. In the third part, we prove that n by m is a Banach space. This quotient space is a Banach space by assuming n is a Banach space. So assume that capital N is a Banach space. Banach space means a complete normed linear space. We prove that n by m is also a Banach space. For this, to prove this, we start with a Cauchy sequence. In the quotient group or in the quotient space n by m, and we have to show that it has a convergent sequence. We take a Cauchy sequence in n by m and we show that it has a convergent subsequence in n by m. We know that if a Cauchy sequence has a convergent subsequence, then obviously a Cauchy sequence has a convergent subsequence means that Cauchy sequence is always convergent. So, right. Now we find a sequence xn plus capital M of original Cauchy sequence such that we are going to define a Cauchy sequence xn plus m such that it satisfies the condition norm x1 plus m minus x2 plus m is less than 1 by 2. Observe this condition, norm x1 plus m minus x2 plus m is less than 1 by 2. Next one, norm x2 plus m minus x3 plus m is less than 1 by 2 square. Next one, norm x3 plus m minus x4 plus m is less than 1 by 2 power m. In general, norm xn plus m minus xn plus 1 plus m is less than 1 by 2 power n. Right. We prove that this sequence is convergent in n by m. Now we define a sequence with satisfying all these conditions. Now we show that this sequence is convergent in the quotient space n by m. So let us begin by choosing vectors y1, y2, y3 and so on according to x1 plus m and x2 plus m and so on. Choose y1 in x1 plus m and y2 in x2 plus m satisfying the condition norm y1 minus y2 is less than 1 by 2. Choose y3 in x3 plus m. We are choosing, observe that, y1 in x1 plus m, y2 in x2 plus m, y3 in x3 plus m, satisfying the condition mod norm y2 minus y3 less than 1 by 2 square. By continuing this process, we get a sequence yn satisfying the condition norm yn minus yn plus 1 is less than 1 by 2 power n. So assume that m is less than n. And now norm ym minus yn is equals to. We add some terms and subtract the terms. Ym minus ym plus 1 plus ym plus 1 minus ym plus 2 plus ym plus 2 and so on. So by splitting the terms which is less than or equals to, we know that norm x plus y is less than or equals to norm x plus norm y. So let us split the terms. Norm ym minus ym plus 1, norm ym plus 1 minus ym plus 2 plus norm ym plus 2 minus ym plus 3 and so on norm yn minus 1 minus yn. So already we give some properties. Norm y1 minus y2 is less than 1 by 2. Norm y2 minus y3 is less than 1 by 2 square. By giving that properties, by giving the same properties here, norm ym minus ym plus 1 is less than 1 by 2 power m. The second term, norm ym plus 1 minus ym plus 2 is less than ym 1 by 2 power m plus 1. And the third term gives 1 by 2 power m plus 2 and so on. Obviously, this series is a geometric progression. By applying the geometric progression convergent formula 1 by 2 power m minus 1, a by 1 minus r, a by 1 minus r. So 1 by 2 power m minus 1. So obviously you get norm ym minus yn is less than or equals to 1 by 2 power m minus 1. From this inequality we conclude that yn is a Cauchy sequence. Yn is a Cauchy sequence. From this inequality, so norm ym minus yn is less than 1 by 2 power m minus 1. From this conclusion, we conclude that from this inequality, we conclude that yn is a Cauchy sequence. Yn is a Cauchy sequence in capital N. Yn is a Cauchy sequence in capital N and n is a Banach space. Every Banach space is complete. Complete means every Cauchy sequence in it is convergent. What is mean by complete? Every Cauchy sequence in it is convergent. Yn is a Cauchy sequence in n. Therefore, yn converges to y for some vector y in n. So right, finally we show that xn plus m is converges to y plus m. So take this norm yn plus xn plus m, norm xn plus m minus y plus m is equals to, by subtraction of cosets, norm xn minus y plus m. So which is less than or equals to infimum of norm xn minus y plus m, which is less than or equals to norm xn minus y plus m. So by our definition, yn is equals to xn plus m, and since yn converges to y, so the sequence xn plus m is also converges to y. So applying the same here, norm xn plus m minus yn plus m converges to 0. It means xn plus m converges to yn plus m. It means every Cauchy sequence in xn plus m, in n by m is convergent. It means n by m is complete. It means n by m is a normal linear space and complete. It means n by m is Banach space. That is the definition of Banach space. Banach space is a complete normal linear space. So in this theorem we prove all the three parts. In the introduction we learn about the statement, and in the second part we prove that n by m is a normal linear space, and in the third part we prove that n by m is a Banach space by assuming n is a Banach space. In the next video we learn another theorem. Keep learning. Hi, welcome to Sunil Maths tutorial, functional analysis, class number 5. In this video we learn a theorem. Let us see the statement. Capital M be a closed linear subspace of a normed linear space capital N. The norm of the coset x plus m in the quotient space n by m is defined by norm x plus m is equals to infimum of norm x plus m, where m belongs to capital M. Then n by m is a normed linear space. Further, if n is a Banach space, then so n by m. It means n by m is also a Banach space. Now we observe that we prove this theorem in three parts. In the first part, we give introduction to the statement and understand the statement elaboratedly, And then in the second step we prove that n by m is a normed linear space, and then in the third step we prove that n by m is a Banach space. So to prove the theorem we use these three steps. So right, first one, introduction. By data, capital N is a normed linear space and capital M be a closed linear subspace of capital N. N is a normed linear space and it is, observe that M is the closed subspace of capital N. Now the quotient space N by M is defined as the set of all cosets, the set of all left cosets. So left cosets means 0 plus m, x plus m, y plus m and so on, where the elements 0, x, y and so on, they are belongs to capital N. They are belongs to capital N. And observe that capital M is equals to 0 plus m is the additive identity in the quotient space N by M. That is the 0 element. 0 plus m is the 0 element in N by M. And additive inverse of any element x plus m, the additive inverse of the element x plus m is given by minus x plus m. Because you observe that capital N is a linear space. Capital N is a linear space. Linear space means it is a vector space. Every vector space is an abelian group under addition. Abelian group with respect to addition. So the additive inverse of the element x plus m is given by minus x plus m. And then we go for, by given data, definition of norm. So norm x plus m is equals to infimum of norm x plus m such that small m belongs to capital M. So x plus m is a left coset. Observe that it is a left coset in N by M. Since norm is always non-negative, so norm x plus m is also greater than or equals to 0. By definition of norm x plus m, it is defined by infimum, and norm is positive. Norm is always positive and it is defined by infimum. It means this set is always bounded below. This set is always bounded below. You see here, this infimum set is always bounded below. If it is bounded below, and already we say that it is positive, so norm of x plus m is always greater than or equals to 0. Further, suppose that norm x plus m is equals to 0. If norm x plus m is equals to 0, then we observe that infimum of norm x plus m such that m belongs to capital M is also equivalent to 0. This condition from definition. By the definition of norm in this theorem, in the present theorem, norm is defined by infimum of norm x plus m. So this term is equivalent to 0 means infimum is also 0. If the infimum of this set is equivalent to 0, there must be a sequence mk which defined over capital M such that norm x plus mk converges to 0 as k tends to infinity. It means norm x plus mk tends to 0 means that mk converges to minus x. Mk converges to minus x means that minus x belongs to capital M. Minus x belongs to capital M means x belongs to capital M, because M is a linear subspace. Capital M is a linear subspace. So every linear space is a vector space, and every vector space is an abelian group under addition. So whenever x belongs to capital M, minus x also belongs to capital M. If minus x belongs to capital M, then x also belongs to capital M. So if here x belongs to capital M implies as x plus m is equals to m. This shows us norm x plus m greater than or equals to 0, and norm x plus m is equals to 0 implies and implied by x plus m is equals to m. Hence, this first condition shows that this satisfies the first property of the normed linear space. This is the first property of normed linear space. Let us take two elements, x plus m and y plus m belongs to N by M. Now norm x plus m plus y plus m is equals to infimum of x plus m plus norm y plus m. So you can split this or addition of cosets. By using the addition of cosets, you can write like this: x plus m plus y plus m. This simply written as x plus y plus m. This is the addition of cosets. So infimum of x plus y plus m. So infimum of norm x plus y plus m1 plus m2. So this can be split again, norm x plus m1 plus x plus m2. Whenever we split the norm, if you divide the above set into two sets, then this equality becomes inequality less than or equals to infimum of norm x plus m1 plus infimum of norm y plus m2. This is nothing but norm x plus m plus norm y plus m. Hence, norm x plus m plus y plus m is less than or equals to norm x plus m plus norm y plus m. This is the second property of the normed linear space. We go for third one. Norm alpha into x plus m, right? Norm alpha into x plus m is equals to infimum of norm alpha into x plus m. This can be written as infimum of mod alpha into norm x plus m. We know the property mod or norm small a into alpha or small a into norm small a into x is equals to mod a into norm x, mod a into norm x. By using that condition, here it can be written as mod alpha into norm x plus m. Right now, mod alpha is a constant, so right outside the set mod alpha into infimum of norm x plus m. This is nothing but mod alpha into norm x plus m. Hence, this proves the third condition. Norm of alpha into x plus m is equals to mod alpha into norm x plus m. This shows us from the conditions 1, 2, 3. Here you observe that this is condition number 1, and this is condition number 2, and this is condition number 3. From conditions 1 to 3, we conclude that n by m is a normed linear space. This is the second part of the theorem. In the third part, we prove that n by m is a Banach space. This quotient space is a Banach space by assuming n is a Banach space. So assume that capital N is a Banach space. Banach space means a complete normed linear space. We prove that n by m is also a Banach space. For this, to prove this, we start with a Cauchy sequence. In the quotient group or in the quotient space n by m, and we have to show that it has a convergent sequence. We take a Cauchy sequence in n by m and we show that it has a convergent subsequence in n by m. We know that if a Cauchy sequence has a convergent subsequence, then obviously a Cauchy sequence has a convergent subsequence means that Cauchy sequence is always convergent. So, right. Now we find a sequence xn plus capital M of original Cauchy sequence such that we are going to define a Cauchy sequence xn plus m such that it satisfies the condition norm x1 plus m minus x2 plus m is less than 1 by 2. Observe this condition, norm x1 plus m minus x2 plus m is less than 1 by 2. Next one, norm x2 plus m minus x3 plus m is less than 1 by 2 square. Next one, norm x3 plus m minus x4 plus m is less than 1 by 2 power m. In general, norm xn plus m minus xn plus 1 plus m is less than 1 by 2 power n. Right. We prove that this sequence is convergent in n by m. Now we define a sequence with satisfying all these conditions. Now we show that this sequence is convergent in the quotient space n by m. So let us begin by choosing vectors y1, y2, y3 and so on according to x1 plus m and x2 plus m and so on. Choose y1 in x1 plus m and y2 in x2 plus m, satisfying the condition norm y1 minus y2 is less than 1 by 2. Choose y3 in x3 plus m. We are choosing, observe that, y1 in x1 plus m, y2 in x2 plus m, y3 in x3 plus m, satisfying the condition mod norm y2 minus y3 less than 1 by 2 square. By continuing this process, we get a sequence yn satisfying the condition norm yn minus yn plus 1 is less than 1 by 2 power n. So assume that m is less than n. And now norm ym minus yn is equals to. We add some terms and subtract the terms. ym minus ym plus 1 plus ym plus 1 minus ym plus 2 plus ym plus 2 and so on. So by splitting the terms which is less than or equals to, we know that norm x plus y is less than or equals to norm x plus norm y. So let us split the terms. Norm ym minus ym plus 1, norm ym plus 1 minus ym plus 2 plus norm ym plus 2 minus ym plus 3 and so on norm yn minus 1 minus yn. So already we give some properties. Norm y1 minus y2 is less than 1 by 2. Norm y2 minus y3 is less than 1 by 2 square. By giving that properties, by giving the same properties here, norm ym minus ym plus 1 is less than 1 by 2 power m. The second term, norm ym plus 1 minus ym plus 2 is less than ym 1 by 2 power m plus 1. And the third term gives 1 by 2 power m plus 2 and so on. Obviously, this series is a geometric progression. By applying the geometric progression convergent formula, 1 by 2 power m minus 1, a by 1 minus r, a by 1 minus r. So 1 by 2 power m minus 1. So obviously you get norm ym minus yn is less than or equals to 1 by 2 power m minus 1. From this inequality, we conclude that yn is a Cauchy sequence. Yn is a Cauchy sequence from this inequality. So norm ym minus yn is less than 1 by 2 power m minus 1. From this conclusion, we conclude that from this inequality, we conclude that yn is a Cauchy sequence. Yn is a Cauchy sequence in capital N. Yn is a Cauchy sequence in capital N and N is a Banach space. Every Banach space is complete. Complete means every Cauchy sequence in it is convergent. What is mean by complete? Every Cauchy sequence in it is convergent. Yn is a Cauchy sequence in N. Therefore, Yn converges to Y for some vector Y in N. So right, finally we show that xn plus m is converges to y plus m. So take this norm yn plus xn plus m, norm xn plus m minus y plus m is equals to, by subtraction of cosets, norm xn minus y plus m. So which is less than or equals to infimum of norm xn minus y plus m, which is less than or equals to norm xn minus y plus m. So by our definition, yn is equals to xn plus m, and since yn converges to y, so the sequence xn plus m is also converges to y. So applying the same here, norm xn plus m minus yn plus m converges to 0. It means xn plus m converges to yn plus m. It means every Cauchy sequence in xn plus m, in n by m is convergent. It means n by m is complete. It means n by m is a normal linear space and complete. It means n by m is Banach space. That is the definition of Banach space. Banach space is a complete normal linear space. So in this theorem, we prove all the three parts. In the introduction, we learn about the statement, and in the second part, we prove that n by m is a normal linear space, and in the third part, we prove that n by m is a Banach space by assuming n is a Banach space. In the next video, we learn another theorem. Keep learning. Hi, welcome to Sunil Maths tutorial, functional analysis, class number 6. In this video, we learn a theorem. Let us see the statement of the theorem. Capital N be a non-zero normed linear space, then capital N is a Banach space, implies and implied by set of all elements x such that norm x is equals to 1 is complete. So we prove this theorem. Let us see the introduction part. N not equals to pi, n is non-zero, n is not equals to pi, be a normed linear space. We notate the set as capital S. So S is equals to x such that norm x is equals to 1. You have to understand this set, capital S. This set means, suppose any element alpha belongs to S means norm alpha is equals to 1. It means capital S is the set of all elements whose norm is equivalent to 1. And clearly it is subset to capital N. By the definition of S, it is a subset of N. Now our aim is to show that capital N is a Banach space implies and implied by capital N is a Banach space implies and implied by capital S is complete. So we take N is a Banach space, we prove that S is complete. In the converse part, we assume that S is complete and we prove that N is a Banach space. So right, let us see. Suppose that capital N is a Banach space. We have to show that S is complete. We have to show that S is complete. What is mean by Banach space? So Banach space is a complete normed linear space. Banach space is a complete normed linear space. Our aim is to show that S is complete. What is mean by complete? Every Cauchy sequence in the set is convergent, then we say that it is complete. So we have to prove that S is complete now. To prove this, let us take a sequence. Let Xn be a Cauchy sequence. Let Xn be a Cauchy sequence in capital S. It is observable that since S is subset to N, implies as Xn is a Cauchy sequence. Xn is a Cauchy sequence in capital N, because Xn is Cauchy sequence in S and S is subset to N. So obviously this sequence Xn is a Cauchy sequence in capital N, and we know that this capital N is Banach space, and every Banach space is complete, implies N is complete. What is the definition of complete? N is complete means every Cauchy sequence in capital N is convergent. Every Cauchy sequence in capital N is convergent, implies the sequence Xn is convergent. The sequence Xn is convergent to a point X in capital N. Now we have to prove that X belongs to capital S, that X belongs to capital X. We know the fundamental fact, norm is always continuous function. Norm is always continuous function. We know that norm is continuous. Norm is a continuous function. By applying this condition, Xn converges to X implies as norm Xn converges to norm X. It means limit n tends to infinity, norm Xn tends to norm X. Limit n tends to infinity 1, because of, you observe that we get 1 means Xn is a Cauchy sequence in capital N. We define that this Xn is a Cauchy sequence, this Xn is a Cauchy sequence in capital S. Here we define that Xn is a Cauchy sequence in S, and by the definition of S consists those elements whose norm is equals to 1. Therefore we conclude that norm Xn is equals to 1. So limit n tends to infinity 1 tends to norm X. This condition implies as norm X is equals to 1. If norm X is equals to 1, obviously X belongs to capital S. Our aim is also same. We have to prove that X belongs to capital S. Already we show that Xn is a converges to X in capital N. Therefore, from this we conclude that the Cauchy sequence Xn in capital S is convergent to X in capital S. It means every Cauchy sequence in capital S is convergent to a element or is convergent to a limit. It means capital S is complete. Therefore, we conclude that capital S is complete. So we assume that N is a Banach space. We assume that N is a Banach space here. We assume that N is a Banach space, and we prove that S is complete. Now let us go for converse. In this converse part, we assume that S is complete. suppose capital S is complete. We have to prove that, or we prove that from this we prove that capital N is a Banach space. Capital N is a Banach space. Already by given data, this N is a normed linear space. Capital N is normed linear space. So N is already a normed linear space. Our aim is to show that it is a Banach space. So it is equivalent to prove that. It means we have to prove that Banach space. It is equivalent to prove that capital N is complete. Capital N is complete. To prove we prove this N is complete in two cases. The first one, case 1. We prove that N is complete in two cases. Case 1. Let us take Xn be a Cauchy sequence. Xn be a Cauchy sequence in capital N such that norm Xn is equals to 1. Remember this point. We define a Cauchy sequence. In capital N. Satisfying the condition norm Xn is equals to 1. By this definition, norm Xn is equals to 1. We conclude that the set or the sequence Xn belongs to S. The sequence Xn belongs to capital S. If the sequence Xn belongs to capital S and we have this S is complete. By the definition of complete, every Cauchy sequence in it is convergent. Therefore, the sequence Xn is convergent in capital S. And we take the one more element is convergent to X in capital S. It means limit n tends to infinity, Xn is equals to X in capital S and S is subset to capital N. It means the same thing holds in N also. The sequence Xn is convergent in capital N. Hence N is complete. In this case. Our aim is also same. You have to show that N is complete. I repeat this part. Observe that. We assume that S is complete. We have to prove that N is a Banach space. Our aim is to show that N is a Banach space. By already given data, capital N is a normed linear space. So it is equivalent to prove that N is complete. To prove N is complete, we use two different cases. One is norm Xn is equals to 1 and in the second case, norm Xn not equals to 1. So case 1, let us take Xn be a Cauchy sequence in capital N such that norm Xn is equals to 1. By the definition of capital S, this sequence Xn belongs to capital S because of norm Xn is equals to 1 means the element Xn belongs to capital S. So right, and S is complete. Complete means every Cauchy sequence in it is convergent. So Xn converges to X in capital S. So that is limit n tends to infinity Xn is equals to X in capital S. And we know that S is subset to capital N. Therefore Xn is convergent in, this is not S, Xn is convergent in capital N. Therefore N is complete. Now we go for case 2. We define the same. Let Xn be a Cauchy sequence in capital N. Let Xn be a Cauchy sequence. In capital N. Such that norm Xn not equals to 1. In the previous case, we define norm Xn is equals to 1. Here in this case, we define norm Xn not equals to 1. That is the difference between the That is the difference between case 1 and case 2. Right. Now define one more sequence. Now define yn is equals to xn by norm xn implies as norm yn is equals to norm of xn by norm xn. This is nothing but norm xn by norm xn. Again the numerator and denominator are same, you get 1. What it means? Norm yn is equals to 1. If norm yn is equals to 1, by the definition of S is the set of all elements x such that norm x is equals to 1. So this shows us that yn belongs to S. It means the sequence yn is clearly defined over S. Clearly defined over S. First we show that this yn is a Cauchy sequence. First we show that this sequence yn is a Cauchy sequence. This sequence yn is a Cauchy sequence in capital S. To prove this, consider one norm ym minus yn is equals to, by definition of ym, xm divided by norm xm minus xn divided by norm xn. Right? We calculate norm xm divided by norm xm minus I'm adding one term minus xn by norm xm plus same term I write plus xn by norm xm minus the last term xn by norm xn. So which is equals to, or which is less than or equals to, by splitting the norm xm minus xn divided by norm xm, because here the denominator is same. For these two terms the denominator is same, plus norm xn minus norm xm minus xn by norm xn. So let us simplify this. Norm xm minus xn divided by norm xm plus, here you observe that here is a xn, here is also xn. So by making norm xn common, and by taking LCM, norm xm norm xn into, you can write in the numerator as norm xn minus norm xm. That's it. And again you can write like this, norm xm minus xn divided by norm xm plus norm xn into norm. The norm is non-negative function, so you can write norm of xm minus xn, because it is a non-negative function, divided by norm xm into norm xm. Here observe that we remove this norm, that's why we get less than or equals to. Here also again you get this norm xn, norm xn get cancelled, norm xn and norm xn get cancelled, and we have simply less than or equals to norm xm minus xn divided by norm xm plus norm xm minus xn divided by norm xm. Both are same terms. So you can write like this, which is less than or equals to 2 into norm xm minus xn divided by norm xm. Therefore final conclusion, norm ym minus yn is less than or equals to 2 into norm xm minus xn divided by norm xm. Let it be equation number 1. So right, now already we have, since this xn is a Cauchy sequence, this xn is a Cauchy sequence. By the definition of Cauchy sequence implies as for each epsilon greater than 0, there exists a positive integer. By the definition of Cauchy sequence, there exists a positive integer n naught such that norm xm minus xn is less than epsilon by 2. Actually, this is the definition of Cauchy sequence. We can write additionally one more term, norm xm. There is nothing wrong in that one. You can define this RHS as your wish. So let it be equation number 2. Let it be equation number 2. Now using equation 2 in equation 1. Using equation 2 in equation 1, we get norm ym minus yn is less than or equals to 2 into epsilon by 2 norm xm divided by norm xm. So you observe that here 2 get cancelled, norm x get cancelled. This is less than or equals to epsilon only. Less than or equals to epsilon only. Therefore, you simply write less than, not less than or equals to less than. Therefore, we conclude that norm ym minus yn is less than epsilon. Therefore, we write like this. For given epsilon greater than 0, there exists a positive integer, small n naught such that norm ym minus yn is less than epsilon for all n comma m greater than or equals to n naught. This shows us, this condition or this definition shows us the sequence yn is a Cauchy sequence. The sequence yn is a Cauchy sequence in capital S. The sequence yn is a Cauchy sequence in capital S. Our aim is also same. You observe that. First we show that yn is a Cauchy sequence in capital S. So by following this derivation part, we show that yn is a Cauchy sequence in capital S. And what is the nature of capital S? Since capital S is complete. What it means? Every Cauchy sequence in it is convergent. Therefore, the sequence yn is convergent to y in capital S. In capital S. Remember this point. Now we go for one more. What is the definition of yn? Since yn is equals to xn by norm xn. From this calculation, you observe that xn is equals to yn into norm xn. Hence, here the sequence xn, the sequence norm xn is a Cauchy sequence, because norm is equal to 1. Is a Cauchy sequence in the set of real numbers and capital R is complete. If capital R is complete, this norm xn or this sequence norm xn converges to a number alpha. Say this is just our assumption, because every Cauchy sequence in capital R is convergent. So converges to alpha in capital R. In the set of real numbers. So it means that norm xn converges to alpha means norm xn into yn converges to alpha into y, because yn converges to y. This condition shows us y xn, the sequence xn converges to alpha y. The sequence xn converges to alpha y. Where that alpha belongs to capital R and that y belongs to capital S. So again this S is subspace of capital N. This shows us the sequence xn is convergent in capital S. In capital N. The sequence is convergent in capital N. So this shows us every Cauchy sequence in capital N, every Cauchy sequence in capital N is convergent. Therefore, capital N is complete. Therefore, capital N is complete. Therefore, capital N is a Banach space. Capital N is a Banach space. This completes the proof of our theorem. Hence, we conclude that capital N is a Banach space. Capital N is a Banach space implies and implied by the set S is equals to the set of all elements X such that norm X is equals to 1 is complete. Is complete. Hence proved. This completes the proof of our theorem. Right, in the next video we'll learn some additional one more theorem. So I think you understand this theorem. Keep learning. Wish you all the best. Hi, welcome to Sunil Maths tutorial. Functional analysis class number 7. In this video we prove a statement. Let us take a Banach space capital B, which is the direct sum of linear subspaces capital M and N, that is B is equals to M direct sum N, and if Z is equals to X plus Y is the unique expression of a vector Z in capital B as the sum of vectors X and Y, where X belongs to capital M and Y belongs to capital N. And we define a new norm, that is in the linear space B by norm Z dash is equals to norm X plus norm Y. We have to prove that this is actually a norm, and B dash symbolizes the linear space B equipped with this new norm. We have to prove that B dash is a Banach space if M and N are closed in capital B. So right, first we analyze the statement. Let us see. They given that capital B is a Banach space. Capital B is a Banach space, and B is direct sum of M and N. Capital B is the direct sum of M and N. It means M and N are linear subspaces of capital M. Linear M and N are linear subspaces of B, and also that B can be expressible as direct sum of M and N. It means every vector belongs to B can be written as sum of two vectors. Every element in B can be written as sum of two vectors X plus Iy. I mean, it is unique expression again. One is from M and the second one is from N. Every element alpha belongs to capital B can be uniquely written as alpha is equals to beta plus gamma, where that beta belongs to capital M and gamma belongs to capital N, and this expression is unique. So right, now we define a new norm. Norm Z dash is equals to norm X plus norm Y. First we show that this new norm is actually a norm. It means it satisfies all the three properties of norm. And then we prove that B dash, here B dash is nothing but capital B together with new norm. B dash is nothing but capital B together with new norm is a Banach space by assuming M and N are closed in capital B. So right, first we show that it is a new norm. Here norm Z dash is equals to norm X plus norm Y. Suppose let us take X not equals to 0 and Y not equals to 0. If X not equals to 0, then norm X is greater than 0. Norm Y is also greater than 0. Since X not equals to 0, Y not equals to 0 implies X plus Y not equals to 0. Therefore, X plus Y not equals to 0 implies as norm X plus norm Y is greater than 0. Norm x plus norm y is greater than 0 means norm z dash is greater than 0. Norm z dash is greater than 0. Further, further, if z dash is equals to 0, norm z dash is equals to 0, it means norm x is equals to 0, norm x is equals to 0, and norm y is equals to 0. Norm x is equals to 0 means x is equals to 0, and norm y is equals to 0 means y is equals to 0. If both x and y are 0, then x plus y is also equivalent to 0. Therefore, this condition implies and implied by also holds. Therefore, norm z dash is always greater than 0 and norm z dash is equals to 0 implies and implied by x plus y is equals to 0. X plus y is equals to 0. This is the first property of norm. This is the first property of norm. Yes, the new norm satisfies the first condition. Now we prove the second property of norm. We prove the second property of norm. For this, let us take two elements. Let z is equals to x plus y, comma s is equals to p plus q, where the x comma p belongs to capital M and y comma q belongs to capital N. Capital N. Now z plus s is equals to x plus y plus p plus q. Rearrange the terms x plus p plus y plus q. Y plus q. Now take the norm. Norm z plus s whole dash is equals to norm of x plus p plus y plus q, which is less than or equals to norm x plus p dash plus norm y plus q, norm y plus q, no need to write dash, so which is again less than or equals to, norm x plus norm p plus norm y plus norm q. Again rearrange the terms, you can write norm x and norm y, so less than or equals to norm x plus norm y, this is the first term, plus you write the second term norm p plus norm q, this is second term, which is clearly less than or equals to norm z dash plus norm s dash. This is the second condition, or this is the second property of the norm. Therefore, norm z plus s whole dash less than or equals to norm z dash plus norm s dash, which is the second property of the norm. Already we proved the first property. Now we prove the second property of the norm. We go for third property now. Let us take z is equals to x plus iy, where x belongs to capital M and y belongs to capital N, and take an element alpha belongs to the field capital F, and alpha z is equals to alpha into x plus y. Now norm alpha z dash is equals to norm alpha into x plus y, norm alpha into x plus y. Again it can be written as mod alpha into norm x plus y, which is less than or equals to mod alpha into norm x plus norm y. So this is norm x plus norm y is nothing but mod alpha into norm z dash. Therefore we prove that norm alpha z dash is less than or equals to mod alpha into norm z dash. There is a small mistake I did. This is not less than or equals to. It is clearly equivalent to. Here also it is clearly equivalent to. Remember that. Sorry for that. It is clearly equivalent to. This is the third condition of the norm. From these three conditions, from these equations 1, 2 and 3, we conclude that the new norm norm z dash is equals to norm x plus norm y is well defined or actual norm. actual norm. It is well defined. No worries. Now we assume that capital M and N are we assume that capital M and N are closed subspaces closed subspaces of the Banach space, closed subspaces of the Banach space capital B, Banach space capital B. By data they given that capital B is equals to direct sum of M and N, direct sum of M and N. Now we have to prove that B dash with respect to new norm, with respect to new norm is a Banach space. New norm is a Banach space. So right, Banach space means already B dash is a normal linear space. So it is equivalent to show that complete. So our aim is to show that. B dash is complete. So if you show that B dash is complete, then obviously B dash becomes a Banach space. So for this, let us define a Cauchy sequence. Let Zn be a Cauchy sequence. Let Zn be a Cauchy sequence in B dash. Let Zn be a Cauchy sequence in B dash. Now write the definition of Cauchy sequence. For each epsilon greater than 0, there exists a positive integer. I'm writing the definition of Cauchy sequence. For each epsilon greater than 0, there exists a positive integer n0 such that norm Zm minus Zn dash is less than epsilon for all m comma n greater than or equals to n0. Let it be equation number 1. So right here the terms Zm comma Zn both belongs to B dash, and this B dash is equals to m direct sum n. So this Zm can be written as xm plus ym, and Zn can be written as xn plus yn, where xm comma xn belongs to capital M, ym comma yn belongs to capital N. Now from equation 1, you see this is equation number 1. Here from equation 1, norm Zm means xm plus ym minus Zn xn plus yn whole dash is less than epsilon. Rearrange the terms. Norm xm minus xn plus ym minus yn is less than epsilon. So this condition implies norm xm minus xn is less than epsilon, norm ym minus yn is less than epsilon. Here the sum of the terms is less than epsilon. So individually both the terms are also less than epsilon. Here you observe that. This is one term and this is another term. If you add both the terms, that is less than epsilon. So obviously both the terms individually they are less than epsilon. This inequality shows us xn is a Cauchy sequence. And this condition shows us yn is a Cauchy sequence. Xn is a Cauchy sequence and yn is a Cauchy sequences. So here you observe that both xn and yn are Cauchy sequences. Therefore, both xn and yn are Cauchy sequences in capital M and N respectively. And we know that capital M and N are closed subspaces of a Banach space, capital B, which implies capital M and N are complete. Capital N, M and N are complete. Remember this point. Remember this point. M and N are closed subspaces of a Banach space capital B. That's why M and N are complete. M and N are complete, and X and Yn are Cauchy sequences in M and N respectively. So the sequence xn converges to x and the sequence yn converges to y. The sequence xn converges to x and the sequence yn converges to y in m and n respectively. Right. By the definition of convergence, norm xn minus x is less than epsilon by 2 for all n greater than or equals to n1, where n1 is a positive integer. According to the same theory from this one, yn converges to y, you can write norm yn minus y is less than epsilon by 2 for all n greater than or equals to n2. So right, now define n is equals to maximum of n1 comma n2 we have, or it is equals to n3, say n3, we have norm xn minus x is less than epsilon by 2, norm yn minus y is less than epsilon by 2 for all n greater than or equals to n3. So now I am going to write norm zn minus z. Norm zn minus z. Norm zn, by the definition of zn can be written as xn plus yn minus z can be written as x plus y. Rearrange the terms. Norm xn minus x plus yn minus y. Split the norm less than or equals to norm xn minus x plus norm yn minus y, which is equivalent to epsilon by 2 plus epsilon by 2, which is equals to epsilon. This condition shows us norm zn minus z is less than epsilon for all n greater than or equals to n3, where n3 is a positive integer. That is, the sequence zn converges to z in b dash. The sequence zn converges to z in b dash. That is, every Cauchy sequence in b dash is convergent. Therefore, we conclude that b dash is complete. Whenever b dash is complete, already it is a normed linear space. Therefore, b dash is a Banach space. B dash is a Banach space with respect to new norm. Norm z dash is equals to norm x plus norm y. Hence proved. This completes the proof of our statement. Hence proved. That's it. Wish you all the best. Keep learning. Hi, welcome to Sunil Maths tutorial, functional analysis, class number 8. So in this video, we learn some definitions and one theorem. Let us see the definition. Continuous linear transformation. Let capital N and N dash be two normed linear spaces. And capital T maps N into N dash be a linear transformation. Then this linear transformation capital T is said to be continuous. The linear transformation capital T is said to be continuous if it satisfies one condition. Xn converges to x in capital N implies Xn converges to x in capital N implies T of Xn converges to T of x in n dash. In n dash. I repeat the definition. Observe that continuous linear transformation. Capital N and n dash be two normed linear spaces. T maps n into n dash be a linear transformation. Then this linear transformation T is said to be continuous linear transformation if it satisfies one condition. When xn converges to x in capital N implies as T of xn converges to T of x in n dash. It means whenever the elements converges in the domain, then the corresponding images are also converges in the codomain. Here n is the domain and n dash is the codomain. Whenever the elements in the domain xn converges to x, then the corresponding images also converges to their corresponding images. So right, remember this condition which is important for us. So whenever xn converges to x, whenever xn converges to x in capital N implies T of xn converges to T of x in n dash. In n dash. So right, we go for next definition, bounded linear transformation. Same theory. You see, let us take capital N and n dash be two normed linear spaces, and capital T maps capital N into n dash be a linear transformation, then this T is called bounded. If there exists a real number, k greater than or equals to 0, such that norm T of x is always less than or equals to k into norm x for all x belongs to capital N. Then we say that T is bounded. Here capital K is called bound. For T. And the T is called bounded linear transformation. I repeat the definition, please observe that. So a linear transformation capital T which maps from one normed linear space to another normed linear space n into n dash is called a bounded set, or is called a bounded linear transformation, not set, bounded linear transformation. If there exists a real number k greater than or equals to 0, satisfying the condition norm T of x less than or equals to k into norm x for all x belongs to capital N. Here the real number k is called bound. Bound for T, and T is called bounded linear transformation. So right, remember these two definitions. One is continuous and the second one is bounded. Now we prove one very important theorem. In the functional analysis according to these linear transformations. Let capital N and n dash be two normed linear spaces, and T maps n into n dash be a linear transformation. Then the following four conditions are equivalent to one another. T is continuous, and T is continuous at origin in the sense that xn converges to 0 implies T of xn converges to 0. There exists a real number k greater than or equals to 0 such that norm T of x is less than or equals to k into norm x, which is nothing but this third condition is nothing but bounded condition. One. And the last one, fourth one, if S is equals to set of all elements x such that norm x less than or equals to 1, norm x less than or equals to 1 is a closed unit sphere in capital N, then its image, the image of S, T of S, is a bounded set in N dash. Is a bounded set in N dash. So observe the four conditions. These conditions are equivalent to one another. So these conditions are equivalent to one another. So we prove this theorem in the sense, we prove this theorem like this. Condition 1 implies condition 2 and condition 2 implies condition 1. It means condition 1 implies and implied by 2. Condition 1 implies and implied by 2. And then we prove 2 implies 3. And then we prove 3 implies 2. It means condition 2 implies and implied by 3. And finally we prove that 3 implies 4. Condition 3 implies 4. And condition 4 implies 3. It means 3 implies and implied by 4. These three, now according to these, all these three, we conclude that all the four conditions are equivalent to one another. All the four conditions are equivalent to one another. Let us start our proof. So 1 implies 2. 1 implies 2. Let us take capital T is continuous. Let us take capital T is continuous. Now we write the definition of continuous one. Xn converges to x implies as T of xn converges to T of x. In particular, replace that x by 0. It means xn converges to 0, which implies T of xn converges to T of 0. Here what is T? Capital T is a linear transformation. One of the property of linear transformation, T of 0 is equals to 0. T of 0 is equals to 0. This condition implies as T of xn converges to 0. T of xn converges to 0. It means what we show that xn converges to 0 implies as T of xn converges to 0. This shows us capital T is continuous. Capital T is continuous at origin. Capital T is continuous at origin. So this proves 1 implies 2. Now the next one is 2 implies 3. Sorry, 2 implies 1. We prove that 2 implies 1. So assume that. Let us take T is continuous at origin. Let capital T is continuous at origin. Let capital T is continuous at origin. What it means? Xn, that is xn converges to 0 implies T of xn converges to 0. T of xn converges to 0. Now we prove that. Suppose xn converges to x. If xn converges to x, then xn minus x converges to 0. Xn minus x converges to 0. What it means? T of xn minus x converges to T of 0. Now we use two properties of linear transformation. Capital T is a linear transformation, which implies as T of alpha minus beta is equals to T of alpha minus T of beta. By applying that condition, here it becomes T of xn minus T of x tends to, here it is T of 0. T of 0 is equals to 0. This one. So which implies as, this condition again implies as T of xn converges to T of x. Converges to T of x. What it means? We take that xn converges to x. We prove that T of xn converges to T of x. This condition shows us capital T is continuous. Capital T is continuous. Hence, this condition implies as 2 implies 1. 2 implies 1. Now you observe that in the first case we prove that 1 implies 2, and in the second case we prove that 2 implies 1. Therefore, finally we conclude that 1 implies and implied by 2. 1 implies and implied by 2. Now we are going to prove. Now we are going to prove 2 implies 3. 2 implies 3. For this, let us take or let us assume, anyone, let us take or let us assume T is continuous at origin. T is continuous at origin. If T is continuous at origin, it means the term xn or the sequence xn converges to 0 implies as T of xn converges to also 0. T of xn converges to 0. We have to prove that norm T of x, we have to prove that norm T of x is less than or equals to k into norm x. K into norm x. This is our aim to show that. So assume the contradiction point. Assume the contradiction point. Suppose that there exists a real number k greater than or equals to 0 such that norm T of x is greater than k into norm x. Actually, we have to show that the converse part for all x belongs to capital N. But we assume the contradiction point. From this condition, from this inequality, you observe that there exists a positive integer. There exists a positive integer small n such that norm T of xn is greater than n into norm xn. So what it means? Norm T of xn divided by n into norm xn is greater than 1. N into norm xn is greater than 1. Applying the norm properties, you can write like this. Norm of T of xn by n into norm xn is greater than 1. So define another sequence yn is equals to xn divided by n into norm xn. By applying this inequality here, you get norm T of yn is greater than 1. Now you observe the limit n tends to infinity, yn is equals to limit n tends to infinity xn by n into norm xn. Everybody knows that 1 by n tends to 0 as n tends to infinity. So by applying that condition, this limit becomes 0. It means limit n tends to infinity yn is equals to 0. Limit n tends to infinity yn is equals to 0. It means the sequence, there exists a sequence yn that belongs to capital N such that norm T of yn is greater than 1. Norm T of yn is greater than 1. What it means? The sequence yn converges to 0, but T of yn does not converges to 0. You see, limit yn is 0. It means yn converges to 0. But T of yn, norm T of yn greater than 1 means T of yn does not converges to 0. This is a contradiction. Because already we know that whenever xn tends to 0 implies T of xn also tends to 0 because T is continuous at origin. This is a contradiction to the fact that T is continuous. That is this one. So our assumption is wrong. What is our assumption? This one. Suppose that there exists a constant k greater than or equals to 0 such that norm t of x greater than k into norm x. This is wrong. So what is right now? Therefore, there exists a real number k greater than or equals to 0 such that norm t of x is less than or equals to k into norm x for all x belongs to capital N. This condition shows us capital T is bounded. Capital T is bounded. Hence, this proves that condition 2 implies 3. Condition 2 implies 3. Now we prove that, next we have to prove that 3 implies 2. Next we have to prove that 3 implies 2. To prove that 3 implies 2, assume that there exists a real number k greater than or equals to 0 such that norm t of x is less than or equals to k into norm x for all x belongs to capital 1. Let it be equation number 1 or equation number A, some inequality equation A. Now let us take xn be a sequence in the Norwood linear space capital N which converges to 0. It means xn tends to 0 as n tends to infinity in capital N. It means norm xn tends to 0. Now from equation number A, norm xn tends to 0 means norm of t of xn is less than or equals to k into norm xn. Because of norm xn tends to 0 implies t of xn, norm t of xn also tends to 0. This shows us capital T is continuous at origin. This proves condition number 2. Therefore, 3 implies 2 is proved. Hence, already we proved that 2 implies 3. Here we prove that 3 implies 2. Therefore, we conclude that 2 implies and implied by 3. Now we are going to prove 3 implies 4. So again, suppose that, assume condition number 3. Suppose that there exists a real number k greater than or equals to 0 such that norm t of x is less than or equals to k into norm x for all x belongs to capital N. This is condition number 3. You have to prove that the set S is bounded. So by data that S is defined like this: set of all elements x such that norm x is less than or equals to 1. Then now write the image T of S. T of S is equals to the set of all images T of x such that x belongs to S. T of x, you can use norm T of x such that x belongs to S means norm x is less than 1. Norm T of x, here you observe that norm T of x is less than or equals to k into norm x. So k into norm x such that norm T of x is less than or equals to k. This shows us this set is completely less than or equals to k. Hence we show that T of S is less than or equals to k. Therefore we conclude T of S is bounded set. In n dash. So right, this condition proves us 3 implies 4. This condition implies us 3 implies 4. So we assume that capital T is bounded, we prove that T of S is bounded. So next we are going to prove 4 implies 3. We have to show that 4 implies 3. To prove this, we define certain things by data. By data, they given that S is equals to X such that norm X less than or equals to 1 is a closed sphere. Is a closed sphere in capital N. Is a closed sphere in capital N. And T of S is a bounded set. T of S is a bounded set in N dash. Remember that. S is closed sphere in N and T of S is bounded set in N dash. Now we have to prove that. Norm T of X less than or equals to K into norm X. K into norm X. So right, to prove this, we use two different conditions. If X is equals to 0, then there is nothing to prove because norm X also equivalent to 0. T of 0, norm T of 0 is also equivalent to 0. So obviously the condition holds, norm T of X is less than or equals to K into norm X. Whenever X is equals to 0, the condition is trivially true. If X equals to 0, then there is nothing to prove. This condition is trivially true. So right, we define X not equals to 0. If X not equals to 0. Now to prove our inequality, we define a set. We define an element. Y is equals to X by norm X. Now you apply that. Norm Y is equals to norm X by norm X. This can be written as norm X by norm X. This can be written as 1. It means norm Y is equals to 1. If norm Y is equals to 1, by applying the definition of S, what is S? S is the set of all elements whose norm is less than or equals to 1. Here norm Y is equals to 1 implies as Y belongs to S. If Y belongs to S, then obviously T of Y belongs to T of S. T of Y belongs to T of S. T of Y belongs to T of S and T of S is bounded. If T of S is bounded, from this you can conclude that T of Y is less than or equals to K. If T of Y is less than or equals to K, what is Y? T of X by norm X is less than or equals to K. This can be written as 1 by norm X into T of X. I mean you can write it as norm T of X. According to here, if T of Y is less than or equals to K, implies as norm T of Y is less than or equals to K also. So here also you can use norm. So you can 1 by norm X into norm T of X is less than or equals to K. Now shift this term to this side, you simply get norm T of X is less than or equals to K into norm X. This is true for all X belongs to capital N. Hence we conclude that T is bounded. This proves condition number 4 implies 3. Hence we prove that 3 implies and implied by 4. Now you see carefully, here 3 implies and implied by 4 and 3 implies and implied by 4. Here we show that from this here 2 implies and implied by 3, and here we show that 1 implies and implied by 2. From all these three conditions, we conclude that all these four properties are equivalent to one another. Are equivalent to one another. T is continuous implies and implied by. T is continuous at origin implies and implied by. T is bounded implies and implied by. The images of a closed sphere, unit spheres, are also bounded in n dash. These four conditions are equivalent to one another whenever the T is a linear transformation. In the next video, we learn one more theorem. Wish you all the best. Keep learning. Hi, welcome to Sunil Maths tutorial, functional analysis, class number 9. In this video, we learn one definition and one theorem. Let us see the definition. Norm of a bounded linear transformation. Norm of a bounded linear transformation. Let us take capital N and N dash be two normed linear spaces, and capital T maps n into n dash be a bounded linear transformation. Bounded linear transformation means norm T of x less than or equals to k for some positive integer k greater than 0 and for all x belongs to capital N. So bounded linear transformation means norm T of x is always less than or equals to k. So right, now we define the norm of T as follows. Norm T is equals to supremum of norm T of x such that x belongs to capital N and norm x less than or equals to 1. This norm is known as operator norm. This norm is known as operator norm. One of the important definition, you observe that in the next theorem we learn the different forms of this norm. I repeat the definition, observe that capital N and N dash be any two normed linear spaces. Capital T maps N into N dash be a bounded linear transformation. The norm of T is defined as norm T is equals to supremum of norm T of x, where x belongs to the capital N and norm x less than or equals to 1. This norm is known as operator norm. Now let us see the theorem. The statement of the theorem is like this. Capital N and N dash be two normed linear spaces and capital T be a bounded linear transformation from N into N dash, and define three different terms. Small a is equals to supremum of norm T of x, where norm x is equals to 1. B is equals to supremum of norm T of x by norm x, where x belongs to N and x not equals to 0. And C is equals to infimum of set of elements k, where k greater than or equals to 0. And you observe that this is important. Norm T of x is less than or equals to k into norm x for all x belongs to capital N. Now you have to prove that norm T is equals to norm A. Norm T is equals to A is equals to B is equals to C. Further, you have to show that one inequality norm T of x less than or equals to norm T norm x for all x belongs to capital N. So right, we prove the theorem now. Let us see. Let capital N and N dash be two normed linear spaces. Capital T maps N into N dash be a bounded linear transformation. The norm of this linear transformation, the norm of T is defined as as follows. Norm T is equals to supremum of norm T of x such that x belongs to capital N, norm x is equals to 1. This is the definition of norm T. Now, in the statement we have three different definitions. One is A and the second one is B and the definition C. What is the definition of C? Let us see. By definition of C we have, the C is given by infimum of K such that K greater than or equals to 0, comma, norm T of X less than or equals to K into norm X for all X belongs to capital N. This condition shows us, the definition of C shows us norm T of X is less than or equals to C into norm X. C into norm X. Because C is infimum. Then obviously C is infimum of this whole set. It means C is always greater than or equals to K. Therefore, norm T of X is less than or equals to C into norm X for all X belongs to capital N. Now we assume that if norm X is equals to 1, what happens if norm X is equals to 1? If norm X is equals to 1, then obviously we have norm T of X is less than or equals to C. Norm T of X is less than or equals to C for all X belongs to capital N. So, right, norm T of X less than or equals to C means supremum of norm T of X such that X belongs to capital N, comma, norm X is equals to 1 is also less than or equals to C. Because norm T of X is less than or equals to C, then its supremum is also less than or equals to C. So, right, which implies us, this condition implies us norm T is less than or equals to C. Let it be equation number 1. Norm T is nothing but this set. This set is nothing but norm T. So, right. So, norm T is less than or equal to C from this above set. So, equation 1. Right. By definition of B and C. By definition of small b and C, it is clear that C less than or equals to B. Let it be equation number 2. Obviously, from the definition of C is infimum. But and B is supremum. C is infimum and B is supremum. So obviously C less than or equals to B. Now, we go for further calculation. Suppose if X not equals to 0. If X not equals to 0, then what happens? Norm T of X divided by norm X is equals to norm T of X by norm X. And you observe that X by norm X has norm 1. Thus we conclude that from this equality we conclude that from or by using definitions of B and C, B less than or equals to C. Sorry, not C, B less than or equals to A. From the definitions of B and A, we conclude that B is less than or equals to A. Let it be equation number 3. Now you observe that first equation, norm T less than or equals to C. Second equation, C less than or equals to B. Third equation, B less than or equals to A. So, right, we go for one more calculation. But trivially, by definition of A, trivially, small a is less than or equals to norm T. Because what is small a? Small a is equals to supremum. If you remove the word supremum, then obviously a is less than or equals to norm T. Let it be equation number 4. Combining equations 1, 2, 3, 4, we get norm T is less than or equals to C, is less than or equals to B, is less than or equals to A, is less than or equals to norm t. Now you observe that the funny thing, the lower limit is norm t, the upper limit is also norm t. Hence, we conclude that from this one, norm t is equals to A is equals to B is equals to C. Further, this is the first condition. We show one inequality. Further, by definition of B, what is norm T of x, divided by norm x is less than or equals to B, and this B is equals to norm T. By using this condition. So this condition implies as norm T of x divided by norm x is less than or equals to norm T. By cross multiplication, you have norm T of x is less than or equals to norm T into norm x. This is true for all x belongs to capital N. You observe that we prove the required two things. This is first one, norm T is equals to A is equals to B is equals to C, and norm T of x is less than or equals to norm T into norm x. So you observe this, from this theorem you must learn one thing: the norm of the bounded linear transformation, defined in this way: norm t is equals to supremum of set of norm t of x such that x belongs to capital N and norm x less than or equals to 1 is called an operator form, and it has different forms. This norm has different forms. All these one. A, it can be represented in A form, it can be represented like B, it can be represented like C. That's why we prove that here the condition. Finally we prove that in the theorem norm T is equals to A is equals to B is equals to C. It means the norm of the bounded linear transformation has three different forms. One is A, the second one is B, and third one is C. So in the next video we'll learn one more theorem. Wish you all the best. Keep learning. Hi, welcome to Sunil Maths tutorial, functional analysis, class number 10. In this video, we prove a theorem. Let us see the statement. If capital N and N dash are normed linear spaces, then the set script B of N comma N dash, of all continuous linear transformations of capital N into N dash is itself a normed linear space with respect to addition and scalar multiplication of linear transformations. And the norm is defined by norm T is equals to supremum of norm T of x such that norm x is less than or equals to 1. In the previous theorem, we learned this norm as a operator norm and we prove the different forms of this operator norm. Further, if n dash is a Banach space, then script B of n comma n dash is also a Banach space. One of the lengthiest theorem, observe that. They given that n and n dash are normed linear spaces, and there is a symbol script B of n comma n dash. Script B of n comma n dash is the set of all linear transformations from capital N into n dash. Remember that. This is important point. Script B of n comma n dash is the set of all linear transformations defined from capital N into n dash. So here these all continuous linear transformations. In the statement we have all the linear transformations which are continuous. Is the set of all linear transform is the set of all continuous linear transformations. We add one more property. Please remember, script b of n comma n dash is the set of all continuous linear transformations from n into n dash. So further, we know that there is a standard result in the linear spaces. In the linear spaces, the set of all continuous linear transformations, the set of all continuous linear transformations forms a linear space, with respect to addition and scalar multiplication, of linear transformations. This is a previous, one of the important results in linear spaces. The set of all continuous linear transformations forms a linear space. They forms a linear space with respect to addition and scalar multiplication of linear transformations. So it means here you observe that script b of n comma n dash is the set of all continuous linear transformations. So from this point we conclude that therefore script b of n comma n dash is a linear space. We have to prove that. This script b of n comma n dash is normed linear space. Script b of n comma n dash is normed linear space. So first part is to show that script b of n comma n dash is a normed linear space. So further, by data the norm is given by norm t or norm t of x is equals to supremum of norm t of x such that norm x less than or equals to 1. By using this definition of norm, we show that script b of n comma n dash is a normed linear space. So right. Here, the norm of every element is less than or equals to 1 and norm t is defined as supremum. It is obviously norm t greater than or equals to 0 because it is the supremum of all positive numbers. Norm t greater than or equals to 0. Further, norm t is equals to 0 implies and implied by supremum of norm t of x such that norm x less than or equals to 1 is equals to 0. So which is implies and implied by norm t of x is equals to 0. Norm t of x is equals to 0. Norm t of x is equals to 0 for all x belongs to capital N, which is implies and implied by t of x is equals to 0. Which is implies and implied by t is 0. It means which is nothing but zero transformation. Therefore, from this calculation, we conclude that therefore norm t greater than or equals to 0 and norm t is equals to 0 implies and implied by t is equals to 0. This is the first property of normed linear space. Now, to prove the second property of normed linear space, let us take two elements t comma s belongs to script b of n comma n dash. It means capital T maps capital N into N dash, capital S maps capital N into N dash. Both are continuous linear transformations. Both are continuous linear transformations. Now, by definition of norm, by definition of norm, norm t plus s is equals to supremum of norm t plus s of x. I am using the definition of norm t plus s of x such that norm x less than or equals to 1. This is equals to supremum of norm t of x plus s of x such that norm x less than or equals to 1. Norm x less than or equals to 1. Split the norm. Split the norm, which is less than or equals to supremum of norm t of x plus norm s of x such that norm x less than or equals to 1. Again split the set. Split this set. Supremum of norm t of x such that norm x less than or equals to 1, norm x less than or equals to 1 plus supremum of norm s of x such that norm x less than or equals to 1. Here this first set is nothing but norm t of x, and the second set is nothing but norm s of x. This is the second property of normed linear space. This is the second property of normed linear space. Therefore, in the LHS we have norm t plus s. In the right side we have norm t plus norm s. Therefore, norm t plus s less than or equals to norm t plus norm s. This is second property of normed linear space. To prove the third property, let us take a scalar. Let us take a scalar. Alpha belongs to capital R, be a scalar, and t is a element from script b of n comma n dash. Now norm alpha t is equals to, I am applying the definition of supremum. Norm alpha t is equals to supremum of norm alpha t of x, norm alpha t of x such that norm x less than or equals to 1. It is very simple and very easy. Supremum of mod alpha norm t of x such that norm x less than or equals to 1, which is equals to mod alpha into supremum of norm t of x such that norm x less than or equals to 1. This is nothing but mod alpha into norm t. This is nothing but third property. Norm alpha t is equals to mod alpha into norm t. This is nothing but third property of the normed linear space. Now let us see. This is the first condition. Norm t greater than or equals to 0, and norm t is equals to 0 implies and implied by t is equals to 0. First property of linear space. Norm t plus s less than or equals to norm t plus norm s, which is second property of normed linear space. Norm alpha t is equals to mod alpha into norm t, which is the third property of normed linear space. From all these three properties, we conclude that script b of n comma n dash is a normed linear space. Is a normed linear space. Further, the second part of the theorem. Next, the second part of the theorem. Assume that n dash is a Banach space. Assume that n dash is a Banach space. Assume that n dash is a Banach space. We have to prove that, by using this fact, we have to prove that script b of n comma n dash is also a Banach space. Is also a Banach space. Already script b of n comma n dash is a normed linear space. So it is equivalent to show that it is sufficient or equivalent to show that script b of n comma n dash is Banach space. We prove that it is complete. It is complete. It means already it is a normed linear space. If we show that it is complete, then obviously it becomes a complete normed linear space becomes a Banach space. I repeat this point, please understand. We have to prove that B of n comma n dash is a Banach space. Already we prove that it is a normed linear space. Already we prove that it is a normed linear space. So it is equivalent to prove that it is a Banach space means you have to prove that it is a complete. A complete normed linear space is again a Banach space. So right, to prove this it is a Banach space. To prove this it is a Banach space. Define a Cauchy sequence. Let us take sequence Tn be a Cauchy sequence. Sequence Tn be a Cauchy sequence in script b of n comma n dash. By the definition of Cauchy sequence, for each epsilon greater than 0, there exists a positive integer n naught. Such that norm Tm minus Tn less than epsilon for all n comma m greater than or equals to n naught. For all n comma m greater than or equals to n naught. This is from the definition of Cauchy sequence. We take a Cauchy sequence. Tn is a Cauchy sequence in script b of n comma n dash. By the definition of Cauchy sequence, for each epsilon greater than 0, there exists a positive integer n naught such that it satisfies the condition norm Tm minus Tn less than epsilon for all n comma m greater than or equals to n naught. This is from definition of Cauchy sequence. Now let it be equation number 1 or equation number 4. Already we used 3 numbers, so let it be equation number 4. So right. Now define an arbitrary element. Let us take x be an arbitrary vector, small x be an arbitrary vector in capital N. If it is an arbitrary vector in capital N, then Tn of x obviously belongs to n dash. Tn of x belongs to n dash means the sequence Tn of x is also belongs to capital N dash, because Tn is a linear transformation from n into n dash. All the images of Tn of x, they are compulsory belongs to n dash. So Tn of x belongs to n dash. It means Tn of x is a Cauchy sequence. Tn of x is a Cauchy sequence in capital N dash. In the second part, we assume that n dash is a Banach space. In the second part, we assume that n dash is a Banach space. What is mean by Banach space? Banach space means it is a complete normed linear space. It means Tn of x is a Cauchy sequence. Tn of x is a Cauchy sequence in n dash, and this n dash is complete. What is the definition of complete? Every Cauchy sequence in it is convergent. Every Cauchy sequence in it is convergent. It means norm Tm of x minus Tn of x is less than or equals to norm Tm minus Tn of x. So which is again, I think it is equivalent to, and then we go for in the next step we are going to equivalent. We write which is equals to, which is less than or equals to. We are splitting the norm. Please See carefully. Now it is less than or equals to norm Tm minus Tn into norm x. We use this condition, this less than or equals to property, because of in the previous class we learned that whenever t is continuous, whenever t is continuous linear transformation, they satisfies one condition. Norm t of x is less than or equals to norm t into norm x. Norm t into norm x. We learned the same property in class number 9. Please remember that. So here by definition of our norm x less than or equals to 1. So applies that norm Tm minus Tn. That's it. And equation 4. Let us see equation 4. What is equation 4? Norm Tm minus Tn is less than epsilon. By applying this equation number 4, it is clearly less than epsilon. Therefore, norm Tm of x minus Tn of x is less than epsilon. Equation number 5. Equation number 5. So remember this point. Remember this point. From equation number 4 and 5. From equation number 4 and 5. From equation number 4 and 5. M comma n greater than or equals to n naught. And norm Tm of x minus Tn of x is less than epsilon, which implies as norm Tn of x is a Cauchy sequence in capital N dash, Again, since capital N dash is complete because it is a normed linear space, we have this sequence Tn of x is convergent. The sequence Tn of x is convergent, and say it is converges to T of x. Say it is converges to T of x. What it means? Tn of x tends to T of x as n tends to infinity. That is, limit n tends to infinity, Tn of x is equals to T of x. Here, let us see 1 minute. Here you observe that equation number 5 and you observe that equation number 4. There is small difference between these two, equation 4 and equation 5. In equation 4 and equation 4, we are representing Tn or Tm. They are only linear transformations. And in equation number 5, it is Tm of x and Tn of x. You observe that there is a small difference between 4 and 5. In the 4 we write only Tm minus Tn. In the 5 we write Tm of x minus Tn of x. The second condition, this condition is true for all x belongs to capital N. Here we don't say that for all x. Here just for a linear transformation only. But here for every linear transformation as well as for all x belongs to capital N. That is the difference between equation 4 and equation 5. Please remember that. Now we have a Cauchy sequence which is converges to T of x. We have to prove that now we shall prove that capital T is continuous linear transformation. Capital T is continuous linear transformation. So we start with very basic. First we show that it is a linear transformation. So x comma y belongs to capital N, alpha comma beta belongs to the field capital F. Obviously this alpha x plus beta y belongs to capital N because N is a linear space. So alpha x plus beta y belongs to capital N. Now we consider T of alpha x plus beta y, which is equals to limit n tends to infinity Tn of alpha x plus beta y, Tn of alpha x plus beta y. We prove the same thing in this step. Limit n tends to infinity, Tn of x is equals to T of x. So T of alpha x plus beta y is equals to limit n tends to infinity, Tn of alpha x plus beta y. It can be written as limit n tends to infinity, Tn of alpha x plus limit n tends to infinity, Tn of beta x. This can be written as alpha into limit n tends to infinity Tn of x plus beta into limit n tends to infinity, not plus, into beta into limit n tends to infinity Tn of beta x. Tn of x. You simply write alpha into T of x plus beta into T of x. Therefore, we conclude that T of alpha x plus beta y is equals to alpha into T of x plus beta into T of y. I am sorry, this is y. Therefore, here also every time I write x instead of x, that is y. Please remember that, correction this point. This is not x, this is y everywhere. Beta y, here also y, it is here also y, here also y. So capital T is a linear transformation. Capital T is a linear transformation. Now we show that T is continuous. Now we show that T is continuous. By definition, T of x is equals to limit n tends to infinity Tn of x. Norm T of x is equals to norm limit Tn of x, which is equals to limit norm Tn of x. This is simple mathematical calculation which is less than or equals to supremum of norm Tn of x, which is less than or equals to supremum of norm Tn into norm x, which is less than or equals to, supremum of norm Tn, we treat it as k, and norm x less than or equals to 1. So here you observe that take supremum of norm Tn is equals to k, and already we have norm x less than or equals to 1. Using these 2 points here, you get this is less than or equals to k. It means norm T of x is less than or equals to k for all x belongs to capital N. This condition implies as capital T is bounded. Capital T is bounded. By previous theorem, a bounded linear transformation is always continuous. Therefore, capital T is continuous linear transformation. Capital T is continuous linear transformation. If capital T is continuous linear transformation, capital T belongs to script b of n comma n dash. Script b of n comma n dash. So we prove that there is a Cauchy sequence Tn, there is a Cauchy sequence Tn of x that converges to T of x, and the T of x is a continuous linear transformation which belongs to script b of n comma n dash. And finally, we show that the sequence Tn converges to T. The sequence Tn converges to T. From equation number 5, already we have norm Tm of x minus Tn of x is less than epsilon for all n comma m greater than or equals to a positive integer n naught. Now hold small m is fixed. And allow n to approach infinity. Remember that. We are allowing small m is fixed and we are holding m is fixed. We are allowing small n to approach infinity. Then obviously we have norm Tn of x minus Tn of x tends to norm Tm of x
minus t of x minus t of x. Thus, we conclude that norm Tm of x minus t of x is less than epsilon. This is nothing but norm Tm minus t, norm Tm minus t is less than epsilon, is less than epsilon. Remember this in mind. Now consider, we give one more, we consider norm, norm Tn of x minus t of x is equals to norm Tn of x minus Tm of x plus Tm of x. I am subtracting and adding the same terms, plus Tm of x. You can write now minus t of x. So split them out, less than or equals to norm Tm of x minus Tn of x plus norm Tm of x minus t of x, which is less than or equals to norm Tm minus Tn into norm x plus norm Tm minus t into norm x, which is less than or equals to epsilon plus epsilon 2 epsilon, or if you divide it, if you define this epsilon by 2, which is equals to 2 epsilon, and a very small number, epsilon is a very small real number. This shows us, norm Tn of x minus t of x is less than a positive real number 2 epsilon. So this condition implies as norm Tn minus t is less than epsilon for all x belongs to capital N, or 2 epsilon for all x belongs to capital N. Thus, the sequence Tn converges to capital T in script b of n comma n dash. So the sequence Tn, every Cauchy sequence, every Cauchy sequence script Tn converges to T in script b of n comma n dash. Therefore, script b of n comma n dash is complete. Already it is a normed linear space. Now we prove that it is a complete normed linear space. Therefore, script b of n comma n dash is a Banach space. Remember that this is a Banach space whenever n dash is a Banach space. This completes the proof of the theorem, and one of the very lengthiest theorem, and I explained in detail also. So go through with the proof carefully. So that's it. Keep learning. In the next video, we learn one more theorem depends upon the functional analysis. Please go through with it. Keep learning. Hi, welcome to Sunil Maths tutorial. Functional analysis class number 11. In this video, we learn a theorem and we solve a problem. Let us see the statement of the theorem. If capital M is a closed linear subspace of a normed linear space capital N, and capital T is the natural mapping of capital N into N by M, defined by T of x is equals to x plus M for all x belongs to capital M, then capital T is a continuous linear transformation for which norm T less than or equals to 1. So right, we prove this theorem. So in the statement we have, they given that capital N is a normed linear space. Capital N is a normed linear space, and capital M is a closed subspace of capital N. Also they given that capital T maps n into the quotient space n by m, and it is defined by t of x is equals to x plus m for all x belongs to capital N. X plus m for all x belongs to capital N. We have to prove that there are 3 points you have to prove. Capital T is a linear transformation. The second point, capital T is continuous. Capital T is continuous. And in the third condition, you have to show that norm T less than or equals to 1. So this is the analysis of statement. They given that capital N is a normed linear space. N is a normed linear space, and M is a closed subspace of N. M is a closed subspace of N, and T is a mapping from capital N into the quotient space N by M, defined by the equation T of x is equals to x plus M for all x belongs to capital N. Now you have to prove that 3 conditions. Capital T is a linear transformation and T is continuous, norm T is less than or equals to 1. So we show one by one. The very first one, to prove that, to show that or to prove that capital T is a linear transformation. Capital T is a linear transformation. Our aim is to show that T is a linear transformation. So right. To prove this, let us take two elements, x comma y belongs to capital N, and two scalars alpha comma beta belongs to field capital F. By the definition of normed linear space, N is a linear space. Linear space means it is a vector space. So obviously alpha x plus beta y belongs to capital N because capital N is a linear space. Linear space means it is a vector space. So alpha x plus beta y belongs to capital N. Now we calculate T of alpha x plus beta y. By the definition of T, you observe that T of x is equals to x plus m. So T of alpha x plus beta y is equals to alpha x plus beta y plus capital M. Now by applying the definition of addition of cosets, you can write like this: alpha x plus m plus beta y plus m. Right. By the definition of scalar multiplication of cosets, we can write alpha into x plus m plus beta into y plus m. Again use this definition. What is that? T of x is equals to x plus m. So this alpha into x plus m means T of x, and beta into y plus m means T of y. Therefore we prove that condition T of alpha x plus beta y is equals to alpha into T of x plus beta into T of y for all x comma y belongs to capital N and alpha comma beta belongs to the field capital F. This condition shows us capital T is a linear transformation. Capital T is a linear transformation. That's it. Capital T is a linear transformation. Right. In the second condition, we prove that T is continuous. The second point, to prove that capital T is continuous. We prove that capital T is continuous. So right, we have, by the definition we have, since T of x is equals to x plus m. Now calculate norm T of x. Norm T of x is equals to norm x plus m. By the definition of norm of a continuous linear transformation, it can be written as supremum of norm x plus m, small m I write, where small m belongs to capital M, which is less than or equals to norm x plus small m. In particular,
If m is equals to 0, what happens? In particular, if m is equals to 0 or for m is equals to 0 which belongs to capital M, we have norm t of x is less than or equals to norm x. Norm t of x is less than or equals to norm x. So you can write like this: norm t of x is less than or equals to k into norm x for k is equals to 1. For k is equals to 1. This condition implies as capital T is bounded. Capital T is bounded. Already we learned that every bounded linear transformation is continuous. Therefore, capital T is continuous linear transformation. Capital T is continuous linear transformation. We prove the second one also. Now we go for third one. By the definition of third condition, by definition of norm of a continuous linear transformation, by definition of norm of continuous or bounded linear transformation, we have, let us write the definition. Norm t, already we learned this definition in the previous video. Norm t is equals to supremum of norm t of x such that norm x less than or equals to 1. So which is less than or equals to supremum of, because it is less than or equals to norm x. So norm x such that norm x less than or equals to 1. This is nothing but 1. Therefore, norm t is less than or equals to 1. Norm t is less than or equals to 1. This proves the every property of the condition theorem. Here we use this step. Norm t of x is less than or equals to norm x. Because of this one, norm t of x is less than or equals to norm x. So you observe that one of the important theorem for 5 marks. Remember that. Now we solve a problem according to the these properties. Let us see that problem. Capital T is a linear transformation or continuous linear transformation of a normed linear space capital N into another normed linear space N dash. If M is its null space, it means capital M is the null space of capital T. Then show that capital T induces a natural linear transformation T dash of N by M into N dash, and also that condition norm T dash is equals to norm T. It means the induced linear transformation is equal to the linear transformation T. So we write the introduction part. They given that capital N and N dash both are normed linear spaces. Both are normed linear spaces. Both are normed linear spaces. And capital T maps N into N dash. Capital T maps N into N dash be a continuous linear transformation. Be a continuous linear transformation. So right, now define one more mapping. Now define a mapping that maps pi capital N into N by M as pi of x is equals to x plus M. Pi of x is equals to x plus M, where small pi of x is equals to, you can write small m, pi of x is equals to x plus M, where small m belongs to capital M. And here this capital M is null space. There here capital M is null space of capital T. So right, again we define one more term. Again we define T dash as N by M into capital N dash such that T dash of x plus M is equals to T of x. Here you observe that how we define. This is important point here in this theorem. This is the important point in this theorem. Now see, we define T dash from N by M to N dash such that T dash of x plus M is equals to T of x for all x plus M belongs to N by M. We can prove that T dash
is induced by t is a linear transformation. So our aim is to prove that, we have to prove that capital T dash is a linear transformation. To prove that it is a linear transformation, let us take two elements x plus, let us take two elements x plus m comma y plus m belongs to n by m. Now addition of cosets, x plus m plus y plus m is equals to x plus y plus m, which belongs to n by m, which belongs to n by m. Now we calculate t dash of x plus m plus y plus m. T dash of x plus m plus y plus m is equals to t dash of x plus y plus m. T dash of x plus y plus m. By the definition of t dash, by the definition of t dash, we define t dash of x plus m. Here you observe that t dash of x plus m, t dash of x plus m is equals to t of x. So applying the same definition here, this step becomes t of x plus y. T dash of x plus y plus m becomes simply t of x plus y. T of x plus y, and t is a linear transformation. You can write t of x plus t of y. It can be written as t dash of x plus m plus t dash of y plus m. Therefore, finally we conclude that. Therefore, we conclude that t dash of x plus m plus y plus m is equals to t dash of x plus m plus t dash of y plus m. This is the first property of linear transformation. Now let us take a scalar. Let us take a scalar alpha belongs to capital F, and alpha into x plus m is equals to alpha x plus m. This is nothing but the scalar multiplication property of cosets. Now calculate t dash of alpha x plus m is equals to t of alpha x plus capital M. Applying the definition, applying the definition t dash of alpha x plus m. I'm sorry, here I write the same step again. T dash of alpha x plus m is equals to t of alpha x, and t is a linear transformation. You can write alpha into, you can write alpha into t of x, because t is a linear transformation, which is equals to alpha into t dash of x plus m. Therefore, we prove the condition t dash of alpha x plus m is equals to alpha into t dash of x plus m. Hence, from these two conditions, here it is the first one, here it is the first one, here it is the two. From conditions 1 and 2, from conditions 1 and 2, we conclude that capital T dash is a linear transformation. Capital T dash is a linear transformation. Further, you have to show that in the same problem, you have to prove that, further you have to prove that norm T dash is equals to norm T. Norm T dash is equals to norm T. So already by apply the definition of norm T dash. Now norm T dash is equals to supremum of norm T dash of x plus m such that norm x plus m is less than or equals to 1. This is the definition of continuous linear transformation. This is nothing but supremum of norm T of x such that norm x plus m is less than or equals to 1. Norm x plus m is less than or equals to 1. Since capital M is the null space by data, this M is the null space of capital T. If it is the null space of capital T, then obviously T of M is equals to 0. T of M is equal to 0. Remember that because it is a null space of T, then T of M is equals to 0. Now you can write norm T dash is equals to supremum of norm T of x plus m, norm T of x plus m such that norm x plus m is less than or equals to 1. It can be written as supremum of norm T of x plus T of m such that norm x plus m less than or equals to 1, which is nothing but supremum of, oh, I write directly that one. So right, here it is. I write directly that one. No need to write this step. No need to write this step. So you simply go through with the first step. That's it. Which is equals to supremum of norm t of y such that norm y less than or equals to 1, where y is equals to x plus m, which belongs to capital N by m, which belongs to capital N by m. This is nothing but norm t. This is nothing but norm t. Therefore, we conclude that norm t dash is equals to norm t. This completes the solution. That's it. Keep learning. Wish you all the best. And this problem is important for your 5 mark section. Observe that. Keep learning. Wish you all the best. Hi, welcome to Sunil Maths tutorial, functional analysis, class number 12. In this video, we learn a lemma which is very useful in the theorem, the Hahn-Banach theorem, which is the very important theorem in functional analysis. Let us see the statement. Let capital M be a linear subspace of a normed linear space capital N, and let f be a functional defined on capital M. If x0 is a vector not in capital M, x0 is a vector not in capital M, and if m0 is equals to m plus generator x is a linear subspace spanned by m and x0, then f can be extended to another functional f0 defined on m0 such that norm f0 is equals to norm f. We prove this theorem. We prove this lemma. This is very important to prove the Hahn-Banach theorem. So right, let us start. Suppose capital N is a real normed linear space. Suppose capital N is a real normed linear space and capital M is a linear subspace. Capital M is a linear subspace of capital N such that there is a vector x0 that does not belongs to capital M, and m0 is equals to m plus generator x0. It means m0 is generated by m plus x0, spanned by or generated by m plus x0. It means for any element y belongs to m0 can be uniquely expressed as, uniquely written as or uniquely expressed as y is equals to x plus alpha x0, where x belongs to capital M and alpha is a real number, belongs to capital R, and x0 is taken from that generator x0 is unique expression. Remember that this is an unique expression for y. This is true for every element of y belongs to m0. So remember that. Remember the symbols. Capital N is a normed linear space. M is a closed subspace of N. There is a vector x0. That does not belongs to capital M. And there is a set m0 generated by m plus generator x0. What it means? Every element y belongs to m0 can be uniquely expressible as y is equals to x plus alpha x0. Y is equals to x plus alpha x0, where x belongs to capital M and alpha belongs to capital R. Now define f0. Now define f naught from m naught into capital R as f naught of y is equals to f naught of y is equals to f naught of x plus alpha x naught, which is equals to f of x plus alpha r naught for some r naught belongs to capital R. So this is important one. Define f naught from m naught to capital R as f naught of y is equals to f naught of x plus alpha naught, which is equals to f of x plus alpha r naught, where r naught belongs to the set of real numbers capital R. Now we can show that f naught is a functional. We can prove that, or we can show that f naught is a functional. F naught is a functional, or similarly, or in another words, f naught is continuous. F naught is continuous linear transformation. We have to show that f naught is a continuous linear transformation. So for this, let us take two elements y1 comma y2. y1 comma y2 belongs to m naught. By the definition of m naught, y1 is equals to x1 plus alpha x naught and y2 is equals to x2 plus alpha x2 plus, don't write alpha every time. You can use another symbol beta x naught, where alpha comma beta are real numbers. Now sum of these two elements y1 plus y2 is equals to, you can simply write x1 plus x2 plus alpha plus beta into x naught. Now calculate f of or f naught of y1 plus y2. F naught of y1 plus y2. Let us see again the definition of f naught. F naught of y is equals to f naught of x plus alpha x naught, and it can be written as f of x plus alpha r naught. So f naught of y1 plus y2 is equals to f naught of y1 plus y2 is equals to f naught of x1 plus x2 plus alpha plus beta into x naught. By applying the definition of f naught, f of x1 plus x2 plus alpha plus beta into r naught. Already we know that f is a linear transformation. This f is a linear transformation. So you can apply this property f of x1 plus f of x2, and here it can be written as alpha r naught plus beta r naught. Now rewrite the terms f of x1 plus alpha r naught, this is the first term, plus f of x2 plus beta r naught, and again applying the definition of f naught, the first term can be written as f naught of y1 and second term can be written as f naught of y2. Therefore we conclude that f naught of y1 plus y2 is equals to f naught of y1 plus f naught of y2. Let it be equation number 1. For any real number, mu belongs to capital R, the field, consider f naught of mu y1. F naught of mu y1 means f naught of mu into what is y1? x1 plus alpha r naught. x1 plus alpha r naught. It is nothing but f naught of mu x1 plus mu alpha, I think this is x naught, mu alpha x naught. So apply the definition of f naught, you get f of mu x1 plus mu alpha r naught. Again f is a linear transformation, So it can be written as mu f of x1 plus mu alpha r naught. By taking common mu, you get simply f of x1 plus alpha r naught. This is nothing but mu into f naught of y1. Mu into f naught of y1. Therefore, we prove that f naught of mu y1, f naught of mu y1 is equals to mu into f naught of y1 for all real numbers. Mu belongs to capital R and x1 belongs to m naught. Let it be equation number 2. Now from this equation 1 and 2, from equation 1 and from equation 2, we conclude that f naught is a linear transformation. Therefore, from equations 1 and 2, we conclude that f naught is a linear transformation. Now we have to show that it is continuous. Right. We know that alpha is a scalar, and r naught is a scalar. They both are scalars. They are from field, which implies alpha into r naught is also a scalar, and every scalar is continuous. It means alpha r naught is continuous. And remember that by data, f naught is a not f naught, f by data, f is a functional. Defined. F is a functional defined on capital M. So every functional is continuous. Therefore, f is continuous. F is continuous means the function f of x is continuous. Now you have two sets. F of x plus alpha r naught is also continuous. Why? Because the sum of two continuous function is continuous. The sum of two continuous functions is again continuous. Already we show that alpha r naught is continuous, f of x is continuous. Their sum, f of x plus alpha r naught, is also continuous. F of x plus alpha r naught is nothing but f naught of x. F of x plus alpha r naught is nothing but f naught of x. F naught of x is continuous. This shows us f naught is a linear transformation. And continuous. F naught is a linear transformation and continuous on capital M naught. This shows us f naught is a functional. On M naught. This is the first part of our lemma. Now we can prove that. Next we can prove that norm f naught is equals to norm f. It is remaining to prove that norm f naught is equals to norm f. So right, without loss of generality, we may assume that we may assume that norm f is equals to 1. Without loss of generality, let us assume that norm f is equals to 1. So now we can show that norm f naught is also equivalent to 1. So right, Since f naught is continuous, to prove this, since f naught is continuous, by apply this norm of norm of the continuous linear transformation, norm f naught of x plus alpha x naught is always less than or equals to norm f naught into norm x plus alpha naught. Norm x plus alpha naught. Right. Remember that since f naught is continuous, then by the definition of norm of continuous linear transformation, we have this inequality. Norm f naught plus norm f naught of x plus alpha naught less than or equals to norm f naught into norm x plus alpha naught. So right. To show that important point, to show that norm f naught is equals to 1, it is equivalent to show that to prove that norm f naught equivalent to 1, it is equivalent to show that norm f naught of x plus alpha x naught is less than or equals to norm x plus alpha naught. Norm x plus alpha naught. Now you observe both these terms. Here there is one inequality here, and here there is another inequality. Let us observe these two inequalities. If you observe these two inequalities carefully, you can understand that norm f naught is equals to 1. So here you observe that here norm f naught is there, here norm f naught is not there. What it means? It means norm f naught is equals to 1. Norm f naught is equals to 1. So our aim is to show that this inequality. Yes. To prove this, we are defining the elements for all x belongs to capital M and take an element alpha not equals to 0. By applying the definition of f naught, since f naught of x plus alpha f plus x plus f naught of x plus alpha naught, sorry, f naught of x plus alpha x naught is equals to f of x plus alpha r naught. So the above inequality can be written as by the definition of f naught. By the definition of f naught, the above inequality can be written as, I mean, norm f of x plus alpha r naught is less than or equals to norm x plus alpha naught. Norm x plus alpha naught. Excuse me. So which implies as minus norm x plus alpha x naught is less than or equals to f of x plus alpha r naught is less than or equals to norm x plus alpha naught. Norm x plus alpha naught. So again this can be written as by subtracting f of x. By subtracting f of x, you can write like this: minus f of x minus norm x plus alpha x naught is less than or equals to alpha r naught is less than or equals to minus f of x plus norm x plus alpha x naught. Here also you have to write alpha x naught. This is not x naught. So again this inequality can be written as divide with alpha minus 1 by alpha f of x minus 1 by alpha norm x plus alpha x naught is less than or equals to r naught is less than or equals to minus 1 by alpha f of x plus 1 by alpha norm x plus alpha x naught. Norm x plus alpha x naught. So this is nothing but by applying the definition of linear transformation, minus f of x by alpha minus f of x by alpha minus norm x by alpha plus you get alpha by alpha 0, so alpha by alpha 1 is less than or equals to r naught, same is less than or equals to minus f of x by alpha plus norm x by alpha plus x naught alpha alpha get cancelled. Let it be inequality number 3. Already we use 1 and 2 there. Now take two elements x1 comma x2 belongs to capital M. x1 comma x2 belongs to capital M. Then calculate f of x1 minus f of x2 or f of x2 minus f of x1, whether it is any one, or x1 minus x2 or x2 minus x1. So since f is linear transformation, it can be written as f of x2 minus f of x1, which is clearly less than or equals to mod f of x2 minus x1. Again this is less than or equals to norm f into norm x2 minus x1. We assume that already norm f is equals to 1. By applying that here, norm x2 minus less than or equals to norm x2 minus norm x1. So which is again less than or equals to norm x2. We are adding and subtracting same element, plus x0 minus x0 minus x1. So again which is less than or equals to norm x2 plus x0 minus norm x1 plus x0. So in the left side we have f of x2 minus f of x1. Let us rearrange the terms in this inequality. We put as it is here minus f of x1 and shift this term into this side minus norm x1 plus x0 is less than or equals to minus f of x2 I think this is plus f of x2 plus norm x2 plus x0. Let it be inequality number 4. Now define two constants. Define a is equals to supremum of mod f of x1 minus norm x1 plus x0 and b is equals to infimum of minus f of x2 plus norm x2 plus x0. From this inequality 3, we can conclude that from this inequality 3, a is clearly less than or equals to b. Now from this inequality 1, I think this one, from inequality 3, again number inequality 3, a less than or equals to r naught less than or equals to b. So hence for the value of r naught or any value of r naught, mod, not minus is there, mod f naught of x plus alpha x naught is less than or equals to norm x plus alpha x naught. Our aim is also same, you have to show that. So finally we conclude that from this inequality norm f naught is equals to 1. Hence norm f is equals to norm f naught is equals to 1. This completes the proof of the lemma which is useful to prove the Hahn-Banach theorem. So one of the lengthiest one, I repeat the statement because of importance of the statement. You learn this statement. and understand this one because it is very useful to prove the Hahn-Banach theorem. Very useful to prove the Hahn-Banach theorem. Capital N is a real normed linear space. Capital N is a real normed linear space. And M is a linear subspace of N. M is a linear subspace of N. And we define a new set M naught. For an vector x naught does not belongs to capital M. M naught can be spanned by M and x naught. M and x naught. This spanned by means every vector y belongs to M naught. Every vector y belongs to M naught can be uniquely expressible as y is equals to x plus alpha x naught for all x belongs to capital M and alpha belongs to capital R. Remember that. And f is a functional defined on capital M. F is a functional defined on capital M. Then this f can be extended to another functional f naught. This f can be extended to another functional f naught and also satisfying the condition norm f naught is equals to norm f. We prove the same lemma on complex normed linear spaces also. Here we prove that we assume that N is a real normed linear space. In a similar manner, you can prove the same lemma with same property by assuming capital N as complex normed linear space. I remember that. So in the next video, we learn the Hahn-Banach theorem, which is very important theorem in functional analysis. Wish you all the best. Keep learning. Hi, welcome to Sunil Maths tutorial, Functional Analysis, class number 13. In this class, we learn one very important theorem known by the Hahn-Banach theorem. Let us see the statement of Hahn-Banach theorem. Hahn-Banach theorem. Capital M be a linear subspace of a normed linear space capital N and F be a functional defined on capital M. Then F can be extended to a functional f naught defined on the whole space capital N satisfying the condition norm f naught is equals to norm f. To prove the Hahn-Banach theorem, the previous lemma is very useful, which is explained in video number 12. Right? Let us prove this statement. Let capital N be a normed linear space. Introduction to the theorem. Let capital N be a normed linear space and capital M be a linear subspace. Capital M be a linear subspace of capital N, that is M subset to N, and F is a functional defined on capital M. F is a functional defined on capital M. What is mean by functional? Functional means is a continuous linear transformation from capital M into either real numbers or complex numbers. This is known as functional. I repeat, learn the definition of functional. Here f is a functional defined on capital M. Functional means functional is a continuous linear transformation from M into capital R or C. It is a continuous linear transformation. Right. So this is the introduction part to the theorem. N is a normed linear space. Capital N is a normed linear space. M be a linear subspace of capital N and F is a functional defined on capital M. Functional means it is a continuous linear transformation from M into either real numbers or complex numbers. So right, by previous lemma, by previous lemma. To understand this lemma, watch video number 12. By previous lemma, there exists a subspace. By previous lemma, there exists a subspace m naught of capital m naught of capital M, such that m naught is equals to capital M plus set x naught, capital M plus set x naught. It means m naught is generated or spanned by m and x naught. M naught is spanned by m and x naught for all x naught does not belongs to capital M, and this functional f can be extended. This functional f can be extended to another functional f naught such that norm f naught is equals to norm f. This is very important lemma. By using this lemma, we prove the Hahn-Banach theorem. Let us see. By using previous lemma, to understand this previous lemma, you watch video number 12 for detailed proof. There exists a subspace m naught of the linear space capital M like this, and defined like this: m naught is equals to m plus set x naught. M plus set x naught. It means m naught is spanned by m and the element x naught. Remember that where that x naught not belongs to capital M, where x naught not belongs to capital M, that x naught is taken from real number, that x naught is taken from the linear space, I mean normal linear space capital N. So right, and the functional f can be extended. The functional f can be extended to another functional. The functional f can be extended to another functional satisfying the condition norm f naught is equals to norm f. So right, now we try to prove the Hahn-Banach theorem. So what happens if m naught is equals to n? This is the important point. If m naught is equals to n, then the theorem is proved. Then there is nothing to prove. The theorem is proved. If m naught is equals to n, then the theorem is proved. If m naught not equals to n, and this m naught is subset to n, then by continuing this process of extension, we obtain functionals. Continuing this process of extension, we obtain functionals f naught, f1, f2, f3, and so on, defined on the subspaces m naught, m1, m2, m3, and so on, respectively, such that they satisfies the condition norm f naught is equals to norm f1 is equals to norm f2 is equals to norm f3 is equals to, and so on, and the sequence m1 is subset to m2, m naught is subset to m1, m naught is subset to m1, it is subset to m2, it is subset to m3, and so on. This is very important one. Observe that. By continuing the process of extension, we obtain the functionals f naught, f1, f2, f3, and so on, defined on m naught, m1, m2, m3, respectively. satisfying two conditions. Norm f0 is equals to norm f1 is equals to norm f2 is equals to norm f3 and so on. And m0 subset to m1, m1 subset to m2, m2 subset to m3 and so on. Now let us define one more set. Let capital P denote, let capital P denote the set of all ordered pairs. The set of all ordered pairs. Let P denotes the set of all ordered pairs functional f comma m, functional f naught comma m naught, functional f1 comma subspace m1 and so on. We denote it as an ordered relation and not as an, we denote it on ordered relation. We denote it on ordered relation less than or equals to as fi comma mi less than or equals to fj comma mj if and only if mi is subset to mj and fi is equals to fj on mi. Fi is equals to fj on mi. We denote all the ordered pairs with the relation less than or equals to as ordered pair fi comma mi less than or equals to fi comma mj if and only if it satisfies the condition mi is subset to mj and fi is equals to fj on the subspace mi. It is very trivial to observe that since the ordered pair f comma m belongs to P, it means capital P is non-empty. Capital P is non-empty. P is non-empty and there is a relation, ordered relation defined on P. It means P is a partially ordered set. P is a partially ordered set. So right, remember that since P is non-empty and there is a ordered relation, defined on P. Therefore, P is a partially ordered set. Now let us take capital Q be the total subset. Let capital Q be the total subset, or it is another, in other words, chain of P. That is, Q is equals to set of all ordered pairs fi comma mi. Then it is very clear because all these ordered pairs are related in ordered relation less than or equals to. Then this Q has an upper bound. Yes. Then this Q has upper bound. Thus, we conclude one point. Thus, any chain in P, any chain in the partially ordered set P has an upper bound. Observe that any chain in P has an upper bound. So any chain in P has an upper bound. Now you can use Zorn's lemma. By Zorn's lemma, I write the Zorn's lemma statement. Every partially ordered set in which each chain, every partially ordered set in which each chain has an upper bound, has a maximal element. I repeat it. See the Jones lemma statement. Every partially ordered set in which each chain has an upper bound, has a maximal element, By applying this Jones lemma to our theorem, therefore, our theorem, P has a maximal element. P has a maximal element. Let it be means let the maximal element be capital F comma H in P. So P has a maximal element and we say that F comma H is maximal in P. So to complete the proof, you have to show that to complete the proof we show that H is equals to N. H is equals to N. To complete the proof, we show that H is equals to N. If possible, we are assuming the contradictive point. If possible, let H be a proper subspace. H be a proper subspace of capital N. You have to show that H is equals to N. So if possible, let us assume that H be a proper subspace of N. That is, H is subset to N again. Then again by previous lemma, there exists an element Y naught belongs to capital N and this Y naught does not belongs to H. This Y naught does not belongs to H. So it means it is the proper subspace. So H is a proper subspace means there must be an element in N that is not belongs to H by previous lemma. Again, previous lemma means this is from video 12. Please watch video 12 to understand. By previous lemma, there exists a functional, by previous lemma, the functional F can be the functional capital F. Here we denote that functional by capital F. The functional capital F can be extended to capital F naught defined on H naught is equals to H plus generator Y naught. H plus generator Y naught which contains H properly. What it means? H is subset to H naught. It means the ordered pair F naught comma H naught is greater than the ordered pair F comma H. The ordered pair F naught comma H naught is greater than F comma H in capital P. This is a contradiction. Why? Because this is a contradiction because of P has a maximal element. And that maximal element is F comma H. This is a contradiction to that. F comma H is maximal. In P. So hence our assumption H is a proper subspace. H be a proper subspace of capital N. This assumption is wrong. H is a proper subspace of capital N is wrong. Thus we conclude that H is equals to N. So you observe that by Hahn-Banach theorem, there must be a functional F naught that is extension of the functional F defined on the closed linear space capital M satisfying the condition norm F naught is equals to norm F. Hence, this completes the proof of Hahn-Banach theorem. This completes the proof of the Hahn-Banach theorem. Hence proved. One of the very important theorem in the functional analysis. In the previous video, in the next video, I wish to explain some basic definitions according to this. The first one is maximal element and Jones lemma in detail. We go for in detail, and chain and upper bound and partially ordered set, like this. In the next video or next introduction basic video, I want to explain partially ordered set and total subset, upper bound, and so on. We'll try to upload in the next day. Keep learning. Wish you all the best. Hi, welcome to Sunil Maths tutorial. Functional analysis, class number 14. In this video, we'll learn a theorem which is an application of Hahn-Banach theorem. Let us see the statement. Capital N is a normed linear space and x0 is a non-zero vector in capital N. Then there exists a functional f0 in the normed linear space capital N satisfying two conditions. First one, f0 of x0 is equals to norm x0, and the second condition, norm f0 is equals to 1. Let us prove this theorem. Let capital N be a normed linear space. Capital N be a normed linear space. And let us define capital M be a linear subspace. Capital M be a linear subspace of capital N spanned by a vector x0, where this x0 is an element of normed linear space capital N. x0 belongs to capital N. So the linear space, the subspace M spanned by a vector x0, it means every element y belongs to capital M can be uniquely expressed as y is equals to every element y belongs to capital M can be uniquely expressed as y is equals to alpha x0, where alpha is a real number. Now define a function. Or a functional f. Now define a functional. Don't write functional. We treat it as function only. Now define a function f on capital M as f of y is equals to f of alpha x0, it is equals to alpha into norm x0. We define the function as follows. F is a function on capital M defined by f of y is equals to f of alpha x0, it is equals to alpha into norm x0. First we can prove that. This function, this f is a functional. F is a functional on capital M. Remember that. What is mean by functional? Functional is a continuous linear transformation from the linear space or subspace into either real or complex number system. This is known as functional. So we have to show that f is a functional on we have to show that f is a functional on capital M. So the first one. First we show that f is linear. F is linear transformation. F is linear transformation. So right. For this, let us take two elements. y1, y2 belongs to capital M. Every element of M can be written like this. y1 is equals to alpha x naught and y2 is equals to beta x naught, where alpha comma beta are real numbers. Alpha comma beta are real numbers. So right, now take any two scalars. Take any two scalars r comma s be any scalars r comma s be any scalars such that f of ry1 plus sy2 is equals to ry1 plus sy2 is equals to f of y1 alpha x naught. Y1 means alpha x naught plus s into y2 beta x naught. Beta x naught. You can write like this. F of r alpha x naught plus s beta x naught. This is nothing but f of r alpha plus s beta into x naught. We define the function like this. Here you observe that f of alpha x naught is equals to alpha into norm x naught. Alpha into norm x naught or mod alpha into norm x naught. So by applying the definition, you can write like this: mod r alpha plus s beta into norm x naught. So right, if you treat this norm x naught is equals to 1, then you can write like this: r alpha plus s beta, it is equals to r into alpha means f of y1 plus s into f of y2. Therefore we prove that f of ry1 plus sy2 is equals to r into f of y1 plus s into f of y2. This condition shows us f is a linear transformation. Next we show that f is continuous. In the first condition, we prove that f is a linear transformation, and in the second condition, we prove that f is continuous. Let us take an element y is equals to alpha x naught belongs to capital M. Now norm y is equals to norm alpha x naught. It is equals to mod alpha into norm x naught. Now norm alpha into mod x naught. Now mod f of y is equals to mod f of alpha x naught. It is equals to, it is obviously equivalent to mod alpha into norm x naught, which is clearly equivalent to norm y, which is less than 2 into norm y. It means mod f of y is less than some constant k, where k is equals to 2 into norm y. This condition f of y, mod f of y is less than k, implies as f is bounded. Every bounded linear transformation is continuous. Therefore, f is continuous. If f is continuous, then we conclude that f is a linear transformation and continuous. We learn that every continuous linear transformation is functional. Therefore, f is a functional on capital M. Further, let us find its norm. Norm f is equals to supremum of mod f of y such that norm y is equals to 1. such that norm y is equals to 1. It is equals to supremum of norm y, because mod f of y is equals to norm y, such that norm y is equals to 1. So this supremum is nothing but it consists only element 1, so the norm is also equivalent to 1. Therefore we conclude that norm f is equals to 1. Norm f is equals to 1. Also f of x naught is equals to norm x naught, where if we treat alpha is equals to 1, because we define f of x naught is equals to alpha x naught, so alpha is equals to 1, then f of x naught is equals to norm x naught. By Hahn-Banach theorem, by Hahn-Banach theorem, the functional f, by Hahn-Banach theorem, the functional f can be extended to another functional, the function f can be extended to another functional f naught which belongs to n star, such that f naught of x naught is equals to norm x naught and norm f naught is equals to 1. This completes the proof of our theorem. In particular, we extend this one. In particular, if you take x naught equals to y, then obviously x minus y not equals to 0. By above case, by using the above calculation, there exists a functional f naught which belongs to n star, such that f naught of x minus y is equals to norm x minus y which is not equals to 0. This condition implies as f naught of x minus f naught of y not equals to 0. Again this condition implies as f naught of x not equals to f naught of y. This shows us x not equals to y implies f naught of x not equals to f naught of y. This condition mathematically shows us n star separates the vectors in capital N. This completes the proof, hence proved our theorem. You see, so this is an application of Hahn-Banach theorem. Keep learning. In the next video we learn another theorem depends upon the same Hahn-Banach theorem. Wish you all the best. Keep learning. Hi, welcome to Sunil Maths tutorial, functional analysis, class number 15. In this video, we prove a theorem. Let us see the statement. If capital M is a closed linear subspace of a normed linear space capital N, and x naught is not a vector, not in capital M, x naught is a vector that is does not lies in capital M, then there exists a functional f naught in n star such that it satisfies two properties, f naught of m is equals to 0 and f naught of x naught not equals to 0. So right, first we write the introduction part of this theorem. They given that capital N is a normed linear space. Capital N is a normed linear space and capital M is a closed subspace. Capital M is a closed subspace of capital N. And x naught is a vector. Not in capital M. That is, x naught does not belongs to M. x naught does not belongs to m. So right, define or consider a functional, in another words, consider a natural mapping. Natural mapping means it is defined from space into quotient space. Consider a natural mapping. Capital T maps n into n by m such that it is defined like this: T of x is equals to x plus m for all x belongs to capital N with the property norm T less than or equals to 1. So right, we define a mapping capital T that maps from capital N into the quotient space n by m, satisfying the condition T of x is equals to x plus m for all x belongs to capital N with the property norm T of x is equals less than or equals to 1. So right, since capital M is closed subspace, since capital M is closed subspace of capital N, then obviously n by m is a normed linear space, with the norm of a coset, with the norm of a coset, coset means x plus capital M, which belongs to n by m, and the norm is defined by norm x plus m is equals to infimum of norm x plus small m such that small m belongs to capital M. We observe that this is true every time whenever M is a closed linear subspace of a normed linear space capital N. Then obviously the quotient space is also a normed linear space with the norm of the coset x plus m that is defined like this: infimum of norm x plus m such that m belongs to capital M. Now we show that capital T is a continuous linear transformation. Now we can prove that capital T is a continuous linear transformation. So right, first one, to show that T is linear, capital T is linear. So to prove that capital T is linear, let us consider two elements. Let us take two elements, x comma y belongs to capital N and two scalars alpha comma beta belongs to capital R are field. Now T of alpha x plus beta y is equals to, what is the definition of T? See here, T of x is equals to x plus m. T of x is equals to x plus m. By using the definition, T of alpha x plus beta y can be written as alpha x plus beta y plus capital M. Now apply the definition of addition of cosets. Alpha x plus m plus beta y plus m. Again, addition of scalar multiplication of cosets. It can be written as alpha into x plus m plus beta into y plus m. Again, by applying the definition of T, it can be written as alpha into T of x plus beta into T of y. Therefore, we prove that T of alpha x plus beta y is equals to alpha into T of x plus beta into T of y for all x comma y belongs to capital N and alpha comma beta belongs to the real numbers capital R. This condition shows us t of alpha x plus beta y is equals to alpha into t of x plus beta into t of y shows us capital T is a linear transformation. Therefore, capital T is a linear transformation. Next, in the second case, you have to show that capital T is continuous. To show that capital T is continuous, capital T is continuous. Right. To prove that capital T is continuous, we use the definition of norm. By definition of the norm, we have norm T is equals to, or norm T of x. Norm T of x is equals to norm x plus m, which is equals to infimum of norm x plus m such that small m belongs to capital M, which is less than or equals to norm x plus small m for all m belongs to capital M. In particular, what happens if small m is equals to 0? If small m is equals to 0, then norm T of x is less than or equals to norm x. Norm T of x is less than or equals to norm x. This condition shows us capital T is bounded. Capital T is bounded. Further, additionally, T is bounded means obviously T is continuous. We move one more step. Norm T is equals to supremum of norm T of x such that norm x less than or equals to 1, which is less than or equals to supremum of norm x, because norm T of x less than or equals to norm x such that norm x less than or equals to 1. This is again less than or equals to 1. So you show that norm T is less than or equals to 1. It means T is bounded. T is bounded. Whenever T is bounded, then T is continuous. It means from these two cases, we conclude that therefore capital T is a continuous linear transformation. Capital T is a continuous linear transformation. So further, let us apply here. For any small m belongs to capital M, T of small m is equals to small m plus capital M by definition. So this is nothing but m, because of small m plus capital M is zero element in capital N by M. So because small m belongs to capital M, obviously this m plus m is equals to capital M. So T of m is equals to capital M, and it is the zero element. In capital M for all small m. This condition holds for all small m. That is, T of m is equals to capital M for all small m belongs to capital M, and that is the zero element in n by m. Therefore, we conclude that T of capital M is equals to 0. Now, since already we said that x naught is a non-zero element and that does not belongs to capital M. So T of x naught is equals to x naught plus capital M, which is clearly not equals to 0. Because x naught is a non-zero element. So right, now we use the previous theorem to prove the extension. By previous theorem, this theorem is explained in video number 13. I think video number 14. Video number 14. This theorem explained in the previous theorem, just previous video of our lecture. So what is the statement of that theorem? If capital N is a normed linear space, and x naught belongs to capital N, then there exists a functional f naught in n star such that f naught of x naught is equals to norm x naught and norm f naught is equals to 1. Clearly, this is previous theorem. Applying this theorem to our theorem in this video, we get there exists a functional f in n by m star such that satisfying the condition f of x naught plus m is equals to norm x naught plus m and norm f is equals to 1. So we are applying this theorem. If n is a normed linear space and x naught belongs to n, then there exists a functional f naught in n star such that f naught of x naught is equals to norm x naught and norm f naught is equals to 1. This theorem explained in 14th video. So applying this theorem to present theorem, there exists a functional in n by m star such that f of x naught plus m is equals to norm x naught plus m and norm f is equals to 1. So now we define one more functional. Or we define a mapping. We define f naught as f naught of x is equals to f of t of x. F naught of x is equals to f of t of x for all x belongs to capital N. First we show that this f naught is linear. This f naught is linear. We prove that this f naught is linear. To prove that f naught is linear, let us consider f naught of alpha x plus beta y. By definition of f naught of x here, f of t of x. So f of t of alpha x plus beta y. Here in this theorem, already we prove that capital T is a linear transformation. And it satisfies the condition t of alpha x plus beta y is equals to alpha t of x plus beta t of y. Applying that condition here, it can be written as f of alpha t of x plus beta t of y. Again, f is also a functional. So f is also a functional. It can be written as alpha f of t of x plus beta f of t of y. Right. Again, f of t of x can be written as here. F of t of x can be written as f naught of x. So it can be written as alpha f naught of x plus beta f naught of y. Finally, we prove that f naught of alpha x plus beta y is equals to alpha f naught of x plus beta f naught of y. This shows us f naught is linear. Now we have to show that f naught is bounded. To prove f naught is bounded. So write norm f naught of x. Norm f naught of x is equals to norm f of t of x. Which is equals to norm f norm t of x. Which is less than or equals to norm f into norm x. Because norm t, we proved that norm t is less than or equals to 1. So this condition shows us norm f naught of x is less than or equals to norm f into norm x. And we know that this f is already bounded function. F is bounded. This shows us f naught is also bounded. If f naught is bounded, we know that every bounded linear transformation is continuous. F naught is continuous. Hence, f naught is a functional
F naught is a functional on n star. F naught is a functional on n star. So right, further, this F naught is an extension of F and it is a functional on n star. Further, you have to show that one more condition. If small m belongs to capital M, if small m belongs to capital M, if small m belongs to capital M, then F naught of M is equals to F naught of M is equals to F of T of M, which is equals to F of 0, which is equals to 0. Already we proved that T of M is equals to M for all 0. Hence, this condition applies as F naught of capital M is also equivalent to 0 for all small m belongs to capital M. For all small m, for all, not small m, for all subspaces, closed subspaces, capital M is subset to capital N. F naught of M is equals to 0. So right, and we go for further, F naught of x naught is equals to F of T of x naught, F of T of x naught, and T of x naught is defined by, already we defined T of x naught is equals to x naught plus capital M. We know that x naught not equals to 0. Obviously, x naught plus M is also not equals to 0. This condition implies as F of x naught plus M is also not equals to 0. It means F naught of x naught is also not equals to 0. Hence, you observe that F naught of capital M is equals to 0 and F naught of x naught is not equals to 0. So from these conditions we prove that we complete the proof of our theorem. Hence there exists a functional, in n star satisfying the above properties. F naught of M is equals to 0 and F naught of x naught is equals to 0. This completes the proof of our theorem. So remember that n star is nothing but the set of all continuous linear transformations, from capital N into either real linear space, either real or complex numbers field. Remember that n star is the set of all continuous linear transformations of n into either R or capital C. In the next video, we prove one more theorem in a similar manner, satisfying some different conditions. F naught of M is equals to 0 and F naught of x naught is equals to M 1 unit 1 and norm F naught is equals to 1 by D. In the next theorem, in the next video we prove this theorem. So keep learning. Wish you all the best. Hi, welcome to Sunil Maths tutorial, functional analysis, class number 16. In this video, we prove a theorem. Let us see the statement. Capital M be a closed linear subspace of a normed linear space capital N and x naught be a vector not in capital M. If D is the distance from x naught to capital M, then there exists a functional F naught in n star satisfying these conditions. F naught of M is equals to 0, F naught of x naught is equals to 1 and norm F naught is equals to 1 by D. This is also one of the application of previous theorems. Let us see the proof. So first we analyze the given statement and we use the previous theorem. Capital N is a normed linear space. Capital N is a normed linear space and capital M is closed linear subspace
closed linear subspace of capital N, then there exists a natural mapping. Then there exists a natural mapping capital T that maps from N into the quotient space N by M such that T of x is equals to x plus M. T of x is equals to x plus M for all x belongs to capital N and norm T less than or equals to 1. N is a normed linear space. Capital M is a closed subspace of N. There exists a natural mapping T that maps from capital N into the quotient space N by M defined by T of x is equals to x plus M for all x belongs to capital N with the property norm T less than or equals to 1. In the given data we have, there is a vector x naught in capital N, but the same vector does not belongs to capital M. X naught does not belongs to capital M means x naught plus M is not equals to 0. X naught plus M is not equals to 0 means T of x naught plus M is equals to, T of x naught is equals to x naught plus M, which is not equals to 0. Therefore, we conclude that T of x naught is not equals to 0. T of x naught is not equals to 0. Right. By previous theorem, I write the statement of previous theorem. By previous theorem, if N is a normed linear space, if capital N is a normed linear space and x naught is a non-zero vector in N, x naught is a non-zero vector in capital N, then there exists a functional N naught, there exists a functional F naught in N star such that F naught of x naught is equals to norm x naught and norm F naught is equals to 1. This is the previous theorem. Actually, this theorem is proved in theorem video number 14. I think video number 14. You check it. So applying this theorem to our present theorem, there exists a functional f that belongs to n by m star such that f of x naught plus m is equals to norm x naught plus m. Let it is equals to d, small d, say. Where it is very clear, d not equals to 0, and we observe that by the property norm f is equals to 1. Now we define a new function. Another function. Define f naught, that is from capital N into real numbers or either real numbers, n into f, satisfying the condition f naught of x is equals to 1 by d f of t of x. 1 by d f of t of x for all x belongs to capital N. First we show that this f naught is a functional. Our first aim is to show that this f naught is a functional. Functional means it is a continuous linear transformation. So in the first phase we prove that it is a functional. To show that f naught is a functional, we show that it is linear. To show that f naught is a linear transformation. Right. To prove this linear, let us take two elements, x comma y belongs to capital N and alpha comma beta belongs to the field capital F, are real numbers, scalars. Then by the definition of linear space, alpha x plus beta y is clearly belongs to capital N because it is a linear space. Since N is linear space. Linear space means it is a vector space. So obviously it satisfies this condition. Alpha x plus beta y belongs to capital N, which implies as or not implies. Let us consider one element. Consider f naught of alpha x plus beta y is equals to, let us see the definition. F naught of x is equals to 1 by d f of t of x. F naught of x is equals to 1 by d f of t of x. Applying this definition here, you can write like this. 1 by d f of t of alpha x plus beta y, which is equals to 1 by d f of t is a linear transformation. Already we know that capital T is a linear transformation. Applying that condition, alpha into t of x plus beta into t of y. Alpha into t of x plus beta into t of y. Again it can be written as 1 by d f of alpha t of x plus 1 by d f of beta t of y. Again it can be written as alpha 1 by d f of t of x plus beta 1 by d f of t of y. Now applying the same definition of f naught, it can be written as alpha into this term 1 by d f of t of x can be written as f naught of x plus beta. Again this term 1 by d f of t of y can be written as f naught of y. Therefore we prove that you observe the LHS, f naught of alpha x plus beta y is equals to alpha into f naught of x plus beta into f naught of y for all x comma y belongs to capital N and alpha comma beta belongs to the real numbers capital R, field of scalars. This condition shows us f naught is a linear function, or f naught is a linear function on N. F naught is linear transformation. F naught is linear transformation where on capital N. The next side heading you have to show that f naught is continuous. To show that f naught is continuous. Right. Since f is a functional, where it is defined? It is defined on capital N. F is a functional on capital N, which implies as f is continuous. Every functional is continuous on capital N. If f is continuous and d is a non-zero scalar, then 1 by d into f is also continuous on capital N. Further, they given that norm t is less than or equals to 1. It implies capital T is bounded linear transformation. We know that every bounded linear transformation is continuous. Therefore, capital T is continuous. If capital T is continuous and also we have this 1 by d into f is also continuous, then we conclude that 1 by d into f of t of x is also continuous. You remember here 1 by d f of f is continuous and t is continuous. Therefore 1 by d f of t of x is also continuous. If this is continuous, by definition of f naught of x, what is f naught of x? F naught of x is equals to 1 by d f of t of x. The term in RHS is continuous. The term in RHS is continuous. What it means? F naught is also continuous. F naught is also continuous. That is the required result. F naught is also continuous. Hence, we conclude that F naught is a functional. F naught is a functional on capital N. If it is a functional on capital N, then it is obviously belongs to N star. F naught belongs to N star. Now we have to prove that. In the next part, we have to show that. We have to prove that, or we have to show that three different conditions. The first one, f naught of x naught is equals to 1, and the second one, f naught of m is equals to 0, and the third condition, norm f naught is equals to 1 by t. We prove one by one. So in this part, we prove these three conditions. Let us go for first one to prove the first condition. Now consider f naught of x naught is equals to 1 by d f of t of x naught. So which is equals to 1 by d f of, what is t of x naught? X naught plus capital M. What is x naught plus capital M? F of x naught plus capital M. We define already, it is norm x naught plus M. And we define norm x naught plus M as d. So d into 1 by d is equals to 1. Therefore, we prove that f naught of x naught is equals to 1. This is the first condition. So we go for again backside. Let us see one by one. Here f naught of x naught, f of x naught plus m is equals to norm x naught plus m. Norm x naught plus m. Norm x naught plus m is equals to d. Norm x naught plus m is equals to d. And already, so we use the same conditions here. F naught of x naught is equals to 1 by d f of t of x naught, and t of x naught is equals to x naught plus m, and f of x naught plus m is equals to norm x naught plus m. Norm x naught plus m is equals to d, and d by d is equals to 1. This proves the condition f of x naught is equals to 1. We go for second condition now. We have to prove the second condition. Now f naught of m is equals to 1 by d f of t of m. Already we know that t of m is equals to 0. This is standard property by previous theorem. T of m is equals to 0. So 1 by d f of 0. F of 0 is equals to 0. 1 by d into 0. F of 0 is equals to 0. So 1 by d into 0. 1 by d into 0 means you get 0. Therefore, f naught of capital M is equals to 0. This is the second condition of our theorem. Now we are going to prove the third condition. Third condition. Norm f naught is equals to supremum of mod f naught of x such that norm x is equals to 1. So this can be written as supremum of, by the definition of f naught, mod 1 by d f of t of x such that norm t of x is equals to 1. Norm t of x is equals to 1. 1 by d is constant, so write outside 1 by d supremum of, this can be written as f of t of x mod f of t of x divided by norm t of x such that, because norm t of x is not equals to 0, I am dividing this one f of t of x divided by norm t of x, f of t of x by norm t of x. So again it is equals to 1 by d supremum of mod let us see I can rewrite like this. I'm sorry. Mod. I'm very sorry for this. Right. Mod. Every time I said mod. Mod f of t of x, divided by norm t of x. F of t of x divided by norm t of x, such that norm t of x not equals to 0. So again, this is nothing but norm t of x by t of x is equals to 1 by d into supremum of mod f of y, where norm y is equals to 1, and where this y is equals to t of x by norm t of x. You observe carefully, norm y is clearly 1 because of y is equals to t of x by norm t of x. So this condition again equivalent to 1 by d into supremum of norm f into norm y, such that norm y is equals to 1. Already we know that this norm f is equals to 1. This norm f is equals to 1. So 1 by d supremum of norm y, and norm y is equals to 1. So this is nothing but 1. 1 by d into supremum of this whole value is equivalent to 1. So you get 1 by d. Hence, norm f naught is equals to 1 by d. Hence, norm f naught is equals to 1 by d. This completes the proof of our theorem. Hence, proved. Observe that. One of the very, very important theorem, or which is also known as application of Hahn-Banach theorem. All these video number 14, video number 15 and video number 16 will learn 3 different theorems which are in the same manner. Their proof is similar to one another. So all these 3 theorems are applications of Hahn-Banach theorem. Wish you all the best. Keep learning. Hi, welcome to Sunil Maths tutorial, functional analysis, class number 17. In this video, we learn some basic definitions and some notations. Let us see. We know that capital R and capital C means the set of real numbers and the set of complex numbers are the simplest of all the normed linear spaces. So the set of real numbers and the set of complex numbers are the simplest normed linear spaces. If capital N is an arbitrary normed linear space, we can form the set of all continuous linear transformations of capital N into capital R or into capital C. I mean the set of all linear transformations capital T, either T maps N into R, this is one set, and one more set, T maps capital N into C. One is the set of real numbers, the second one is set of complex numbers. So the set of all continuous linear transformations of capital N into R or capital N into C. We denote the set of all these continuous linear transformations by script b of n comma r or script b of n comma c. See, this one is denoted by script b of n comma r, it means, and this one is script b of n comma c. What it means? Set of all continuous linear transformations from capital N into R. This is also same, but the codomain is C, complex numbers. So remember the notations. Script B of R is the set of all continuous linear transformations defined from a normed linear space into the set of real numbers. And the script B of n comma c is the set of all continuous linear transformations defined from normed linear space into the set of complex numbers capital C. Simply it is denoted by n star. This set is denoted by, these two sets are denoted by n star, and it is called, the wording, this is important, conjugate space of n. I mean, n star is the, what it means? What it means? Capital N star is the, capital N star is the set of all continuous linear transformations from capital N into R or from capital N into C according to the field either R or C. And this one is known as conjugate space of n. This one is known as conjugate space of n. Also, the elements of n star are called linear functionals. The elements of n star are called linear functionals, or more briefly, simply functionals. The elements of n star are called linear functionals. They are simply called functionals, right? And then we say that n star is called the conjugate space of n. N star is called the conjugate space of n. Remember that n star is called the conjugate space of n and is itself a linear normed linear space. Remember that n star is also normed linear space, right? Next, continue this one. It is possible to form the conjugate space n star whole star of capital N star. It means n star is a conjugate space of n double star is conjugate space of n star. That's it. We denote this space by n double star. So n double star is known as second conjugate space of n. N double star is known as second conjugate space of capital N. Second conjugate space of capital N. And n star is known as conjugate space or first conjugate space of capital N. Next, we see the definition: isometric isomorphism. Isometric isomorphism. Let capital N and N dash be two normed linear spaces. A linear transformation capital T that maps N into N dash is called isometric isomorphism. If it satisfies two conditions. One, capital T is a 1-1 mapping and norm T of x is equals to norm x for all x belongs to capital N. I repeat the definition, you observe that capital N and N dash are two normed linear spaces. Capital T is a linear transformation from N into N dash. This linear transformation T is called isometric isomorphism if it satisfies two conditions. First one, T is 1-1, and second one, norm T of x is equals to norm x for all x belongs to capital N. Further, if capital T is onto, in addition to these two properties, if T is onto, then we say that capital N is isometrically isomorphic. Then capital N is isometrically isomorphic or simply congruent. Either isometrically isomorphic or congruent to the linear space N dash. So right, next we go for next definition. Let capital N be a normed linear space and T be an operator. T is an operator means capital T is continuous linear transformation on capital N. It means capital T maps N into N is a linear transformation. That's it. Capital T maps N into N is a linear transformation which is also continuous. Now we will define another linear transformation N star, T star on N star. So here you observe that the T is defined over N and T star is defined over N star into N star. Then this mapping is known as conjugate of T. T star is known as conjugate of T. So T defined over capital N and T star is defined over N star, conjugate space N star. That's why we say that T star is conjugate of capital T. In the next video, we learn natural embedding theorem. embedding, natural embedding theorem. In the next video, we'll learn this theorem, natural embedding theorem, which is very, very important. So keep learning. Wish you all the best.
Hi, welcome to Sunil Maths tutorial, functional analysis, class number 18. In this video, we learn one very, very important theorem, natural embedding theorem. Let us see the statement. If capital N is a normed linear space with second conjugate n double star, then there is a natural embedding of n into n double star. The same statement can be written like this also. This one is known as elaborated statement, in detailed statement. Capital N be a normed linear space, then each vector x belongs to capital N induces a functional fx of n double star defined by fx of f is equals to f of x for all f belongs to n star such that norm fx is equals to norm x for all x belongs to capital N. Further, the mapping pi maps capital N into n double star defined by pi of x is equals to fx is isometric isomorphism of capital N into n double star. Let us prove this statement. In the previous lecture, we learned about isometric isomorphism. Let us prove the statement now. Let capital N be a normed linear space. Capital N be a normed linear space. Right? For each x belongs to capital N, define for each x belongs to capital N, define fx on n double star as fx of f is equals to, you see, I'm sorry, fx of f is equals to f of x for all x belongs to n star. This is the definition of fx. Remember that. Throughout this theorem, we use the same definition. First, we shall show that fx is a functional on n double star. First, we show that this fx is a functional on n double star. It means we show that this fx is linear transformation and continuous. So the first side heading, fx is linear. First we show that it is a linear transformation. To prove that it is a linear transformation, let us take two elements, small f comma g belongs to n star, are any two arbitrary functions. They are any two arbitrary functions, and alpha comma beta are any two scalars, means belongs to real numbers. F comma g belongs to n star and alpha comma beta are any two scalars. Now consider fx of alpha f plus beta g. By the definition of fx, we define fx like this. Fx of f is equals to f of x. So by applying the same definition, it can be written as alpha f plus beta g of x. Alpha f plus beta g of x. It can be written as alpha f of x plus beta g of x. Alpha comma beta are scalars. It can be written as alpha into f of x plus beta into g of x. Alpha into f of x plus beta into g of x. Again, what is this f of x? Alpha
capital fx of x or capital fx of f plus beta fx of g, fx of g. Therefore, we prove that fx of alpha f plus beta g is equals to alpha fx of f plus beta fx of g. This condition shows us fx is a linear transformation. Fx is a linear transformation. We know that the standard definition of linear transformation t of a alpha plus b beta is equals to a into t of alpha plus b into t of beta. The same condition we prove here in terms of fx. In terms of fx. Therefore, fx is a linear transformation. Next, I am going to prove fx is bounded. Next side heading, fx is bounded. Fx is bounded. So, right. We know the definition of norm fx. We know that norm fx is equals to supremum of mod fx of f such that norm f less than or equals to 1. This is the norm of the linear transformation. Which is equals to supremum of mod f of x by the definition of fx, mod f of x such that norm f less than or equals to 1, which is less than or equals to supremum of norm f into norm x such that norm f less than or equals to 1. Again, norm f is less than or equals to 1. This inequality is less than or equals to norm x. Therefore, we prove that norm fx is less than or equals to norm x. Let it be equation number 1. And remember this equation. Norm fx is less than or equals to norm x and it is equation 1. This condition implies as fx is bounded. Every bounded linear transformation is continuous. Therefore, fx is continuous. What it means? Fx is continuous linear transformation. On capital N star. This shows us fx is a functional on n double star or conjugate, second conjugate space of n. So fx is a functional on n double star. Now we can prove that, or now we have to prove that. Now we have to prove that norm fx is equals to norm x. Remember this equation 1. In equation 1 we prove that norm fx less than or equals to norm x. So to prove that norm fx is equals to norm x, it is equivalent to prove that norm x less than or equals to norm fx. If this condition holds, by previous condition norm fx less than or equals to norm x, then we combining both the conditions, we get the required this result. So right. Now let us take x be any non-zero vector. X is any non-zero vector. Then by Hahn-Banach theorem, by applying the Hahn-Banach theorem here, there exists a functional f naught that belongs to n star, such that f naught of x is equals to norm x and norm f naught is equals to 1. So applying here fx of f naught is equals to f naught of x. fx of f naught of x is equals to f naught of x. Now norm x is equals to norm fx of f naught, because this is equals to norm x. This is equals to norm x. So mod fx of f naught, which is less than or equals to norm fx into norm f naught. And again norm f naught is equals to 1. So this is less than or equals to norm fx. Therefore we show that norm x is less than or equals to norm fx. Let it be equation number 2. Equation number 2. What is equation 1? What is equation 1? Norm fx is less than or equals to norm x. This is equation 1. So from equation 1 and 2, from equations 1 and 2, from equations 1 and 2, we conclude that norm fx is equals to norm x. Norm fx is equals to norm x. Let it be equation number 3. So further here observe that it is a non-zero vector. Non-zero vector. Here x is a non-zero vector. Further, whenever x equal to 0, what happens? Norm f naught is equals to norm 0. It is equals to 0. It means norm fx is equals to 0 if x is equals to 0. Norm fx is equals to 0 if x equals to 0. So remember that. Norm fx is equals to 0 if x equal to 0. So right, up to this part, we prove a functional fx satisfying all the required conditions of the theorem. Now finally we show that the mapping pi maps capital N into N double star second conjugate space defined by pi of x is equals to capital Fx is an isometric isomorphism. An isometric isomorphism. An isometric isomorphism is nothing but a continuous linear transformation which is 1 1. A linear transformation which is 1 1, not continuous. A linear transformation which is 1 1. So isometric isomorphism means you have to show that it is a linear transformation as well as it is 1 1 also. So right, we are going to prove that. So remember that here the function is defined like this: pi of x is equals to fx. Pi of x is equals to fx. So we have to show that pi is both 1 1 and linear transformation. Our aim is to show that pi is both 1 1 and linear transformation. So right, the first one, pi is linear. So to prove that pi is linear, we use two different conditions. By that definition of linear transformation, t of alpha plus beta is equals to t of alpha plus t of beta, and t of a alpha is equals to a into t of alpha. We use these two conditions to prove that our pi is linear. So let us take any two vectors in n, x comma y belongs to capital N. Now fx plus y of f is equals to, by definition of fx, f of x plus y, and f is a linear transformation, you can write f of x plus f of y. Since f is linear, small f is linear transformation, so f of x plus f of y, f of x can be written as fx of f of y can be written as fy of f. So this is nothing but fx plus fy of f. From this we conclude that, fx plus y is equals to fx plus fy. This is the first condition like this. T of alpha plus beta is equals to t of alpha plus t of beta. Now consider any scalar. For any scalar alpha, consider f alpha x of f. This can be written as f of alpha x. This can be written as alpha into f of x. This can be written as alpha into fx of f. Therefore, we conclude that f alpha x is equals to alpha fx. This is the second condition. This is nothing but like this second transformation, t of a alpha is equals to a into t of alpha. So here fx plus y is equals to, here fx plus y is equals to fx plus fy means pi of x plus y is equals to pi of x plus pi of y, and here f alpha x is equals to alpha f of x means pi of alpha x is equals to alpha into pi of x, alpha into pi of x. From these two conditions, 1 and 2, from these two conditions, we conclude that pi is linear. We conclude that pi is linear. Therefore, pi is a linear transformation. Next, you have to show that pi is 1, 1. To prove that pi is 1, 1. To prove that pi is 1, 1. To prove that pi is 1, 1, again let us take two elements. Let us take two elements, x comma y. They belongs to capital N. And suppose you assume that pi of x is equals to pi of y. If pi of x is equals to pi of y, then pi of x minus pi of y is equals to 0, which implies as pi of x minus y is equals to 0, which implies as x minus y is equals to 0, x minus y is equals to 0, which implies as x equal to y, x equal to y. Therefore, we assume that, pi of x is equals to pi of y, and we prove that x equal to y. We prove that x equals to y. This shows us pi is 1, 1. This shows us pi is 1, 1. Therefore, pi is 1, 1. Further, we calculate one thing. Further, pi of or norm pi of x minus y is equals to norm pi of x minus pi of y, which is equals to norm fx minus fy, which is equals to norm fx minus y, which is equals to norm x minus y. Why? Because norm fx is equals to norm x. Norm fx is equals to norm x. So norm fx minus y is equals to norm x minus y. Therefore, norm pi of x minus y is equals to norm x minus y. Hence, pi maps capital N into N double star is 1, 1 and linear transformation, and also preserves the mapping, and also norm pi of x minus y is equals to norm x minus y. Hence, from this function pi, we conclude that for each vector x belongs to capital N induces a functional fx of n double star, such that norm fx is equals to norm x is an isometric, induces an isometric isomorphism pi, an isometric isomorphism. Therefore, we conclude that capital N is isometric isomorphism to n double star. So remember that. This completes the proof of the theorem. Hence proved. Keep learning. Wish you all the best. Hi, welcome to Sunil Maths tutorial, functional analysis, class number 19. In this video, we learn some definitions and one very important and lengthiest theorem. Let us see the definitions. Open sphere. Let us define open sphere first. Let capital X comma D, let capital X comma D be a metric space, capital X comma D be a metric space, and X naught is an element of capital X if capital R is any positive real number, if small r, I'm sorry, if small r is any positive real number, then the set of all elements X belongs to capital X such that D of X comma X naught less than small r is called an open sphere, is called an open sphere, or it is also called an open ball. Open sphere and open ball are same terms. Here the point X naught is called, there is a point, the point X naught is called center. X naught is called center of the sphere, center of the open sphere, center, and R is called, small r is called radius, small r is called radius of the open sphere, and it is denoted by, there is a symbol for this, it is denoted by capital S of X naught comma R or SR of X naught. So let us see, X comma D be a metric space, X naught is an arbitrary point of capital X, small r is an element, small r is any positive real number, then the set of all elements small x belongs to capital X satisfying the condition D of X comma X naught is less than R is called an open sphere or open ball. The point X naught is called center and the positive real number R is called radius of the open sphere. This open sphere is denoted by S of X naught comma R or SR of X naught. That is, you can write like this. S of X naught comma R is equals to SR of X naught is equals to set of all elements X belongs to capital X such that D of X comma X naught is less than small r. Here this X naught is center and this positive real number small r is radius. This set is known as open ball or open sphere. That's it. This is the definition for open sphere. Right, now we go for next definition, closed sphere. A closed sphere, it is also known as a closed ball. Closed ball is denoted by capital S of closed interval X naught comma R and defined as the set of all elements X belongs to capital X such that D of X comma X naught less than or equals to small r. Now you observe the difference here. This is open ball, and whenever you write the closed ball, the symbol is closed interval X naught comma R and defined as set of all elements X belongs to capital X such that D of X comma X naught less than or equals to small r. Here this is the main difference. Here the set of all points which less than r. Here the set of all points which less than or equal to r. less than or equal to R. So this is known as closed sphere. This is known as closed sphere, right? Now we go for next definition, open set. Open set. Let capital X comma D be a metric space. Let capital X comma D be a metric space, and capital capital A is a subset of capital X. Capital A is a subset of capital X. Then capital A is called open set. Capital A is called open set if and only if for each x belongs to capital A, there exists small r greater than 0 such that s of x comma r is a subset to capital A. S of x comma r is subset to capital A. What it means? That is for every point x belongs to capital A, for every point x belongs to capital A, there is an open sphere, in capital A corresponding to x. Remember that, corresponding to x, that is the point. So whenever we said that a set is open, it means for every x belongs to capital A is open, implies and implied by for each small x belongs to capital A, there exists an open sphere S of x comma r which is subset to capital A, So that's it. Now we go for next definition, interior point. Let capital A be a subset of a metric space. Let capital A be a subset of a metric space, capital X comma D. A point small x belongs to capital A is called an interior point, of capital A if capital A is a neighborhood of x. Capital A is a neighborhood of x. Then it is called, the point is called interior point. So here we learn one more term, the set of all interior points. The set of all interior points of capital A is called interior of A, and it is denoted by interior of A is denoted by int of capital A, or it is also denoted by a power naught, a power 0, small 0, a power small 0. So right, so this is the definition for interior point. So we learn here open sphere, and we learn closed sphere, we learn open set, and we learn interior point. Now let us see some properties of all these definitions. So first one, properties of all these. A power 0 means interior of A is largest. A power 0 means interior of A is the largest open set in A. Let us see in the note point 2, or second property. A power 0 means interior of A is the union of Interior of A is the union of all open sets, all open sets contained in capital A, contained by capital A, contained in capital A. Property number 3, A power 0 is subset to A is subset to A bar. A bar means closure. And fourth point, A power 0, fourth point, A is open, capital A is open, implies and implied by A power 0 is equals to A. Interior, what is A power 0 means? Remember that it is interior of A. Interior of A is equals to A. And property number 5, capital A is closed set, capital A is closed set, implies and implied by A is equals to A bar, A closure. A is equals to A bar. And property number 6, A subset to B implies A interior is subset to B interior, and A closure is subset to B closure. A closure is subset to B closure. Now go for seventh point. A intersection B whole power 0 is equals to A interior intersection B interior. In a similar manner, A interior union B interior is equals to A union B whole interior. Let us see eighth point. A union B whole bar is equals to, or it is subset to A bar intersection B bar. And A union B whole bar is equals to A bar intersection B bar. And let us see, there is a small doubt in this interior one. I can clarify this again. Let us see the eighth one. A interior power interior to the interior, A power whole power 0 is equals to A power 0, and A bar whole bar is equals to A bar. A bar whole bar is equals to A bar. Let us see now. We learn one more definition here. Closure of a set. Let us see. Let capital A be a subset. Let capital A be a subset of a metric space. Capital X. The closure of capital A is denoted by the symbol A bar and defined as the intersection of all closed sets, containing capital A, all closed set containing capital A. That is A bar is equals to intersection set of all sets F such that F is closed and F is superset to A. F is closed and F is superset to A. So remember that by using this definition, you can conclude that A bar is the, by this definition, you can conclude that A bar is the smallest closed set containing capital A. A bar is the smallest closed set containing capital A. So right. So this is known as closure of a set, and you remember this definition. Closure means it is the intersection of all closed sets. Containing the set capital A. All closed set containing the set capital A. Remember that. Here we learn some properties according to this closure. First one, A union B whole bar is equals to, A union B whole bar not is equals to A union B whole bar is subset to A bar intersection B bar and A union B whole bar is equals to A bar union B bar. A bar union B bar. Remember this. Remember this. A union B whole bar is equals to A bar union B bar. At the same time, A union B whole bar is subset to A bar intersection B bar. A bar intersection B bar. I think there is a small correction in this property even in our textbook also. A intersection B whole bar. A intersection B whole bar is subset to A bar intersection B bar. Is subset to A bar intersection B bar. You can see the proof also. You can see the proof also. In the next video we will learn that. Let us continue our class. There is a theorem, one of the very important one, which is very useful to prove the open mapping theorem. So this is the base for open mapping theorem. Let us see the statement. Capital B and B dash are two Banach spaces and capital T maps B into B dash is a continuous linear transformation of B onto B dash. Then the image of each open sphere centered at origin in capital B contains an open sphere centered at origin in B dash. I repeat the statement. Observe carefully. B and B dash are Banach spaces. T is a linear transformation from B into B dash, which is continuous and onto. Then the image of each open sphere. Centered at origin in B contains an open sphere centered at origin in B dash. Right. In the next video, we write the proof of this theorem. Keep learning. Wish you all the best. Hi, welcome to Sunil Maths tutorial, class number functional analysis, class number 20. In this video, we prove a theorem. Let us see. Capital B and B dash are two Banach spaces and capital T maps B into B dash is a continuous linear transformation of B onto B dash. Then the image of each open sphere centered at origin in capital B contains another open sphere centered in B dash. So right, let us prove this theorem. Lengthiest one, be patient and follow carefully. Let capital B and B dash be any two Banach spaces. And capital T maps B into B dash, is a continuous linear transformation and is itself onto also. Now define let two open spheres. Let SR be the open sphere. With radius small r, centered at origin in capital B, and SR dash, same SR dash be another open sphere. SR dash be the open sphere with radius small r, centered at origin in B dash, respectively. Remember that I define two open spheres, SR with radius r with centered at origin in B, SR dash with radius R centered at origin in B dash. Remember that both are open spheres with same radius R. Both are centered at origin, but one is defined in B, the second one is defined in B dash. Right. Now we see that. Then we see that what is SR? Let us write the definition of open sphere. X such that X belongs to B and norm X is less than small r, which is equals to X such that X belongs to B, norm X by R is less than 1. Now replace X by Ry. Now replace X by Ry. Ry such that Y belongs to capital B, norm Ry divided by R is less than 1. It can be written as which is equals to set of elements Ry where Y belongs to capital B and R into norm Y divided by R is less than 1. This is nothing but set of all elements Ry such that Y belongs to capital B and norm Y is less than 1. Norm Y less than 1. So this R is constant. It can write outside of the set small r into Y such that Y belongs to B, comma norm Y is less than 1. So this by applying, if you understand the set carefully, this is also an open sphere. This is also an open sphere centered at origin with radius less than 1. With radius less than 1. What it means? This set can be equivalent to small r into S1. Small r into S1 because radius is 1. So now you observe that SR is equivalent to R into S1. So we prove that SR is equals to R into S1. R into S1. Now apply T of SR. T of SR is equals to T of R into S1. Capital T is a linear transformation. So it can be written as R into T of S1. R into T of S1. Therefore, T of SR is equals to R into T of S1. Remember this equation throughout the theorem, it is useful for us. Let it be equation number 1. Let it be equation number 1. Now we show that, or now it is sufficient to show that T of S1 contains some SR. T of S1 contains some SR. Then obviously the open sphere lies in another open sphere. So we go for it. First we prove that T of S1 bar contains an open sphere. T of S1 bar contains an open sphere SR dash. So right, for each positive integer n belongs to capital N, consider an open sphere Sn in capital B. Let us see. For each positive integer small n belongs to capital N, consider an open sphere Sn in the Banach space capital B. Then it is clear that this B can be written as union n is equals to 1 to infinity Sn. Union n is equals to 1 to infinity Sn. Since capital T is onto, by applying the definition of onto, B dash is equals to T of B. It is equals to T of union n is equals to 1 to infinity Sn, which is equals to union n is equals to 1 to infinity T of Sn. Let it be equation number 2. Therefore, I mean this is b dash is equals to union n is equals to 1 to infinity t of Sn. Again, since this b dash is complete, b dash is complete, we know that every Banach space is complete. Every Banach space is complete. So b dash is complete. Now by applying Bayer's theorem, I write here. Therefore, Bayer's theorem. What is the Bayer's theorem? I write the statement here. If a complete metric space, is the union of sequence of its subsets, then the closure of at least one set in that sequence must have non-empty interior. Remember that this is known as Bayer's theorem. You remember that. You practice this theorem, you by heart this statement. Bayer's theorem states that if a complete metric space is the union of sequence of its subsets, then the closure of at least one set in that sequence must have non-empty interior. Here b dash is also union of subsets, union of sequence of its subsets. So by applying this Bayer's theorem to our b dash, there exists some t of Sn naught has an interior point y naught, which may be assumed to lie in t of Sn naught. That is, y naught belongs to t of Sn naught. Now consider a mapping. F that maps from b dash into b dash such that f of y is equals to y minus y naught. Let us consider a mapping that maps from b dash into b dash such that f of y is equals to y minus y naught. We can see that this f is a homeomorphism. We can see that this f is a homeomorphism. By using this mapping, we see that by using the mapping f, 0 is an interior point. Of the set capital T of Sn naught bar minus y naught, because already it is a y naught is an interior point of T of Sn naught. So obviously 0 is an interior point of T of Sn naught minus y naught. So T of 0 is an interior point of this one, means there exists an open set. Capital G such that y naught belongs to G and it is subset to T of Sn naught bar. There exists an open set G such that y naught belongs to G, it is subset to T of Sn naught bar. Y naught is subset to, applying the same condition to our theorem, f of y naught is belongs to f of G subset to f of T of Sn naught bar. So here in the first case we write only y naught belongs to G subset to T of Sn naught bar. Here in this case I write the images. F instead of y naught, f of y naught. Instead of G, f of G is subset to f of T of Sn naught bar. So right, therefore, which implies as this condition implies as y naught minus y naught is equals to 0, which belongs to f of g, which belongs to f of g, and this f of g is subset to t of Sn naught minus y naught bar. So this condition implies as 0 belongs to f of g, which is subset to t of Sn naught bar minus y naught. This shows us 0 is interior point, 0 is interior point of t of Sn naught bar minus y naught. Again, we know that in the initial stage, y naught is an element in t of Sn naught. In the first Bayer's theorem, we conclude that y naught belongs to t of Sn naught. So, y naught is an element in t of Sn naught. Now, applying the same property, t of Sn naught minus y naught is subset or equivalent to t of S2n naught, which implies t of Sn naught bar minus y naught is subset to t of S2n naught. Let us take an element y belongs to t of Sn naught minus y naught. Then there exists another element x belongs to S2n naught such that y is equals to t of x minus y naught, where norm x is less than n naught. Also since y naught belongs to t of Sn naught implies there exists an element x naught belongs to Sn naught such that y naught is equals to t of x naught, because t is onto with the property norm x naught is less than or less than n naught. Norm x naught is less than n naught. So right, we continue. So using all these calculations, we conclude that y is equals to t of x minus t of x naught. This is equals to t of x minus t of x naught. This is equals to, by linear transformation definition, t of x minus x naught. Let it be. Therefore, we conclude that y is equals to t of x minus x naught, where both x comma x naught belongs to Sn naught. Let it be equation number 3. Equation number 3. Here norm x is less than n naught. Norm x naught is also less than n naught. Applying these two conditions, norm x minus x naught is less than or equals to norm x plus norm x naught, which is less than or equals to n naught plus n naught, which is less than or equals to 2n naught. Therefore, norm x minus x naught is less than or equals to 2n naught. This condition implies as the element x minus x naught belongs to S2n naught. S2n naught. If the element x minus x naught belongs to S2n naught, then t of x minus x naught belongs to t of S2n naught, which implies t of x minus x naught is nothing but y that belongs to t of S2n naught. Already we defined here. Here see, from equation 3, y is equals to t of x minus x naught. So t of x minus x naught belongs to t of S2n naught means y belongs to t of S2n naught. So this shows us y belongs to t of Sn naught minus y naught. So which implies sorry, which implies t of Sn naught minus y naught is subset to t of S2n naught. That is the point. T of Sn naught minus y naught is subset to t of S2n naught. So right, already we proved that in the initial stage, t of Sr is equals to r into t of S1. Applying the same logic here, t of S2n naught is equals to 2n naught t of S1. Applying the same property here, Here you can write like this: T of Sn naught minus y naught, T of Sn naught minus y naught is subset to T of S2n naught, which is clearly subset to 2n naught T of S1. Let it be equation number 4. Again, since this f is a homeomorphism, this f is a homeomorphism which is both continuous 1 onto and open mapping homeomorphism, then f of t of Sn naught bar is equals to f of t of Sn naught whole bar. Oh, because of f of a bar is equals to f of a whole bar by applying this axiom. So this condition implies as t of Sn naught bar minus y naught is equals to t of Sn naught minus y naught whole bar, which is subset to 2n naught t of S1 bar. Let it be equation number 5. But origin O is an interior point. But remember that this origin O is an interior point. Origin O is an interior point of T of Sn naught minus y naught. This condition implies as origin is an interior point. Origin is an interior point of 2n naught T of S1. Tn naught T of S1. So origin is an interior point of 2n naught and S1 means clearly this origin is an interior point. This origin is an interior point of T of S1. T of S1. Hence, there exists an open sphere. Hence, there exists an open sphere of radius epsilon. Hence, there exists an open sphere of radius epsilon greater than 0, centered at origin. Centered at origin. Centered at origin in B dash. Centered at origin in B dash. In B dash. Contained in T of S1 bar. Contained in T of S1 bar. Contained in T of S1 bar. Which implies as S epsilon dash is subset to T of S1 bar. S epsilon dash is subset to T of S1 bar. Let it be equation number 1. Now complete the proof by showing that. We complete the proof by showing that S epsilon dash is subset or equivalent to T of S1. Remember that. So finally, if we show that this one, there must be an open sphere in B dash containing an open sphere in B. So remember that. So to complete this proof, let us take an element y. Let y be an arbitrary point of S epsilon dash such that norm y is less than epsilon. We take an element y which is arbitrarily chosen from an open sphere S epsilon dash with the property norm y is less than epsilon. Since S epsilon dash is subset or equivalent to T of S1 bar, which implies as y belongs to T of S1 bar. Y belongs to T of S1 bar means y is an adherent point. Y is an adherent point of T of S1. Don't confuse. Adherent means limit point of T of S1. Y is limit point of T of S1. If y is limit point of T of S1, then there exists a vector. Y1 belongs to T of S1. Then there exists a vector y1 belongs to T of S1 satisfying the condition norm y minus y1 is less than epsilon by 2. but remember, this y1 is taken from t of s1, which implies as y1 is equals to t of x1 for some x1 belongs to s1, because t is onto, so that it satisfies the condition norm x1 is less than 1. Again we observe from this equation number 6. I don't write equation number 6. Actually, this is not equation 1. I'm very sorry here. This is equation number 6, I think. Yes. S epsilon dash is a subset to T of S1 bar. Again from that equation number 6. Again that from equation number 6. We observe that S epsilon by 2 dash is subset to T of S1 by 2 bar. And since norm y minus y1 is less than or equals to epsilon by 2, this condition implies as y minus y1 belongs to s epsilon by 2 dash, which is subset to t of s1 by 2 bar. So similarly, there exists a constant. Similarly, there exists 1 by 2 belongs to t of s1 by 2, satisfying the condition norm y minus y1 minus y2 is less than epsilon by 2 square, where y2 is equals to t of x2 with the property norm x2 is less than 1 by 2. By continuing this process, we obtain a sequence. Xn in capital B such that norm xn is less than 1 by 2 power n minus 1. And also norm y minus y1 plus y2 plus and so on plus yn is less than 1 by 2 power n. Let it be equation number 7, where again this yn is equals to t of xn with the property norm xn is less than or equals to 1. If we put Sn is equals to x1 plus x2 plus and so on plus xn, then obviously it follows that norm Sn is equals to norm x1 plus norm x2 plus and so on plus norm xn. I'm very sorry. Norm Sn means you have to apply the whole norm to whole the sequence and so on. This one norm x1 plus x2 plus and so on plus xn. Let us split the norm. If you split the norm, you get norm x1 plus norm x2 plus and so on plus norm xn. Norm, this is nothing but this is less than or equals to 1. This is nothing but 1 by 2. The next term is 1 by 2 square plus and so on plus 1 by 2 power n minus 1. So this is whole less than 2. Obviously this is less than 2 by using geometric progression. Therefore we conclude that norm Sn is less than 2. For any n greater than m, norm Sn minus Sm is equals to norm xm plus 1 plus xm plus 2 plus and so on plus xn, which is less than or equals to norm xm plus 1 plus norm xm plus 2 plus and so on plus norm xn. These are simple calculations, you go through with it, which is less than or equals to 1 by 2 power m plus 1 by 2 power m plus 1 plus and so on 1 by 2 power n minus 1, which is less than 1 by 2 power m into 1 minus 1 by 2 power n minus 1. This is nothing but the sum of the geometric progression with common ratio r is equals to 1 by 2. So 1 minus 1 by 2, which is less than 1 by 2 power m minus 1 minus 1 by 2 power n minus 1. This tends to 0 as both m comma n tends to 0. What it means, norm Sn minus Sm tends to 0 as m comma n tends to infinity. This is infinity. This tends to 0 as m comma n tends to infinity. So right, this condition shows us the sequence Sn is a Cauchy sequence. The sequence Sn is a Cauchy sequence in capital B. It is a Cauchy sequence in capital B. And what is B? B is complete. B is a Banach space, so it is complete. In every Cauchy sequence in a Banach space is convergent. This shows us limit n tends to infinity Sn is equals to x. Means the sequence Sn converges to x. This shows us norm x is equals to norm limit n tends to infinity Sn, which is equals to limit n tends to infinity norm Sn. Norm Sn is less than or equals to 2. So this is less than or equals to 2, less than 3. So you observe that norm x is less than 3. For all x belongs to S3, because of it is less than 3, I write S3. Therefore, now calculate T of x. T of x is equals to T of limit n tends to infinity Sn, which is equals to limit n tends to infinity T of Sn, which is equals to limit n tends to infinity T of Sn means y1 plus y2 plus and so on plus yn. So which is equals to y, Therefore t of x is equals to y, where norm x is less than 3. This condition applies as y belongs to T of S3. Therefore y belongs to S epsilon dash implies as y belongs to T of S3. This condition shows us S epsilon dash is subset to T of S3. S epsilon dash is subset to T of S3. So we conclude that here the image of each open sphere, centered at origin in capital B contains an open sphere centered at origin in B dash. This completes the proof of the theorem. In the next video, we learn one very important theorem, which is known as open mapping theorem. And that open mapping theorem is entirely depends upon this theorem. So this is the base for the open mapping theorem, and one of the lengthiest theorem, and there is lot of derivation involved in this theorem. Keep learning, try to write the notes, then it will be more easy to understand. Keep learning. Wish you all the best. Hi, welcome to Sunil Maths tutorial, functional analysis, class number 21. In this video, we prove a theorem, open mapping theorem, which is very important theorem. Class number 21. Let us see the statement. If capital B and B dash be two Banach spaces, and if capital T is a continuous linear transformation from B on to B dash, then capital T is an open mapping. Okay, we prove this theorem. Let B and B dash be any two Banach spaces. Let capital B and B dash be two Banach spaces. And capital T maps B into B dash is a continuous linear transformation and onto. It is continuous linear transformation and onto also. we have to prove that capital T is an open mapping. Capital T is an open mapping. That is, to prove that capital T is open mapping, we prove that T of G is an open set. T of G is an open set in B dash whenever G is open set in B. Whenever G is open set in B. So our aim is to show that T is an open mapping. Our aim is to show that T is an open mapping. Our aim is to show that T is an open mapping. So now it is equivalent to prove that T of G is an open set in B dash whenever G is an open set in capital B. So right, to prove this, let us take Y is an element of T of G. Let Y be an element, of T of G. Then by definition of T, because T is onto, implies as there exists an element X belongs to capital G such that T of X is equals to Y. And since X belongs to capital G and G is open set, it means there exists an open sphere. With center at X, and radius small r, that is SR of X, which is equals to S of X comma R, is subset to capital G. This is nothing but the definition of open set. But we know that there is a fact. We know that this S of X comma R, this open set can be written as X plus SR, where SR is an open sphere, centered at origin. SR is an open sphere centered at origin. Thus, we conclude that X plus SR is subset to G. Let it be equation number 1. It is very clear. X plus SR is subset to G. By previous theorem, you see video number 20. There exists an open sphere, S epsilon dash in G dash, centered at origin, such that S epsilon dash is subset to T of SR. All this is from previous theorem. You must learn previous theorem, or you write the previous theorem statement here, that is explained in video number 20. There exists an open sphere S epsilon dash in G dash, centered at origin, such that S epsilon dash is a subset to T of SR. So right, now we go through with this. S epsilon dash can be written as, add on both the sides, y plus S epsilon dash is subset to y plus T of SR. It can be written as S dash of y comma epsilon, means it is a sphere, it is an open sphere centered at y having radius epsilon, is subset to T of X, because y is equals to T of X plus T of SR, which implies
S dash of s comma epsilon is subset to T of x plus SR because T is a linear transformation, which implies S dash of y comma epsilon, this is not S, y comma epsilon is subset to T of G because T of G is equals to, from this equation number 1, sorry, here, from this S of x comma T of x is equals to y, T of x plus SR is equals to T of G. Where is G? This one. G is x plus SR is subset to G. So T of G. So which implies, remember that I can prove again here, x plus SR is subset to G. Therefore T of x plus SR is subset to T of G. So please remember that. So this condition implies as S dash is an open sphere centered at y having radius epsilon is entirely lies in T of G. Hence, what it means, for each point y, belongs to T of G, for each point y belongs to T of G, there exists an open sphere, in B dash, centered at y, and contained in T of G. This equation means, I write here, this equation S dash of y comma, this equation S dash of y comma epsilon, subset to T of G means for each point y belongs to T of G, there exists an open sphere in B dash centered at y and contained in T of G. This shows us T of G is open. Hence, this completes the mapping capital T is open mapping. The linear transformation is open mapping. Hence proved. This completes the proof of the open mapping theorem. One of the important theorem for examination, in examination point of view. Keep learning. So, and also before going to close the session, I repeat the definition of open mapping. What is mean by open mapping? A mapping is said to be open mapping. Here, T is a linear transformation from B into B dash. So this set is said to be open mapping. If T of G is an open set in B dash, T of G is open set in B dash. Whenever G is open set in B. In other words, G is open in the domain B, implies as T of G is open in B dash. Thus we conclude that capital T is open. This completes the proof of the theorem. One of the very important theorem in functional analysis, open mapping theorem. The question may be like this: state and prove open mapping theorem. Including statement, by had the state. Including statement is important, by had this. In the next video, we prove one more theorem. Keep learning. Wish you all the best. Hi, welcome to Sunil Maths tutorial, functional analysis, class number 22. Let us see one result. Let capital B and B dash be two Banach spaces, capital B and B dash be two Banach spaces, and capital T be a one-to-one continuous linear transformation from capital B on to B dash. Remember that T is 1 continuous and it is also a linear transformation. Then capital T is a homomorphism. Such that T inverse is also continuous linear transformation. It is one of the result. It is direct application of open mapping theorem. What is we learn in previous video, video number 21. So B and B dash are Banach spaces and T be the one and continuous linear transformation of capital B onto B dash. Then T is a homomorphism and T inverse is also continuous. Now we learn one very important definition, projection. We learn one very important definition, projection. A projection P on a Banach space capital B is an idempotent operator which is continuous. So projection P defined on a Banach space is an idempotent operator. It means its domain and codomain is B. It is an idempotent operator means P square is equals to P, and it also that P is continuous. So I said that is P square is equals to P and P is continuous. P square is equals to P and P is continuous. So remember that one of the very important definition, projection. Projection P on a Banach space B is an idempotent operator which is continuous. It means it satisfies two properties, P square is equals to P as well as P is continuous. Remember that it is clearly a linear transformation. Now we learn two more properties of this projection. A projection P defined on a Banach space, a projection P defined on a Banach space determines a projection P defined on a Banach space capital B defined on a Banach space capital B determines two linear subspaces capital M and capital N of capital B such that B is equals to M direct sum N. Remember that where this M is equals to P of X such that X belongs to B. P of X such that X belongs to B means this capital M is range of P. This capital M is range of capital P and capital N is equals to set of those elements which satisfies the condition P of X is equals to 0. Set of those elements X which satisfies the condition P of X is equals to 0, and this is known as null space of P. So every projection P defined on a Banach space capital B determines two linear subspaces capital M and N satisfying the condition B is equals to M direct sum N. Capital B is equals to M direct sum N, where M is the range of the projection and N is the null space of the projection. Remember that. So right, we go for next theorem, and which is very useful theorem for our next coming theorems. Let us see the statement. P is a if P is a projection defined on a Banach space capital B, and if capital M and N are its range and null spaces, then M and N are closed linear subspaces of B such that B is equals to direct sum N. In other words, this direct sum N is nothing but the property of P. You have to show that these M and N are closed subspaces. So we prove this theorem. Let P be a projection. On defined on capital P. P be a projection defined on capital P. That is, P satisfies two properties. P square is equals to P and P is continuous. P square is equals to P and P is continuous. These two are properties of projection. These two conditions are properties of projection, right? And they given that capital M is the range, capital M is the range of P, that is M is equals to set of all elements P of X, set of all images where X belongs to capital B, and capital N is null space of P, null space of P, that is capital N is equals to set of all elements such that which satisfies this condition P of X is equals to 0, P of X is equals to 0. So right, such that by definition of projection capital B is equals to M direct sum N, M direct sum N. Now we can prove that. Now we can prove that capital M and N are closed subspaces. Capital M and N are closed subspaces of capital B. We can prove that capital M and N are closed subspaces of capital B. Right. For this, by definition of null space, by definition of null space, capital N is equals to set of all elements X such that P of X is equals to 0. This is nothing but P inverse of set 0. Obviously, P of X is equals to 0 means this condition implies as X is equals to P inverse of 0. X is equals to P inverse of 0. So, the whole set is denoted by simply P inverse of 0. P inverse of 0. Now, we go for that P is, since that P is projection, that P is projection, it means P is continuous, P is continuous. We know that there is a property, every singleton set in a metric space, every singleton set in a metric space is closed set, is closed. It follows that P inverse of set 0 is closed, P inverse of set 0 is closed subspace of capital B. This implies as capital N is closed subspace of capital B, closed subspace of capital B. I repeat these properties, see here, right? P is a projection, every projection is continuous, every projection is continuous, and we know that every singleton set in a metric space is closed, every singleton set in a metric space is closed. So obviously P inverse of 0 is clear, is also a closed subspace of B because it is singleton set, it consists only 0. So N is also a closed subspace of B. N is also a closed subspace of B. Now it is remaining to prove that M is also closed subspace, right? By definition of capital M, we have M is equals to set of all images P of X such that X belongs to capital B. So which can be written as X such that P of X is equals to X. X such that P of X is equals to X, which can be written as X such that P of X is equals to I of X, where I is idempotent operator, where I is idempotent operator, where I is idempotent operator. Remember that here P of X is equals to idempotent operator. So it can be written as X such that P minus I of X, P minus I of X is equals to 0. P minus I of X is equals to 0. So which is equals to, this condition implies as, so before going to apply one condition, so remember that the capital M is set of those elements which satisfies this condition P minus I of X is equals to 0, which satisfies this condition. So I means I identity operator, not idempotent, I'm sorry. Identity, I is identity operator. I is identity operator, so obviously this I is continuous. This I is continuous. So by this definition M, you conclude that P minus I, P minus I is not P minus I, I'm sorry, every time I'm very sorry for this. So we observe this, please observe this. Capital M is null space of, capital M is null space of the operator, the operator P minus I. M is null space of the operator P minus I. This is important. Already we proved that the null space is a subspace. The null space is a subspace. Here also we prove that M is null space of the operator P minus I. P minus I. And clearly this P minus I is continuous. This P minus I is continuous. It means M is the null space of the continuous operator P minus I. This shows us capital M is closed subspace. Capital M is closed subspace of capital B. That's it. This completes the proof of the theorem. This completes the proof of the theorem. From this theorem, you learn that every projection, if there is a projection P defined on a Banach space capital B, then this projection has two sets. One is range space, the second one is null space, such that the Banach space can be written as some direct sum of M and N, and also these M and N both are closed linear subspaces of capital B. Closed linear subspaces of capital B. Right. In the next theorem, we learn one of the major important property of projections. Keep learning. Wish you all the best. Hi, welcome to Sunil Maths tutorial. Functional analysis class number 23. In this video, we prove a theorem. Let us see the statement. Capital B be a Banach space. M and N are closed linear subspaces of B such that B is equals to M direct sum N. If Z is equals to X plus Y is unique expression for each vector in capital B as the sum of vectors in M and N respectively, then the mapping P defined by P of Z is equals to X is a projection on capital B whose range and null spaces are M and N. Okay, we prove this theorem, one of the lengthiest one. Let us see. Let capital B is a Banach space. Capital B is a Banach space. And capital M comma N are closed linear subspaces of B. Closed linear subspaces of B such that capital B is direct sum of M and N. Capital B is direct sum of M and N. It means each vector Z in capital B can be uniquely expressible as or represented as Z is equals to X plus Y, where that X belongs to capital M and Y belongs to capital N. So right, now define an operator. Define an operator P on capital B as P of Z is equals to X for all Z belongs to capital B, where Z is an expression or unique expression X plus Y
and that x belongs to capital M, y belongs to capital N. We define P of Z is equals to x. So it is very easy to see that. Then we can easily see that P is linear, P is idempotent, P is linear, P is idempotent, except P is continuous. So to prove that P is continuous, we define a new norm. For this, let B dash denotes linear space. Let B dash denotes linear space capital B equipped with new norm defined by norm Z dash is equals to norm x plus norm y. B dash is a linear space, nothing but B equipped together with another norm Z dash is equals to norm x plus norm y. First we show that this norm is well defined. First we show that this norm is well defined. So let us see the first condition of norm definition. Norm Z dash is equals to norm x plus norm y. Right. Suppose if x not equals to 0, implies as norm x greater than 0. Y not equals to 0 implies as norm y greater than 0. Therefore, x plus y not equals to 0 implies norm x plus norm y greater than 0. This is nothing but z not equals to 0 implies norm z dash is greater than 0. Norm z not equals to 0 implies norm z dash is greater than 0. That's it. You see, further, norm z dash is equals to 0 if and only if norm x is equals to 0 and norm y is equals to 0. If and only if x equals to 0 and y equals to 0. If and only if x plus y is equals to 0. Therefore, norm z dash is equals to 0 implies and implied by x plus y is equals to 0. Right. From these two conditions, the first property of norm is well defined. We go for second property. To prove the second property, let us take two elements. Let z is equals to x plus y, s is equals to p plus q, where x comma p belongs to capital M, y comma q belongs to capital N. Then z plus s is equals to, then what is z plus s? It is very simple, x plus p plus y plus q. Now norm z plus s dash is equals to norm x plus p plus norm y plus q, which is less than or equals to norm x plus norm p plus norm y plus norm q, which is less than or equals to norm x plus norm y. I'm separating the elements, plus norm p plus norm q. This is nothing but norm z dash plus norm s dash. This is nothing but the second property of norm. This is nothing but the second property of the norm. Therefore, norm z plus s whole dash is less than or equals to norm z dash plus norm s dash. We prove two properties of norm. We go for third property of the norm. Let z is equals to x plus y, where x belongs to capital M and y belongs to capital N. Take a scalar alpha belongs to the field capital F such that alpha z is equals to alpha into x plus y. Now norm alpha z dash is equals to norm alpha x plus norm alpha y, which is equals to mod alpha into norm x plus mod alpha into norm y, which is equals to mod alpha into norm x plus norm y, which is equals to mod alpha into norm z dash. So this is nothing but third property of norm alpha z dash is equals to mod alpha into norm z dash for some scalar alpha. From these three conditions, this is condition number 3, here it is condition number 2, here it is condition number 2, and these two together with condition number 1. From these three conditions, we conclude that the norm defined as norm z dash is equals to norm x plus norm y is actually a norm or well-defined norm. So B dash is a Banach space together with this norm. B dash is a linear space together with this norm. I said that B dash, here it is. B dash denotes a linear space equipped with new norm. So right. Now we show that this new norm. Now we show that this B is a Banach. This B dash is a Banach space. Next we show that B dash is a Banach space. B dash is a Banach space. Next we show that B dash is a Banach space together with this norm with respect to this norm Z dash. So right, to prove that it is a Banach space, it is equivalent to show that it is complete. So we have to prove that B dash is complete. We have to prove that B dash is complete. So to prove that B dash is complete, let us take a Cauchy sequence in B dash. Let Zn be a Cauchy sequence. Let Zn be a Cauchy sequence in B dash, which implies for given epsilon greater than 0, there exists a positive integer. Small n naught such that m comma n greater than or equals to n naught implies norm zm minus zn dash is less than epsilon. So right, so that is norm zm minus zn dash is less than epsilon, where remember that B dash is also equivalent to direct sum of m plus n. So this is nothing but this Zm can be written as xm plus ym minus Zn can be written as xn plus yn whole dash is less than epsilon. This can be written as norm xm minus xn plus ym minus yn whole dash is less than epsilon. Now split the norm. Norm xm minus xn plus norm ym minus yn is less than epsilon. This is clearly equivalent to norm xm minus xn is less than epsilon by 2, norm ym minus yn is less than epsilon by 2. So this condition shows us the sequence xn and the sequence yn are Cauchy sequences. These sequences are Cauchy sequences in capital M and N respectively. They are Cauchy sequences in M and N respectively. And already we know that these M and N are closed subspaces. Since capital M comma N are closed subspaces, these are closed subspaces of the Banach space B, of the Banach space capital B. It means these sequences xn and xm yn, xn and yn are Cauchy sequences, in capital B, and capital B is complete normed linear space. So this shows us we know that complete means every Cauchy sequence in it is convergent. Therefore the sequence xn converges to x, which belongs to capital M, and the sequence yn converges to y, which belongs to capital N. It means that is there exist positive integers n1 comma n2 such that norm xn minus x is less than epsilon by 2 for all n greater than or equals to n1. Norm yn minus y is less than epsilon by 2 for all n greater than or equals to n2. Now define another one. Now define small n is equals to maximum of n1 comma n2 which is equals to n3. Say we have norm xn minus x is less than epsilon by 2, norm yn minus y is less than epsilon by 2 for all n greater than or equals to this n3, for all n greater than or equals to n3. Here define maximum of n1 comma n2 is n3, not n. So applying this condition to previous, here applying that condition here, we can conclude like this. Norm zn minus z whole dash is equals to norm xn plus yn minus x plus y which is less than or equals to norm xn minus x plus norm yn minus y which is less than epsilon by 2 plus epsilon by 2 is equals to epsilon. Therefore norm zn minus z dash is less than epsilon for all n greater than or equals to n3, a positive integer. This condition shows us the sequence Zn converges to Z in B dash as n tends to infinity. This shows us the Cauchy sequence in B dash is convergent. The Cauchy sequence in B dash is convergent. It means B dash is complete. It means B dash is a Banach space. That's it. Now to show that P is continuous, Let us see. We have to show that P is continuous. Actually, our main aim is also to show that P is continuous. We develop all these conjecture to define the continuous linear transformation. Right. Now, to show that P is continuous, from B into B dash, that P of Z is equals to X, norm P of Z is equals to norm X, which is less than or equals to norm X plus norm Y. I add the Y, so this equality becomes inequality, which is less than or equals to norm Z dash. Therefore, norm P of Z is less than or equals to norm Z dash. So this is the cause we define here norm Z is equals to norm X plus norm Y. That's why we prove that this norm Z dash is a well-defined norm. Here we use for a simple one. Here we use this norm Z dash to prove that P of Z is bounded. But the main aim is that new norm is well-defined. This norm condition implies as P of Z is bounded. P of Z is bounded. It means P is continuous. P is continuous. From P is continuous from where to where? B into B dash. B into B dash. Which is also idempotent. It is very simple. Therefore, P is a projection. Right. Now we have to prove that B dash and B have same topology. We have to prove that this B and B dash have same topology. This B and B dash have same topology. Suppose if capital T denotes the identity mapping, if capital T denotes the identity mapping of B dash onto B, then norm T of Z is equals to norm Z, which is equals to norm X plus Y, which is less than or equals to norm X plus norm Y, which is less than or equals to norm Z dash. Therefore, we conclude that norm T of Z is less than or equals to norm Z dash. This condition is true for all Z. So, from this we conclude that capital T is bounded as well as it is continuous. That T is continuous from B dash to B. From B dash to B. This is right. From B dash to B. Therefore, we conclude that capital T is a homeomorphism. Not homomorphism, homeomorphism. Because it is a 1-1 continuous and open mapping also. Homeomorphism. Therefore, B and B dash have same topology. This completes our theorem. Hence proved. So one of the lengthiest theorem, we prove this theorem in different stages. So one of the lengthiest one, be careful and write the notes and practice it once, then it is very easy to understand. Keep learning. Wish you all the best. Hi, welcome to Sunil Maths tutorial, functional analysis, class number 24. In this video, we learn 2 definitions and 1 theorem. Let us see the first definition. A graph of a mapping. We define graph for the mapping. Let us take x and y be to any non-empty sets. Let capital X comma y be to non-empty sets. Both are non-empty sets. And f is a mapping from x into y. F is a mapping from x into y with the domain x, with the domain capital X, and range in y. It means the range of this function is subset to y. Obviously, it is subset to y. Then the graph of f, the graph of this mapping f is defined as x cross y, means Cartesian product of x and y. Cartesian product of x and y, which consists of all ordered pairs, which consists of all ordered pairs of the form x comma f of x. It means graph of f is equals to set of all ordered pairs x comma f of x such that this x belongs to capital X and f of x belongs to capital Y. And this set is subset to or equivalent to, either subset to or equivalent to the Cartesian product of x and y. This is known as the graph of the function. So graph of f is equals to set of all ordered pairs x comma f of x such that where x belongs to capital X and f of x belongs to capital Y, such that the set is completely subset to the Cartesian product of f and y. And the graph of f is denoted by fg, is denoted by simple symbol f suffix small g. The graph of g is denoted by fg. Right. We go for a simple note point. One of the important note point to remember. Right. Suppose n and n dash be two normed linear spaces. Capital N and n dash be normed linear spaces. N and n dash be normed linear spaces. Then the Cartesian product n cross n dash, is also a normed linear space, with coordinate wise linear operations. Remember that, coordinate wise linear operations. And the norm is defined by norm x comma y is equals to norm x plus norm y. So norm x plus norm y. So with respect to this norm, this Cartesian product n cross n dash is also a normed linear spaces. Moreover, this norm induces the product topology. This norm induces the product topology on n cross n, the product topology on n cross n dash, yes, n cross n dash. And also further, you remember one point here, this n cross n dash is complete. This n cross n dash is complete, implies and implied by both n and n dash are complete. N and n dash are complete. Important note point to remember, and which is useful to prove some theorems in the next videos. So right, we go for next definition. Closed linear transformation. Closed linear transformation, right. Let us take capital N and N dash be two normed linear spaces. Be two normed linear spaces. And capital D is a subspace of N. Capital D is a subspace of capital N. And capital T that maps from D into N is a linear transformation. So here N and N dash be two normed linear spaces. D is a subspace of N. Capital T is a linear transformation from D into N. Now this T is said to be closed. This T is said to be closed. T is closed, implies and implied by, for each xn belongs to capital D and xn converges to x, and t of xn converges to y, implies t of xn converges to y implies x belongs to D and t of x is equals to y. X belongs to D and t of x is equals to y. So the mapping or the linear transformation T is said to be closed if it satisfies this condition. For each sequence xn belongs to T which converges to x, such and t of xn converges to y, implies as that x belongs to capital D as well as t of x is equals to y. So according to linear transformation is said to be closed, it is one of the condition for that. So next we prove a theorem. Let us see the statement. N and n dash be two normed linear spaces and D is a subspace of N. Then the linear transformation T that maps from D into n dash is said to be closed if and only if it satisfies the condition xn belongs to D and xn converges to x, t of xn converges to y, implies x belongs to D and y is equals to t of x. And y is equals to t of x. I'm sorry, this is I read the statement wrongly. Let us check it. T is said to be closed if and only if the graph of T is just a minute. The graph of T is closed. Here the if and only if condition is different. If and only if the graph of T is closed. The graph of T is closed. Remember that. The mapping T that maps D into N is closed if and only if the graph of T is closed. The graph of T is closed. So I rewrite the statement. This is the correct statement. Please observe that. So I repeat the statement. N and n dash be normed linear spaces. D is a subspace of N. Then a linear transformation T maps D into n dash is said to be closed if and only if it satisfies the condition the graph of T is closed. The graph of T is closed. Let us prove our statement. I write the introduction. capital N and N dash B to normed linear spaces, to normed linear spaces, and D is a subspace of N. D is a subspace of capital N, and capital T maps D into N dash is also is a linear transformation, is a linear transformation. We have to prove that, we have to prove that capital T is closed, capital T is closed, implies and implied by, implies and implied by its graph, its graph TG, its graph TG is closed, its graph TG is closed. Our theorem is this one. So understand this. N and N dash B to normed linear spaces. D is a subspace of N, and T maps D into N dash is a linear transformation. Our aim is to show that T is closed, implies and implied by its graph TG is also closed set. So let us start. We assume that closed, T is closed. Suppose the linear transformation capital T is closed. We have to prove that, TG is closed. We have to prove that TG is closed. That is, TG contains all its limit points, all its limit points. It is very well known definition. Any set is said to be a closed set if it consists all of its limit points, all of its limit points. So to prove this, let us take a limit point. Let x comma y be any limit point, let x comma y be any limit point of Tg. Then by the definition of limit point, there exists a sequence of points, there exists a sequence of points in Tg, there exists a sequence of points in Tg, that is, that points xn comma t of xn in Tg, xn comma t of xn, where this xn belongs to T, converging to x comma y, converging to x comma y. You understand this point, x comma y be any limit point of Tg, then there must be a sequence of points in Tg, that is xn comma t of xn, where xn belongs to T, converges to x comma y, converges to x comma y. So that is what it means, the sequence of points xn comma t of xn, xn comma t of xn converges to x comma y, converges to x comma y, which implies norm xn comma t of xn, norm xn comma t of xn minus norm xn comma t of xn minus x comma y converges to 0, tends to 0 or converges to 0, which implies as norm xn minus x, norm xn minus x, comma t of xn minus t of y, t of xn minus t of y converges to 0. So which implies as norm xn minus x converges to 0, norm t of xn minus t of y converges to 0. Both are converges to 0 because T is closed. Because T is closed. This condition implies as xn converges to x and T of xn converges to y. Oh, there is a small correction. Here, this is not T of y. This is y only. This is y only. Remember that. This is y only. T of xn converges to y. So right, T of xn converges to y. So this means by the definition of closedness of D, closedness of T, we get this x belongs to capital D, this x belongs to capital D, and T of x is equals to y. This happens from T is closed. T is closed. Already we learned here. by the definition of closed linear transformation. So right, what happens now? X belongs to D and T of X is equals to Y. This condition implies as the ordered pair X comma Y belongs to the graph TG. Belongs to the graph TG. So this condition implies as every limit point, every limit point of TG, every limit point of TG, every limit point of TG lies in TG, entirely lies in TG. This shows us the graph TG is closed. The graph TG is closed graph. That's it. This is the first part. So we assume that T is closed, we prove that TG is closed. The converse. Let us take the opposite parts. Assume that suppose the graph of T is closed. That is, the graph TG is closed. TG is closed. We have to prove that capital T is closed. We have to prove that capital T is closed. So right, to show that T is closed, let us take a sequence of points xn belongs to capital D, comma, xn converges to x, and T of xn tends to y. T of xn tends to y. It is very easy to see that the point, I'm sorry, this is very easy to see that it is easy to see that the point x comma y is an adherent point, adherent means limit point, is an adherent point of TG, so that the point x comma y belongs to TG because TG is closed, since TG is closed, by definition of TG, by the definition of closedness, by the definition of TG, where we have x belongs to T and y is equals to T of x, because TG is closed, there must be a sequence converging to satisfying all those conditions. X belongs to T and y is equals to T of x. What is this? This condition implies us, that is, this condition, what is this condition? Where xn belongs to D and xn converges to x and T of xn converges to y, then we have x belongs to D and y is equals to T of x. This is nothing but closedness of T. Therefore, T is a closed linear transformation. Hence, capital T is closed implies and implied by its graph TG is also closed. This completes the proof of our theorem. Observe that in the next class, we learn one very important theorem which is known as the closed graph theorem. Keep learning. Wish you all the best. Hi, welcome to Sunil Maths tutorial, functional analysis, class number 25. In this video, we prove closed graph theorem, one of the very important theorem in functional analysis. Let us see the statement of closed graph theorem. If capital B and B dash are two Banach spaces, and if capital T is a linear transformation from B into B dash, then T is continuous if and only if its graph is closed. So we prove this theorem, and one of the very important theorem. Let us see. Let capital B and B dash are two Banach spaces, and T maps B into B dash is a linear transformation. We have to prove that capital T is continuous. Capital T is continuous implies and implied by its graph Tg is closed. Tg means the graph of T. Tg means the graph of T. So first we assume that T is continuous. Suppose capital T is continuous. The linear transformation is continuous. We have to prove that the graph Tg is closed. That graph Tg is closed. It is enough to show that Tg is equals to Tg bar, closure of Tg. It is enough to show that Tg is equals to Tg bar. So right, by definition always, since we know that it is true always, Tg is subset to Tg bar. Closure is always subset to set. Let it be equation number 1. Now we prove the converse of equation 1, reverse of equation number 1. For this, to prove this, let us take an element x comma y belongs to Tg. X comma y belongs to Tg. Tg bar. Let us take x comma y belongs to Tg bar. What it means? X comma y belongs to Tg bar means the point x comma y is a limit point. The point x comma y is a limit point of the graph Tg. So if it is a limit point of the graph Tg, it means there exists a sequence of terms xn comma t of xn in Tg such that it satisfies one condition. The sequence xn comma t of xn converges to x comma y. This is from definition of continuity. What it means? The sequence xn converges to x and the t of xn tends to y. But t is continuous. This t is continuous. Whenever this t is continuous, we have xn converges to x implies t of xn converges to t of x. T of xn converges to t of x. Therefore, we conclude that y is equals to t of x. If y is equals to t of x, this shows us the point x comma y is equals to x comma t of x. Obviously, x comma t of x is the ordered pair which belongs to the graph Tg. Therefore, we conclude that the point x comma y belongs to Tg bar implies the point x comma y belongs to Tg. This shows us Tg bar is subset to Tg. The closure of Tg is subset to Tg. Equation number 2. Let us see equation 1. Tg is subset to Tg bar. See equation number 2. Tg bar is subset to Tg. From equations 1 and 2 we conclude that. From equations 1 and 2 we have Tg is equals to Tg bar. Tg is equals to Tg bar. The graph of T, closure of graph of T is equivalent to graph of T, which implies as Tg is closed. Therefore, the graph of linear transformation, the graph of T is closed. So we assume that T is continuous. We prove that Tg is its graph is closed. Now we prove the reverse part. Now assume that Tg is closed. We have to prove that capital T is continuous. So right, let us continue. We denote the linear space B by B1 sorry, we denote the linear space, we denote the linear space B by B1 renormed means we are introducing another norm, renormed by norm x1 is equals to norm x plus norm t of x. Obviously norm t of x is less than or equals to norm x plus norm t of x. Obviously norm t of x is less than or equals to norm x plus norm t of x, which is less than or equals to norm x1, which is less than or equals to norm x1. So we conclude that norm t of x is less than or equals to norm x1 means this t is bounded. This linear transformation capital T is bounded. Consequently continuous, which implies T is continuous as a mapping, continuous as a mapping of B1 into B dash. This is the here restriction here. T is continuous as a mapping of B1 into B dash, not B. T is continuous as a mapping of B1 into B dash. Now it is sufficient to show that. Now it is sufficient to show that. B and B1 have same topology. B and B1 have same topology. So we have to prove that they have same topology. That is, they are homomorphic. To prove this, consider a mapping. Capital I that maps from B1 into B such that I of x is equals to x for all x belongs to B1. By definition, this I is identity mapping. Obviously, this I is, every identity mapping is 1, 1 and onto. So, this I is also onto. Further, we calculate its norm. Norm I of x is equals to norm x. This norm x less than or equals to norm x plus norm t of x. And this norm x plus norm t of x is less than or equals to norm x1 because it is equivalent to norm x1. Therefore, norm I of x is less than or equals to norm x1. This condition shows us I is bounded. Obviously, this I is continuous. Every bounded linear transformation is continuous. So, I is continuous. So, if we can show that, another part, if we can show that B1 is complete, then by previous theorem, I note that theorem here. Then by previous theorem, let capital B and B dash be Banach spaces and capital T maps B into B dash is 1, 1 and continuous linear transformation of capital B into B dash of capital B onto, not into, onto B dash. Then capital T is a homomorphism. So if we show that B1 is complete, then by using this theorem, our aim is complete. It means I becomes a homomorphism. Capital I, this mapping I is homomorphism. So to prove that B1 is complete, let us take a Cauchy sequence in it. Let us take a Cauchy sequence in it. Let xn be a Cauchy sequence. Let xn be a Cauchy sequence in B1 such that norm xn minus xm tends to 0 as m comma n tends to 0 infinity. Norm xn minus xm tends to 0 as n comma n tends to infinity, which implies as norm xn minus xm plus norm t of xn minus xm tends to 0 as m comma n tends to infinity. So this condition implies as norm xn minus xm plus norm t of xn minus t of xm tends to 0 as m comma n tends to infinity, which implies norm xn minus t of xn plus norm xm minus t of xm tends to 0 as m comma n tends to infinity. This shows us the sequence xn is a Cauchy sequence. Xn is a Cauchy sequence in B and t of xn is a Cauchy sequence in B dash. But remember that both B and B dash are complete. Both B and B dash are Banach spaces. It means they are complete normed linear spaces. They are complete normed linear spaces. Since B and B dash are complete, this shows us the sequence xn converges to x in B and the sequence t of xn converges to y in B dash. So already we assume that the graph of tg is closed. The graph of t is closed. This shows us the ordered pair x comma y belongs to tg. The ordered pair x comma y belongs to tg implies as y is equals to t of x. Now norm xn minus x1 is equals to norm xn minus x plus norm t of xn minus x, which is equals to norm xn minus x plus norm t of xn minus t of x, which is equals to norm xn minus x plus norm t of xn minus y. This condition implies as xn converges to x, this gives 0, and t of xn converges to y, this gives 0 as n tends to infinity. It follows that this condition shows us the sequence xn in B1 is convergent. The sequence xn in B1 is convergent and converges to x belongs to B1. This shows us therefore B1 is complete. If B1 is complete, then by this previous theorem, B and B dash are Banach spaces. T maps B into B dash is 1 1 and continuous linear transformation of B onto B dash. Then T is a homomorphism. By applying this theorem, we conclude that our mapping capital I is a homomorphism. If our mapping capital I is a homomorphism, then we conclude that B and B1 have same topology. B and B1 have same topology. That is the required one. If B and B1 have same topology, then obviously the mapping capital T is continuous. This completes the proof of the closed graph theorem, which is very important in exam point of view. Let us see, I prove the same theorem in another method also in another video. So keep learning. Wish you all the best. And one of the very important theorem, closed graph theorem. Any linear transformation is continuous if and only if the graph of its linear transformation is a closed set. Keep learning.
Hi, welcome to Sunil Maths tutorial. Functional analysis class number 26. In this video, we prove a theorem, uniform boundedness theorem. It is also known as uniform bounded principle. One of the very important theorem in functional analysis. Let us say the statement of this theorem. Capital B be a Banach space and N be a normed linear space. If set Ti, collection Ti or set of Ti is a non-empty set of bounded continuous linear transformations from capital B into N, having the property that the set Ti of X is bounded subset of capital N for each vector X in capital B. Then set of norm Ti is a bounded set of numbers, that is Ti is bounded as a subset of script B of B comma N. One of the very important theorem. Let us see the proof. Let capital B be a Banach space. Let capital B be a Banach space and capital N be a normed linear space. Capital N be a normed linear space. And set Ti be the set of all continuous linear transformations of capital B into capital N. Set Ti be the set of all continuous linear transformations which are defined from capital B into capital N. Right. Now for any positive integer small n, let us define. For any positive integer small n, define a set capital Fn is equals to set of those elements x such that x belongs to capital B and norm Ti of x is less than or equals to n for all I. Let it be equation number 1. For any natural number small n belongs to capital N, define a set Fn, the set of those elements x which belongs to the Banach space capital B, satisfying the condition norm Ti of x is equals to x for all I. Let it be equation number 1. First we show that this Fn is a closed subset of B. First, we show that this Fn is a closed subset. Of capital B. First, we show that this Fn is a closed subset of B. So, right, take an element small x belongs to Fn. Take an element x belongs to Fn. So, x belongs to Fn means which implies and implied by it satisfies the condition norm Ti of x is less than or equals to n for all I, which implies and implied by Ti of x belongs to some open sphere Sn power 0 for all I, where what is this Sn power 0? Sn power 0 is a closed sphere centered at origin O and radius n.
Remember this symbol, Sn power 0 is the closed sphere centered at origin having radius small n. And this sphere entirely, this Sn power 0 is entirely lies in capital N. Entirely lies in capital N. So which is again implies and implied by, I mean Ti of x, this one, Sn power 0, I mean this one, Ti of x belongs to Sn power 0 implies and implied by x belongs to Ti power minus 1 of Sn power 0, inverse of t, again which is implies and implied by, this is true for all I, implies and implied by x belongs to intersection I is equals to intersection over I means for all arbitrary elements, intersection over I Ti inverse of Sn0, Sn0 for all I. So this shows us that set Fn is equals to intersection over I Ti inverse of Sn0, which is closed, being intersection of closed sets. This is nothing but intersection of closed sets, obviously intersection of closed sets is closed, therefore the set Fn is closed. Our first aim is that is, so first we show that Fn is closed subset of B, so obviously this Fn is closed. Since again, now we continue. Further we can write, we can write Fn, I mean capital B is equals to union n is equals to 1 to infinity Fn, union n is equals to 1 to infinity Fn. Suppose if this B not equals to union n is equals to 1 to infinity Fn, it means there exists some x belongs to capital B such that x does not belongs to Fn for any n. If you assume that this point, B not equals to union Fn, then there must be an element x belongs to B that does not belongs to Fn. This condition implies norm Ti of x is greater than n. Norm Ti of x is greater than n for that x belongs to capital B. This is a contradiction. This is a contradiction to the fact. What is the fact? To that Ti of x is bounded. But we show that norm Ti of x is greater than n. So this is a contradiction. This contradiction exists because of our assumption B not equals to union n is equals to 1 to infinity. Hence we conclude that B must be equivalent to union n is equals to 1 to infinity Fn. B is equals to union of all closed sets. Right. That is the complete space capital B, is the union of sequence of its closed subsets. That is, capital B is the complete space B is the union of the sequence of its closed subsets. Now by applying Baire category theorem, there exists an integer n naught such that Fn naught bar has non-empty interior. has non-empty interior. This is from Berry category theorem. Because the space capital B can be written as a union of sequence of closed subsets of itself. Therefore, by applying Berry category theorem, for any there exists a positive integer n naught satisfying the condition f n naught bar has non-empty interior. Non-empty interior. Right. Again since fn naught is closed, fn naught is closed set, it means fn naught bar is equals to fn naught, fn naught bar is equals to fn naught, and this fn naught bar has non-empty interior, implies as fn naught has non-empty interior, fn naught has non-empty interior. If Fn naught has non-empty interior, if any set has non-empty interior, then there exists some x naught belongs to Fn naught such that this Fn naught is a neighborhood of that point x naught. Non-empty interior. Non-empty interior means there must be a point x naught belongs to Fn naught such that Fn naught is a neighborhood of x naught. That Fn naught is a neighborhood of x naught. Again, since Fn naught is closed, there exists a closed sphere. S is equals to x belongs to capital B such that norm x minus x naught is less than or equals to R naught, which is subset to Fn naught. Let it be equation number 2. Right. Now we are assuming that if norm y less than or equals to 1, then norm ti of y is equals to norm ti of z by r naught, where z is equals to r naught into y, You can write this r naught as like this, small r naught. So which is equals to again 1 by r naught norm ti of z. It can be written as 1 by r naught norm ti of z plus x naught minus x naught, which is equals to 1 by r naught norm ti of z plus x naught plus norm ti of x naught. This 1 by r naught is multiple for both the terms, which is clearly less than or equals to. Here one more step. You can write this step also like this. 1 by r naught norm ti of z plus x naught minus ti of x naught by the definition of linear transformation. So which is again, so from this condition you can write like this. You can write directly, no worries, which is less than or equals to 1 by r naught into n naught plus n naught. This is clearly less than or equals to 2n naught by r naught. Therefore, what is in the left side? Ti of y. Therefore, we conclude that norm Ti of y is less than or equals to 2n naught by r naught if norm y less than or equals to 1. Therefore, norm Ti is equals to supremum of norm Ti of y such that norm y less than or equals to 1, which is clearly less than or equals to 2n naught by r naught. It follows that the set norm Ti is a bounded set of numbers. Because norm is always positive number. It gives a positive number, and it is always less than or equals to 2n naught by r naught. So this norm ti, set of norm ti is a bounded set of numbers. This completes the proof, hence proved. This completes the proof of the uniform boundedness theorem. This is our main aim also. So we have to prove that the set ti is a bounded set as a subset of script b of n, and norm set of all norm ti is a bounded set of numbers. State and prove uniform boundedness theorem. The question may be like this in your examination. In your examination, the question may be like this: state and prove uniform bounded theorem or uniform boundedness theorem. So very, very important theorem. Keep learning. Hi, welcome to Sunil Maths tutorial, functional analysis, class number 27. In this video, we learn a theorem and one problem. Let us see the statement of the theorem. A non-empty set capital X of a normed linear space capital N is bounded, implies and implied by f of x is a bounded set of numbers for each f in conjugate space n star. So let us see the proof. Let capital N be a normed linear space and capital X is a non-empty subset of n. Capital X is a non-empty subset of n. That is, capital X is subset to n and this x is not equals to pi, non-empty set. So we have to prove that capital X is bounded, capital X is bounded, implies and implied by f of x is a bounded set of numbers. F of x is a bounded set of numbers for each f, in the conjugate space n star. So part 1, suppose assume that f is bounded. Suppose capital X is bounded. Suppose capital X is bounded subset of n. Subset of n. By the definition of bounded subset, there exists a positive constant. There exists a positive constant k1 such that norm x is less than or equals to k1 for all x belongs to capital X. Let it be equation number 1. This is nothing but the definition of bounded subset. Suppose capital X is a bounded set, then there exists a positive constant k1 satisfying the condition norm x less than or equals to 1 for all the elements x belongs to capital X. Let it be equation number 1. Now we can show that f of x is bounded. F of x is bounded since f belongs to n star. It implies f is a functional. F is a functional. Conjugate means it is a functional space. So f is a functional. F is a functional means every functional is bounded. Therefore f is bounded. F is bounded means there exists another constant k2 such that mod f of x is less than or equals to k2 into norm x for all x belongs to capital X. Let it be equation number 2. This is also from the definition of functional. Now from equation 1 and 2 we conclude that, you see, let it equation 1 and equation 2. So from these two equations, from equation 1 and equation 2, we conclude that mod f of x less than or equals to k1 into k2 for all x belongs to capital X. Suppose this k1 into k2 treated as
some constant r, where mod f of x less than small r for all x belongs to capital K, for all x belongs to capital X, in both the places, for all x belongs to capital X. For all x belongs to capital X in both the places. This condition implies as f of capital X is bounded set of numbers for each f belongs to the functional n star conjugate space n star. That's it. This is the first part of our theorem. Let us see what we take and what we prove that. Suppose that capital X is bounded set. I write the bounded set definition here. F of norm x less than or equals to k1 for all x belongs to capital X. Let us, since f belongs to n star, so f is a functional. Every functional is bounded. So again, by the definition of boundedness, there exists another constant k2 satisfying this condition, mod f of x less than or equals to k2 into norm x. Now combining these two, equation 1 and equation 2, we can write mod f of x less than or equals to k1 into k2. Suppose this k1 into k2, the product k1 into k2 is equals to some constant r, then we say that now mod f of x is less than or equals to small r for all x belongs to capital X. This shows us f of x is bounded set of numbers for each functional f belongs to n star. So now we prove the reverse part. Let us assume that f of x is bounded set of numbers. Let us assume that f of x is bounded set of numbers. F of x is bounded set of numbers. Now we can prove that this f of this capital X is bounded. Capital X is bounded. For our convenience, we exhibit the vectors in capital X by simply writing capital X is equals to set of all elements small xi. Consider the natural embedding. That maps from small xi into capital Fxi of capital X into the conjugate space n star. That is Fxi can be defined as Fxi of small f is equals to f of small xi. So by applying this definition, you can write like this: f of capital X is equals to f of xi, small xi, such that each small xi belongs to capital X, which is equals to fxi of f such that each xi belongs to capital X. For each f belongs to conjugate space n star, for each f belongs to conjugate space n star, the function or the set f of x is bounded. This shows us what is this f of x? Collection of fxi of f. Collection of fxi of f is bounded set for each f belongs to n star. Already we know that this conjugate space is complete. N star is complete. It follows from uniform boundedness theorem uniform boundedness theorem. It follows from uniform boundedness theorem. The collection fxi of f, the collection fxi of f is bounded. Bounded subset of n star. It is clearly bounded subset of n star. So this condition implies as norm fxi is bounded. Norm fxi is bounded. If norm fxi is bounded, then the collection norm fxi such that each xi belongs to capital N is bounded set of numbers. Is bounded set of numbers. So you observe that here each xi belongs to capital N. By natural embedding, we know that natural embedding preserves norm properties. Natural embedding preserves the norm properties. This condition implies as norm fxi is equals to norm xi for all xi belongs to capital X. So if you apply this condition here, the collection norm xi such that xi belongs to capital X, which is subset to capital N, is a bounded set of numbers. This is nothing but, this set is nothing but f of capital X is bounded set of numbers for each f belongs to the conjugate space n star. So which is required one? Capital X is a bounded set of numbers. Capital X is a bounded set of numbers. So here this is not f of x, this is not f of x. I mean collection xi means this is the collection of all norms, norm xi such that xi belongs to capital X is bounded set of numbers. For each f belongs to n star. This shows us capital X is bounded set only, not bounded set of numbers. It is only a bounded set. That's it. This completes the proof. Therefore, we prove that capital X is bounded if and only if f of x is a bounded set of numbers. That's it. Here in this video we prove one problem also, and one of the simple one. Let us see. Let capital B be a Banach space, and N be a normed linear space. If Tn, sequence Tn, is a sequence in the collection script B of B, N, such that T of x is equals to limit Tn of x. Exists for each x in capital B. Then prove that capital T is a continuous linear transformation. This is our problem. So they given that capital B be a Banach space, and capital N be a normed linear space, and Tn be a sequence, in script B of B, N, the set of all functionals defined from B to N. And it is defined in a way such that T of x is equals to limit Tn of x. For all x belongs to the Banach space capital B. Our aim is to show that we have to prove that this Tn or this t, both this t, this one, this t is continuous linear transformation. This t is continuous linear transformation. So first we prove that it is linear. To prove that capital T is linear, this is the first side heading. Let us take two vectors. Let x comma y belongs to B and alpha comma beta are any scalars, and x comma y belongs to the Banach space. Now consider T of alpha x plus beta y, T of alpha x plus beta y, which is equals to limit Tn of alpha x plus beta y, limit Tn of alpha x plus beta y, limit n tends to infinity you can take. This can be split. Limit n tends to infinity Tn of alpha x, plus limit n tends to infinity Tn of beta y. Again, these alpha and beta are scalars, so they cannot influenced by the limit alpha into limit n tends to infinity Tn of x plus beta into limit n tends to infinity Tn of y. Again, by the definition, you can write like this: alpha T of x plus beta T of y. In the LHS we have T of alpha x plus beta y. In the RHS we have alpha T of x plus beta T of y. Therefore, we prove that T of alpha x plus beta y is equals to alpha into T of x plus beta into T of y for all x comma y belongs to capital B and alpha comma beta are scalars. They belongs to the field capital R. This condition shows us capital T is a linear transformation. Capital T is a linear transformation. Next, you have to show that this capital T is continuous. This linear transformation is continuous. So by definition we have T of x is equals to limit n tends to infinity Tn of x for all x belongs to capital B. So you observe that this sequence, since Tn of x is continuous, which implies Tn of x is bounded. Every continuous function is bounded. So Tn of x is continuous, so implies as Tn of x is bounded. So by uniform boundedness theorem, by applying uniform boundedness theorem, we have norm Tn of x is also bounded. This is the point. So Tn of x is continuous, obviously it is bounded. By applying uniform boundedness theorem, norm Tn of x is also bounded. Now, what is norm Tn of x? Norm Tn of x is nothing but, so are taking limit on both sides. Limit n tends to infinity, norm Tn of x is equals to norm T of x. So this condition implies as norm Tn of x limit n tends to infinity norm Tn of x is also bounded, in another way I can explain like this. So consider this. Here norm Tn of x is also bounded, implies limit n tends to infinity norm Tn of x is also bounded. This is the point. This is right way. Also bounded. What is this limit? This limit is equivalent to norm T of x. So implies as norm T of x is also bounded because of T of x is equals to limit Tn of x. So norm T of x is equals to limit norm Tn of x. So So you can conclude like this, which implies norm t of x is also bounded. If norm t of x is bounded, then we conclude norm t of x is less than or equals to a, where small a is any constant for all x belongs to capital B. This condition shows us capital T is bounded. It means it is a bounded linear transformation. Every bounded linear transformation is continuous. Therefore, capital T is continuous. This is the second point. Capital T is continuous. Hence, finally, we conclude that capital T is linear. Capital T is linear transformation, as well as it is continuous also. This completes the solution of this problem. In the next video, we solve one more theorem. Keep learning. Wish you all the best.
Hi, welcome to Sunil Maths tutorial. Functional analysis class number 30. In this video, we prove a theorem. Let us see the statement. If capital T is an operator on a normed linear space capital N, then its conjugate T star is an isometric isomorphism defined by T star of f of x is equals to f of T of x is an operator on the conjugate space N star, and the mapping T from to T star is an isometric isomorphism of script B of n into script B of n star, which reverses products and which preserves identity transformation. One of the lengthy theorem, let us prove this one. So, in the initial stage, they given that let capital T be an operator, capital T be an operator on n, and n star be the conjugate of n, n star be the conjugate of n. Now we shall prove that, or we shall show that T star is an operator. T star is an operator. To prove that T star is an operator, it is equivalent to prove that it is a continuous linear transformation. So the first side heading, to show that T star is linear. To prove that T star is linear, let us take elements. Let f comma g belongs to n star and alpha comma beta are scalars. Now consider T star of alpha f plus beta g of x is equals to alpha f plus beta g of x, alpha f beta g t of x. This is defined in our statement. See here, T star f of x is equals to f of t of x, So alpha f plus beta g t of x. So it can be written as alpha f into t of x plus beta g into t of x. Again, this can be written as alpha f of t of x plus beta g of t of x. Again, it can be written as alpha t star of f of x plus beta t star of g of x. So this can be simply written like this: alpha t star of f of x plus beta t star of g of x. So that is what we prove that. Therefore, we conclude that t star of alpha f plus beta g is equals to alpha t star of f plus beta t star of g. This condition shows us t star is linear. T star is linear defined on n star. So this is the first condition. Next we prove that T star is continuous. To show that T star is continuous. To prove that T star is continuous, now define that norm T star is equals to supremum of norm T star of f such that norm f less than or equals to 1 by the definition of norm of a functional, which is equals to supremum of norm T star of f of x such that norm f less than or equals to 1 and norm x also less than or equals to 1. So again this is equals to supremum of, by the definition of T star here, norm f of tx or t of x such that norm f less than or equals to 1, norm x less than or equals to 1. So which is clearly less than or equals to supremum of norm f, norm t and norm x such that norm f less than or equals to 1, norm x is also less than or equals to 1. This is nothing but norm f is less than or equals to 1, norm x is less than or equals to 1, the whole condition is less than or it becomes norm t. Therefore, we prove that norm t star is less than or equals to norm t. Norm t star is less than or equals to norm t. Since norm t is bounded, which implies as norm t star is also bounded. Norm t star is also bounded. If norm T star is bounded, then obviously this T star is continuous. This T star is continuous because every bounded linear transformation is continuous. Therefore, we conclude that T star is an operator. T star is an operator defined on n star. That's it. So right now, by applying Hahn-Banach theorem here, this is the second part. We are going to prove norm T star is equals to norm T. We are going to prove that norm T star is equals to norm T. So next we show that norm T star is equals to norm T. So right, to prove that we use the Hahn-Banach theorem. By applying Hahn-Banach theorem, for each non-zero vector, small x in capital N, there exists a functional f naught in n star such that f naught of x naught is equals to norm x naught and norm f naught is equals to 1. This is one of the application of Hahn-Banach theorem. For each non-zero vector x in capital N, there exists a functional f naught in n star such that f naught of x naught is equals to norm x naught and norm x naught is equals to 1. Hence, we conclude like this. Therefore, f of t of x is equals to norm t of x. F of t of x is equals to norm t of x. And also, norm f is equals to 1. Norm f is equals to 1. Let it be equation number 2. Here, norm t star is less than or equals to norm t is equation number 1. So now, again, we are going to write the definition of norm t. Norm t is equals to supremum of norm t of x, supremum of norm t of x, such that norm x is equals to 1. Norm x is equals to 1, which is equals to supremum of norm f of t of x, f of t of x, such that norm f is also equivalent to 1, norm x is also equivalent to 1. So which is equals to again supremum of norm t star f of x, norm t star of f of x, such that norm f is equals to 1, norm x is equals to 1. So which is less than or equals to supremum of norm t star of f, norm t star of f into norm x, such that norm f less than or equals to 1, norm x is also less than or equals to 1, which is less than or equals to norm t star into norm f into norm x, which is less than or equals to norm t star only, because these two are less than or equals to 1. Hence, what we show that here, norm t is less than or equals to norm t star. Let it be equation number 3. Now see equation number 1. Now see equation number 1. Norm t star is less than or equals to norm t. Now see equation number 3. Norm t less than or equals to norm t star. From equations 1 and 3, we conclude that norm t is equals to norm t star. Norm t is equals to norm t star. Right. In the next part, we now show that t extends to t star is an isometric isomorphism. Is an isometric isomorphism. That is, there is a mapping pi from script b of n into script b of n star given by pi of t is equals to t star is an isometric isomorphism. So our aim is to show that there is a mapping pi that is from script b of n into script b of n star defined by pi of t is equals to t star is an isometric isomorphism. So first we show that t is linear. In this part, first we show that t linear. So first to prove that isometric isomorphism, first we show that this pi is linear, not t, this pi is linear. So right, let us take two operators t1 comma t2. Let t1 comma t2 belongs to script b of n and alpha comma beta belongs to capital R scalars. Pi of alpha t1 plus beta t2, pi of alpha t1 plus beta t2 is equals to alpha t1 plus beta t2 whole star. So this can be written as excuse me. So now we can alpha t1 plus beta t2 whole star of f is equal f whole star of f of x, whole star of f of x is equals to f into alpha t1 plus beta t2 of x, which is equals to f of alpha t1 of x plus beta t2 of x, beta t2 of x. Again, this can be written as alpha t1 star of f of x, t1 star f of x plus beta t2 star f of x, t2 star f of x. So again alpha t1 plus beta t2 whole star f of x is equals to alpha t1 star f of x plus beta t2 star f of x. So if you that is you conclude this calculation like this: alpha t1 plus beta t2 whole star of f is equals to alpha t1 star of f plus beta t2 star of f, beta t2 star of f. This is nothing but, again, this is nothing but alpha t1 plus beta t2 whole star is equals to alpha t1 star plus beta t2 star. Using this identity, now using this identity here, you can conclude like this: pi of alpha t1 plus beta t2 is equals to alpha t1 plus beta t2 whole star, which is equals to alpha t1 star plus beta t2 star, which is equals to alpha pi of t1 plus beta pi of t2. Therefore, we conclude that pi of alpha t1 plus beta t2 is equals to alpha pi of t1 plus beta pi of t2. This condition shows us pi is linear. This condition shows us pi is a linear transformation. Pi is a linear transformation. Now we show that this pi is 1 to 1. We have to prove that pi is 1 to 1. We prove that this pi is 1 to 1, 1 1 mapping. To prove that pi is 1 1. So to prove that pi is 1 1, let us take two elements. Pi of t1, or directly assume that suppose pi of t1 is equals to pi of t2. So this condition implies as t1 star is equals to t2 star. This condition implies as norm t1 star minus t2 star is equals to 0. Implies as norm t1 minus t2 whole star is equals to 0. Implies as norm t1 minus t2 is equals to 0. Implies as t1 minus t2 is equals to 0. Implies as t1 is equals to t2. Implies as t1, so this is the required condition. Am I right? Yes, required condition. Therefore, pi of t1 is equals to pi of t2 implies as t1 is equals to t2. Pi of t1 is equals to pi of t2 implies t1 is equals to t2. Therefore, we conclude that pi is 1 1. Hence, pi is linear transformation and 1 1. Therefore, pi is an isometric isomorphism. That's it. Pi is an isometric isomorphism. So, to complete our proof of the theorem, it is remaining to prove that pi reverses the product. Pi reverses the product. To prove that pi reverses the product, let us consider t1 t2 whole star f of x is equals to f of t1 t2 of x. This is from definition of t star. So this can be written as f of t1 of t2 of x. f of t1 of t2 of x. This is nothing but t1 star of f of t1 star of f into t2 star t2 star sorry t1 star f into t2 star f t2 star f. This is nothing but t2 star t1 star of f of x. This is nothing but so we prove the condition t1 t2 whole star f of x is equals to t2 star t1 star of f of x. Therefore t1 t2 whole star is equals to t2 star into t1 star into t1 star. Now the original one, pi of t1 t2 is equals to t1 t2 whole star it is equals to t2 star into t1 star. This condition shows us pi reverses the product. So next it is remaining to prove that pi preserves identity mapping. So right, pi preserves identity mapping. Pi preserves identity mapping. This is the last condition of our theorem. So right, now let us take to prove this I star identity operator. I star f of x. This equals to f of I of x. This is nothing but f of I of x. This is nothing but f of x, because I of x is equals to x. F of x is nothing but I of f of x. I of f of x. Therefore, I star f is equals to IF. I star f is equals to IF. This condition shows as I star is equals to I. I star is equals to I means pi of I is equals to I star is equals to I. Therefore, pi preserves the identity mapping. Pi preserves the identity mapping. This completes the proof of our theorem, hence proved. You see, in the statement you have elaborated statement, we prove everything. What is in the statement? We prove everything. So one of the application of Hahn-Banach theorem. Go through with the theorem. Keep learning. Wish you all the best.